Hi, I'm your instructor, Frank Kane, and we're going to learn about Spark Streaming. Why should you listen to me? Well, I spent 9 years at Amazon.com and IMDb.com making sense of their massive data sets, and I've been staying up on the latest technology. A hot new technology now is Spark Streaming, and that not only lets you process massive data sets across a cluster of computers, it lets you do it in real time as that data comes in. At the end of this course, you'll be able to use Spark Streaming to process massive data sets as it comes in real time. Maybe it's user behavior data coming in from web logs. Maybe it's sensor data from Internet of Things applications. Whatever the source, big data processing is a very hot and valuable skill these days, and Spark Streaming is an important piece of technology for it. After getting everything set up, we'll dive right into a Spark Streaming application that actually processes a Twitter feed, live tweets in real time using Spark Streaming. And after that, I'll give you a crash course in the Scala programming language. Scala is what Spark itself is written in, and it's the best choice for doing Spark Streaming. Don't worry, Scala is not too hard to learn, and I'll give you lots of hands-on examples to get familiar with the language. It's not that hard. After that, we'll go through a bunch of simple Spark Streaming examples using our Twitter data and also using some simulated weblog data that's feeding into you. And we'll learn how to process and receive and transform and output data streams using Spark Streaming. Next, I'll show you how we can actually integrate Spark Streaming into other systems, including Spark SQL, Kinesis, Kafka, Flume, Cassandra, and more. And not just theory, I'm going to show you some real code that actually works with these technologies. After that, we'll do some more complicated stuff. I'll show you how to maintain stateful information in a Spark Stream and keep track of web sessions. And we'll actually do some real-time machine learning, believe it or not, using linear regression and k-means clustering using a real-time stream of data from Spark Streaming. Finally, we'll go through setting up Spark Streaming in a production environment. What do you need to set it up? How do you get it running on a cluster? How do you troubleshoot it? How do you tune its performance? We'll go through all of that and show you how it actually works in the real world. Is this course for you? Well, if you have any programming or scripting ability, then I think you can pick it up. Yeah, a little bit of experience with Spark or Scala would help, but it's not necessary. We do cover all those basics in the beginning of the course, so as long as you have some programming or scripting experience, you should be okay. So now let's just dive in and get you set up with the software that you need. Let's get you set up with the software that you need. So all we need to do is install three things. One is a Java development kit. Reason being that even though we're developing in Scala, Scala itself runs on top of the Java runtime. So the fundamental thing that we need is a Java development environment. After that, we'll go download the Spark package itself and just set a couple of environment variables so your system knows where to find it. And finally, we'll install the Scala IDE, which will install both Scala and an IDE, the Eclipse IDE, to develop it in. That'll make life a little bit easier, so let's dive in. Let's start by installing a JDK, a Java Development Kit. So open up your favorite web browser and just type in JDK, that should bring it up. We're going to go to the oracle.com website to get that. And we're going to hit the JDK download button here. Go ahead and accept the license agreement and download the version for your operating system. For me, that's Windows 64-bit. And that will come down 187 megabytes later. All right, Chrome's going to run a quick virus scan on it, and off we go. Let's open that up. And again, this is going to install a Java development environment because Scala needs Java to run on top of. Let's go ahead and hit next. Now, I'm going to change the installation location for the Java development kit. And I just want to make it something you can remember. So, maybe C:\JDK. We're going to have to enter this into some environment variables later on, so it's important that you remember where it is and make sure it's going someplace where you have space for it. So let's go ahead. Standard Windows installer here, nothing special. We're just going to go with the defaults except for the paths. And now it's going to actually extract the installer itself, which should kick off now. Now, why it doesn't remember exactly what we said before for the installation location, I don't know. It's a little bit annoying. So let's go ahead and remind it that we want it to go into the CJDK folder. And now the Java runtime environment will be installed. And we're done. Now next we need to set some environment variables to make sure that other tools can actually find Java and the executables in it. So on your operating system there might be a different way of setting environment variables. On Windows I'm going to show you how to do it, Windows 10 to be precise, but on Mac and Linux you'll have to follow different directions. So just go ahead and look up how to set environment variables on whatever your operating system is. Probably involves modifying a bashrc file or a .profile file in your home directory, but again, it depends very much on your specific operating system. So if you're not on Windows, go look that up now, how to actually set environment variables, and then we'll come back here and take a look at what we're doing. On Windows, however, what we're going to do is right-click on the little window icon here and go to Control Panel. Click on System and Security. Click on System, and then click on Advanced System Settings. And from here, we can finally get to the environment variables. And we want to add in a Java underscore home. So I hit New there, Java underscore home, and I'm going to set that to where I install Java, which for me was C:\JDK. Another thing I have to do is add that to my path. So if I run Java from someplace outside of where I installed it, Windows can still find it. So I'm going to highlight path up here in my user variables and hit Edit. And I'm going to add in a new path that's going to use %, Java underscore home %/bin. And what that does is reference the Java home environment variable that we set and say we want the bin folder underneath that to be part of our system path. Hit OK, and hit OK again. And I'm going to leave this up because we're going to have to come back to this environment variable page for Spark. So this next step is only going to be important if you're on Windows. If you are on Windows, and you probably are, I want you to download from the resources on this lecture the winutils.exe file. And wherever you download files on your computer, go there. Hit pause and go take care of that right now, please. I'll still be here. All right, once you have that winutils.exe file downloaded from this lecture, go find where you downloaded it, right-click and hit Copy, and go up to your C drive and make a new folder and call it winutils, just like that. Okay. Now inside that winutils folder, open that up and create a new folder in there as well called bin. Okay. And now open up the bin folder and paste in that winutils.exe file that we downloaded. Next thing we need to do is set up an environment variable to tell Spark where that is. Spark won't work without this file on Windows, so it's very important. Go back to your environment variables and create a new one under your user variables. And we're going to call it Hadoop underscore home, just like that, all uppercase. And for the value, we're going to put in C:\winutils, which is the folder we created for it. All right, and with that, we have a little extra thing that Spark needs to be happy. So let's download Spark itself, shall we? So head on over to spark.apache.org and click on the handy-dandy download button here. Now, Spark 2.0 is out at this point, and you might even see a newer release depending on when you watch this course, but I want you to select Spark 1.6.2, okay? Now don't worry, all the code we're going to write in this course is actually compatible with Spark 2, so I'm not really teaching anything that's out of date. The reason I want to use Spark 1.6 is that it includes a handy Twitter class that we can use for easily connecting to Twitter streams, and we're going to use that as a fun example in this course. So select 1.6.2. We want the pre-built for Hadoop 2.6 version and a direct download. Go ahead and click on Download Spark, and that'll come on down. Now what it's downloading is a TGZ file, and that's kind of like a zip file. So if you're on Windows and you don't have a utility for decompressing TGZ files, you're going to need to get one. And the one that I like is called WinRAR. If you head over to rarlab.com, you can download it there. Just hit the download icon there and select the version for your operating system and install it. And that will give you what you need to actually just right-click that Spark installation and decompress it. So let's go ahead and do that. We'll show that in the downloads folder. And since I have WinRAR installed, I can just right-click on that and say extract to a folder. And through the magic, oh no, it's almost done. All right. So now I should have a Spark 1.6.2 bin Hadoop 2.6 folder here. Let's open that up. And here we have the contents of Spark itself, and we need to put that someplace safe. So I want you to open up a new file explorer, go to your C drive, and we're going to create a new folder called Spark under your C drive. Open that up and copy the contents of the Spark folder you downloaded and extracted into that Spark folder. So what you should have at this point is under your C drive a Spark folder that contains all this stuff. Got it? All right, let's move on. So just like we did for the JDK, I need to set some environment variables so that other things know where Spark is. Let's go ahead and do that. Back to the system properties here, we're going to hit environment variables again, and we're going to add another new user environment variable. This one's going to be called Spark_home, and that's going to be set to wherever you installed it. For me, that was C:\Spark. If you have another drive that has more room, maybe it makes sense to put there, but just to keep things consistent, we'll go with that. And just like with the JDK, we're going to add that to our path as well. So edit the path, add a new environment variable. We're going to reference the Spark_home variable we just sent, and again, add the bin path to that. All right, so double check things at this point, okay? We should have Java home/bin and Spark home/bin in our path. Again, those are surrounded by by percent signs. And make sure that you have a Java_home environment variable set to where you put Java, the JDK. And make sure you have a Spark home environment variable set to where you installed Spark. All right, that's all the hard part. We can go ahead and close out of the system control panel there. And the last thing we're going to install is the Scala IDE. And to get that, you can just go to scala-ide.org and go ahead and download it. So get whatever makes sense for your OS. For me, it's Windows 64-bit. Go ahead and get that. Notice that it has a requirement of JDK, which we already installed as our first step. And that should come down in a couple of seconds. All right. Now the thing with Scala IDE is that it's built on top of Eclipse, so there's nothing to install really. You just go ahead and unzip that, right-click on it, extract all. And we'll wait for that to decompress. There's quite a few items in there, so it will take a little bit of time. Through the magic of video editing, we'll come back when that's done. Okay, it finally decompressed and left us opened in this extracted folder here that contains an Eclipse folder. And all we need to do to install Eclipse is to copy this folder someplace where we're not going to lose it. So I'm going to hit Control-X to cut that out of my Downloads folder, and I'm going to stick it on my C drive. Paste. And that will just copy it over. And if you want an easy way of getting to it later on, you might want to consider creating a shortcut to where you put that. So if you go to open up Eclipse, Eclipse.exe is actually the Scala IDE itself. So you might want to right-click on that, drag it to your desktop, and say Create Shortcut here. And that will make it a little bit easier to get there in the future. All right, let's just make sure everything's working at this point. So if you right-click on here and go to Command Prompt, I have a handy-dandy prompt for this in my taskbar, but if you don't, you can just go here. And let's CD to where we installed Spark itself. So that was C:\Spark. Obviously, if you're in a different OS, the path will be different. So on Windows, I'm going to do a dir, see what's in this directory. On Linux or Mac OS, it'll be ls. And looks like we have some stuff in here. There's a changes.txt file. So let's do a little simple Spark program to count up the number of lines in that file. So let's type in spark-shell. And that should bring up an interactive Scala prompt with Spark all set up for us. Looks like Windows Firewall wants us to open a port. That's fine. Hit Allow Access. And that's pretty cool. So we have a Spark environment spinning up here. All these info and warn messages are normal, so don't worry about them. But look, we have a prompt. We can actually write some Spark code. Let's do that. So here's your first Scala code ever. Val text file, pay attention to case, it matters, equals sc.text file, open parentheses, quote, changes.txt. All right. And we actually just created an object in Spark called a resilient distributed data store based on top of that big text file. So now we can just call methods on that thing. Text file.count, for example. And that will count up the number of lines in that file, 34,960. Woo! So, what's in there? Let's do like a text file dot, I don't know, take 10. Gives me a little array of the first 10 lines of the file. Pretty cool stuff. So hey, it's actually working. We're actually writing some Spark code here. How cool is that? Now, if you're seeing some error messages or something like that, go back, double check your environment settings, make sure that all those environment variables are correct, make sure everything's installed that you need. If you follow those instructions, it should be working. If not, go ahead and post a question on the course and we'll try to help you out. But at this point, you should have a working Scala environment. Go ahead and quit it with an exit command, and we're back to the command prompt. So up next, we'll actually write a complete Spark streaming program in Scala that prints out live tweets. So let's go ahead and do that next. So congratulations. Believe it or not, you just got through probably the most tedious and difficult part of this course. Getting all that stuff set up properly is a bit of a chore, but hey, you got it done now, and we have an actual working development environment now for Scala and Spark streaming. And hey, we actually saw it running. We actually ran a little bit of Spark code there to analyze a little text file really simply. So, woo! Time to rock and roll, right? So next lecture, let's actually do something with all this stuff we installed, and we're going to play around with some Twitter streams and see what we can do with them. Let's check it out. All right, let's stream some tweets. We're going to write our first Spark streaming application and just show you how it works. So to do that, first we need to set up a Twitter developer account and get some access tokens so that we can actually programmatically receive live Twitter updates as they happen. So let's head over to apps.twitter.com, https apps.twitter.com, and show you how to get that all set up. Okay, here we are at apps.twitter.com, https apps.twitter.com. So if you don't have a Twitter account, you will need one to go through these examples, and there are a lot of examples in this course that use Twitter data. So if you need to go create a Twitter account, hit pause now and go take care of that. Assuming you do have one, go ahead and hit the sign in link here and log in with whatever your Twitter account information is. And you should see something like this. Now, I already have an application set up. You won't see anything there yet, but what you will see is this Create New App button. So go ahead and hit that. And give your application a name. It doesn't really matter what. Let's say Spark Streaming Course Examples. And description can be whatever you want. Playing with Spark Streaming. And if you have a website, you can enter it here. You do need to enter something here. But again, I don't think it really matters what. Don't need a callback URL. And go ahead and read through the terms here. Make sure there's nothing you find objectionable. And assuming everything looks okay, hit yes, I agree, and create your Twitter application. And you should see this. So hey, we're getting somewhere. We have a consumer key already. Now I'm not going to bother blurring out all these keys and access tokens because I'm going to delete this application when I'm done. So they're not going to do you any good. Make sure you write down your own when you get them. So, okay, we're making good progress here. We have application settings here. We also need a access token though. So we're going to click on keys and access tokens. And we are going to say, create my access token. And there we have it. So here's all the information we need to actually have Spark Streaming connect to Twitter and start receiving live Twitter information. Pretty cool. So keep this up. You know, we're going to need this next. Now in the resources for this lecture, you should see a twitter.txt file. So go ahead and download that. And while you're at it, download the other files in there too. There should be a twitter.txt file. There should be a printtweets.scala file and a utilities.scala file. So download all of those to wherever you download stuff. And we need someplace to put it all. So go to your C drive or wherever you want. And I want you to create a folder for wherever you're going to keep all the stuff for this course. So I called it Spark Streaming Course. So go ahead and create a folder like that on your C drive, or if you're on Linux or Macs, on your home directory somewhere. And in there, I want you to copy the twitter.txt file that you downloaded from the resources for this course. Go ahead and open that up in a text editor. And you'll see that I've already copied and pasted in all the consumer keys and secret keys that are from that Twitter page. Now you're just going to see blank values here for these actual values. So go ahead and copy and paste them in from here. So you'll see there's a consumer key, a consumer secret, an access token, and an access secret here. All you need to do is copy and paste those values into these lines next to each key. So make sure when you're done, you have a field name followed by a value on all 4 of these lines. And again, these are all expired credentials, so don't bother copying these from the video. They won't do you any good. But once you have your own in there, go ahead and close that out. And now you are set up for connecting to Twitter. That's all the information we need. So let's actually run some code, shall we? All right, now that your Twitter credentials are set up, let's go ahead and open up Eclipse. You probably have a shortcut still from when you installed it. And if you've done Java before, this will all look very familiar. Now I want you to set your workspace to wherever you put the stuff for this course, the folder that you made to put that twitter.txt file in. So that was C Spark Streaming course when we went through it in the video. If you put it someplace else, enter that here. Hit browse if you need to find it, but do not leave this to the default setting. You want the workspace to be the stuff where you're putting, the place where you're putting the stuff for this course. So do that, hit OK, and up will come Eclipse. Difference being this is set up for Scala as well as Java. So first thing we're going to do is create a new project. Go to File, New Scala Project. And we'll call it, I don't know, Spark Streaming Examples. How about that? Hit Finish. And we're going to right-click on that, hit New Package, and we'll type in com.sundogsoftware, like that, .spark streaming. And that's just my domain name, so it's available. I can use it safely. That's what we're using in this course. So double check the spelling and all that, com.sundogsoftware.sparkstreaming, and hit Finish. Now we need to actually import some source code. So hopefully you already downloaded the printtweets.scala and the utilities.scala files from the resources for this course. If not, hit pause, go take care of that now. When you're ready, right-click on this new package we made and say Import. And we're going to go to General and say from the file system, we want to go to your download folder, wherever you downloaded those files to. So for me, that's C downloads. And we should see these two files that you just downloaded. So select both of those and hit Finish. All right. Open that up. We can open up the printtweets.scala file, take a look at it. This is all the code we need to actually connect to Twitter and start printing out some tweets in real time, so using Spark Streaming. Now the good thing about Eclipse is that it can tell us when there are problems. You see there's a bunch of menacing looking red X's here and whatnot telling us that there's a problem. Problem is we haven't actually set up the Scala IDE to work with Spark yet, so we need to take care of that. Go ahead and right click on the Spark Streaming Examples project and click on Properties. And we're going to go to the Java build path here and click on the Libraries tab. First thing we have to do, double click on the Scala library container, change that to the latest 2.10 bundle, because that's what Spark is built with currently. And we're going to add in the Spark libraries. So hit Add External Jars, and from there navigate to the lib folder of wherever you installed Spark. So if you followed along with the setup video, that will be C Spark lib. Go ahead and highlight all of those and hit Open to import all of those Spark libraries into our project and hit OK. And if we give things a minute here, everything should be a lot happier. Yay, all my X's went away. That's a good sign. All right, let's go ahead and run this puppy. So go to Run and select Run Configurations, because we need to tell it what our class is that we're starting with. Click on Scala Application, double click that. We'll give this configuration a name called printtweets. And the main class, make sure you enter this carefully, is going to be com.sundogsoftware.sparkstreaming.printtweets. Just like that. Pay attention to capitalization because it all matters. All right. Hit pause if you need to. Double check that again. Look good. All right, let's hit run and see what happens. You might get a little pop-up from Windows saying that it wants you to allow something through the firewall. If so, go ahead and allow that. And look at that! We're getting tweets in real time. This is an actual Spark streaming application connecting to Twitter and actually launching 4 different processes on all 4 of our cores to actually connect to Twitter, suck in all the information it can, and every batch of information is printing out the top 10 tweets that it gets. Now, mind you, Twitter is not always safe for work. If you see something nasty and offensive in here, it's not my fault. There's some bad people in the world, but hey, check it out. You're actually doing Spark streaming right now. That wasn't that hard, was it? You can just sit here and watch things scroll by. Kind of interesting how English isn't quite as prominent as you would think in the grand scheme of things on Twitter. When you're done looking at things, Just hit that red stop button to actually terminate the process. And how cool is that? Your first Spark streaming program. We'll go through what it's doing in more detail later on, but feel free to take a peek at the code here. You know, you're looking at some Scala code here, and next we're going to go through Scala and introduce you to the different quirks of the language. It's not that hard. You can kind of figure out what's going on here. Just like any programming language, we have a little function we call to set up our Twitter credentials based on that twitter.txt file that we set up. We set up a streaming context, which is kind of what creates the objects that we work with in Spark streaming. Reduce our logging level to something a little bit more manageable. And then here's where the magic happens. We create a stream from Twitter. And from that stream, we can actually call this function to extract the text from each tweet as it comes in. And it's doing all this in a distributed manner, potentially across a cluster even. And then as that information comes in, each batch, it's going to print out the first 10 results from each batch. And just keep doing that over and over and over again once we start it, and just wait for termination. So that's all there is to it. That's Spark streaming actually working. Woohoo! It's working. All right, congratulations. You actually got a real Spark streaming application up and running there. Pretty cool stuff. All that setup actually paid off finally. Congratulations. So next, let's try to focus on understanding what really happened in there. To do that, we're going to have to cover the Scala programming language first. And that's what we're going to do next, a little crash course in Scala. So let's soldier on, shall we? So the next 4 lectures are going to be a crash course in the Scala programming language. Scala is a very popular choice for programming in Spark and Spark streaming because Spark itself is written in Scala, and it's a lot easier to use than Java for this sort of a thing. So let's just dive in and learn about some Scala code. All right, let's start our crash course in the Scala programming language. It's going to make life a little bit easier when we're programming in Spark and Spark streaming because it's a lot simpler than Java, and yet it has all the latest and greatest features of Spark streaming available to it, unlike Python. So let's dive in, and at the end of all this, hey, you can say you've learned Scala and you've learned maybe functional programming as well. It's kind of a big buzzword these days. So why are we learning Scala? What is it? Well, yeah, it's yet another programming language. Seems like every month there's a new one these days, you know, Go or whatever we have. Anyway, Scala is what Spark is built with, so it's a very good choice for doing your Spark programming. You're going to find out that it looks a lot like Python code in Spark if you've done Spark work before with me. Syntax is a little bit different. The advantage, though, is that new features in Spark are often developed first with Scala and Java support. So by having Scala under your belt, you can take advantage of new developments in Spark quicker than if you were just limited to Python. Now, Scala runs on top of the Java virtual machine, so as long as you have a Java runtime environment installed, you can run Scala code. Under the hood, it just gets compiled down to Java classes. It's just a little bit of a simpler syntax on top of it. And it's also built on the concepts of functional programming, so basically we have lots of little functions that are treated as objects themselves that we can pass around, and you'll see how that works shortly. So let's just dive in and learn some of the quirks of the Scala syntax, and we'll start off with some real basics of the language, you know, setting up variables and printing stuff out and all that good stuff. So let's dive in. All right, let's learn some Scala, shall we? So first thing I want you to do is go to the resources for this lecture and download the learningscala1.sc file. That's a Scala workbook file, worksheet file. And just download that wherever you download your stuff, your downloads folder, and hit pause while you go take care of that, please. I'll stay here and wait for you. Done? All right, let's move on. So I've opened up the Scala IDE here by opening up my Eclipse shortcut on the desktop. And what I want you to do next is go to the File menu and say New Scala Project. And let's call this project Learning Scala, shall we? Just like that. All right, now we do actually need a separate project for these worksheet files, and well, the reasons are complicated. Basically, there's a conflict with the Scala version that we used in the other project, but just go with it. So go ahead and right-click on that Learning Scala project and hit Import, and go to the File System, and select whatever folder you download stuff from your browser into, wherever you downloaded that Learning Scala 1 file. So for me, that's the C Downloads folder. And we'll select learningscala1.sc and just hit Finish. And we should have, if we open up Learning Scala, learningscala1.sc. So go ahead and double click on that, and here we go. Now what we're looking at here is what's called a Scala worksheet. It's kind of like a notebook in Python in that you can actually interactively enter commands and see them evaluated right in line there. So you wouldn't, go and write a real script this way, but it's a good way to get familiar with the language and just sort of experiment and try different commands and you can immediately see the effect they have. So what's going on here is, you have a line of code, and after you evaluate it, which happens automatically whenever you save the worksheet, it will tell you over here on the right the actual output from the Scala interpreter that resulted from that command. So very good way to see, what you're typing in for code and the result that code has immediately. Pretty cool stuff. So let's just dive in and take a look at some of the Scala code. So, every language has variables, right? And variables can be mutable or immutable. And mutable means they can be changed. Immutable means they can't be changed. So in other languages, that might be a constant variable or a final variable, depending on the language we're talking about. Now in Scala, they encourage the use of immutable variables as much as possible. And those are called values with the keyword val. So the syntax here for declaring a string value is a little bit unusual. Let's look at what's going on here. So we have val, meaning that it's an immutable constant. We're going to name this immutable constant hello. It's going to be of type string, and then I set its value to hola. So val hello, colon, string equals value. So the syntax here, val, meaning it's immutable. Hello is the name of the variable. Colon, and then the type equals whatever it is. Okay, so that's how we declare an immutable value in Scala. Now, just to show you that it actually works, let's change that to, I don't know, what's French for hello? Bonjour. Now, watch what happens when I hit Control S to save it. This actually all gets interpreted again. Unfortunately, it goes to the bottom of the file whenever I do that, but if we scroll back up, we can see that it now says hello string equals bonjour. And we can print out the value of that string with a print line command. So in Scala, that's how you print out a line of output. Print line, parentheses, hello, the value name, will print out, output the value bonjour. So there you have it. Very simple string, very simple there. Now, although Scala encourages using immutable values, you can also use mutable variables as well if you need to. Sometimes you just can't get around it. So if you need to do that, you use the var keyword instead of val. So here we have an example where we have hello there, which is initially set to the value that we had in hello, which you remember we sent to bonjour. So here we are assigning a variable called hello there and assigning it the value hello. Hello referring to this value up here that contains the string bonjour. With me so far? Makes sense? If you've done any programming before, you can probably follow along what's going on here. So at this point, the value of the hello there variable is set to the string bonjour because that's what my hello value was set to. Now, because it's a variable, I can actually change it. So I can say hello there equals hello plus the string there. So I'm changing the value of hello there from bonjour to bonjour there. And you can see that when I print that out, indeed, it does contain bonjour there. And just for fun, we can change this back to hello up here. Watch everything get reevaluated when I save it, and now it says hello there instead. Okay, so you got it. Basically, there are vals that are immutable, vars that are mutable, and the syntax in Scala is a little bit weird for declaring things. You have the variable name colon type equals whatever you're assigning it to. Okay, so that's a little bit backwards for most languages. Takes a little bit of getting used to, but you'll get the hang of it. All right. So one thing I want to point out is that in functional programming, we're using a lot of functions. And the danger of that is that if you have a function that quietly changes the value of something behind your back, that can lead to bugs. It can lead to unexpected behavior. So in functional programming languages like Scala, they really encourage the use of immutable constants whenever possible. So you want to be using vals whenever you can instead of vars. So instead of using a mutable constant and modifying it as you go, create new immutable constants and build them up over time. So here's an example of how that works. So let's say I start off with an immutable hello there that is initially constructed from the concatenation of whatever's in my hello string and the string there. So initially I'm just putting hello there into my immutable hello there. So you see here I'm actually doing the combination here on the right hand side here and putting it into the final value where it won't be changed. Now, you can change these together. So let's say I want to add something else here. Let's say I want a new val that's immutable. More stuff. And I can set that to immutable hello there plus, yeah, I don't know, I'm just making this up as I go, right? So let's see what that does. So now I have hello there, yeah. And basically, you know, I still have two values here. One's called immutable hello there, one's called more stuff, but I never changed the value of immutable hello there, and I never changed the value of more stuff after it was initially created. Okay? So I kind of like always know what's in this symbol, this name here. It doesn't change, and that makes coding a lot more safe. If I need to go back to that value, I can just refer to it by its original name, and that's the best practice for dealing with functional programming. Now, one thing I want to point out too, notice that I didn't actually declare the type here. Scala can actually implicitly figure it out in a lot of cases, so I didn't have to say val immutable hello there colon string, because it knows that I'm sticking together two strings and that produces a string object in return. So in cases where there's really no ambiguity over the type, Scala can infer it for you automatically, and you don't actually have to do that colon type name syntax all the time. Okay? Some other types. We've been dealing with strings so far, but there's all the usual suspects here. If you want an integer, it's just an int type, capital I. We also have Boolean values. That can be true or false, lowercase are the keywords there. If you want a single character, you know, basically a 256, one of 256 characters, 8-bit value, represented as an ASCII character, you can use the char type. Double precision floating point is double, single precision is float, and notice that we have the usual f suffix here indicating a floating point constant. Scala is a little bit pickier than other languages in enforcing that you use that. So if you are using single precision constants, make sure you remember to put that f at the end. Double wide integer is a long, and we also have a 8-bit value called byte, just like in Java, that ranges from -127 to 127. And you'll find a lot of these types are very analogous to the types in Java, reason being that Scala is built on top of the Java virtual machine, so there's a lot of transparency between the two languages. All right, moving on. Want to take a break now? It's fine. Go get a drink. You know, hit pause. It's all right. But let's talk about printing stuff out. So a common thing you need to do in a language is output human readable stuff. Very simple to do in Scala. If you just want to tack a bunch of stuff together, you can just use the plus operator to do that. So you can see I have a bunch of different types of information up here, and I can just mush them all together with the plus sign here and create a big old giant string. So print line, here's a mess. I'm starting with a string, and then I'm concatenating on the number 1, a Boolean value, a character value, a double precision value, and a long value all together. And when we print all that out, we get exactly what you would expect. Here's a mess followed by all this stuff jammed together in the form of a string. And that all just happens automagically. All right. Now sometimes you need to format numerical output, and you might be familiar with the printf style of output in other languages. Scala supports that too, but the syntax is a little bit strange. So what you do, if you want to do formatting of that nature, you need to prefix your string with the character f, and that expands to a little macro that says I'm going to use a printf style format within this string. So here we're saying print line f, meaning that I'm going to be formatting the text in here somehow, and I'm going to say pi is about. Then I have a $sign followed by the variable name that I'm going to be formatting, followed by a %, and then the printf format for how I want to display that. So in this case I have 0.3f, meaning that I want to display a floating point value with 3 decimal points of precision on the right hand side of the decimal point. And if you're not familiar with that syntax, you can go look up printf on the interwebs and get more details, but pretty common tool for formatting your output if you need to make sure that it's human readable and only has a reasonable amount of precision. And if we run that, we see sure enough pi is about 3.142. So that took the value of pi single precision, which is 3.141599265, applied this formatting string to it, 0.3f, and that made sure that we only had 3 decimal points, places of precision, to the right of the decimal point. Here's another example. You can also use the same trick for putting 0 padding on the left of numbers. Sometimes that's useful for sorting strings, for example. So in here we have the f prefix again, $sign by the variable name number 1. In this case it's an integer, which is the number 1, and we're using a %sign followed by the formatting string, which is 05D. The D means that it is an integer value, and the 05 means that I want 5 places of precision with zeros padding it in if necessary. And the output from that is with 5 decimal places, 00001. Okay? All right, another trick we can do is actually substitute in variables as part of our string as they're being constructed. So for that, we use the S prefix, and then anything that's preceded by a $sign will just be interpreted as a variable or a value name. So we have this S prefix. I can use the S prefix to use variables like $1, and that will pull in the integer value 1 up here. $truth, which should pull in true. $letter A, which should pull in the character A, and sure enough, it works. When we evaluate that, we get, I can use the S prefix to variables like 1, true, A. And you can also do fancier stuff. You can do more than just reference values and variables. Here's an example where we actually evaluate an expression. So again, that $sign means I'm about to evaluate something, and it might be a variable or a value name, or it might be a whole expression. So if you put something within curly brackets, that basically says, I got a little bit of code here that I want to execute. And you can put whatever you want in there. It might be like a little tiny little function even. But in this case, we're just going to add 1 plus 2 together. And sure enough, it works. When we actually run that, we get the S prefix isn't limited to variables. I can include any expression like 3. So $sign brackets 1 plus 2 just got converted to the value 3 inside that string automatically. So very handy tools for producing output when you're printing stuff out or writing it to a file or what have you. All right, the next section gets a little bit weird. So again, if you want to rest your brain a little bit, let that previous stuff sink in, that's okay. But let's move on. Now, if you're familiar with regular expressions, they can be a powerful tool for pattern matching strings and extracting information out of structured, formatted data. So let's say you have, for example, an Apache access log that has a very specific format. You might use a regular expression to extract fields out of that line of log information. And we do that in this course later on, quite a bit actually. So, for example, let's say I start with a string that has to life, the universe, and everything is 42, and we're going to call that string the ultimate answer. If you read Douglas Adams, you know what I'm talking about. So the syntax for handling regular expressions in Scala is really weird, okay? It's going to blow your mind. It's strange. Nothing I can do about it. Sorry, you just have to live with it. What we have is this strange triple quotes syntax followed by a .r. And that basically means I want to construct a regular expression out of the stuff in between the triple quotes. So if you're familiar with regular expressions, you'll know what this all means. .star means extract a bunch of characters, then look for a space, and then we're going to look for one or more number characters. That's what the \d plus means, followed by a bunch of other characters. So basically this is saying, go look for the first number in this string. So I'm trying to suck out the 42 out of this string, basically. Now, regular expressions is a whole topic in itself. There are multiple O'Reilly books on the subject that you can do some very, very fancy and some very complicated things with them. So if you want to learn more about regular expressions, go look on the internet or try out the Introduction to Regular Expressions book from O'Reilly. That's probably a good start. But odds are you've seen these before. And if you haven't, you can usually find the one you need on the internet if you just look. I'll provide you the ones you need in this course for logs, for example. So don't get too hung up on the syntax. But the way it works in Scala, like I said, it's pretty weird. So we have this regex that we created using this .r operator here. And what we're going to do to apply that, it's really weird how this works. You take that regex and you pass in where you want to put the result that you extract information from. So we're going to basically try to pull out that number from the string and put it into a new value called answer string. And then we use the equal sign to say, well, I want to run this on the string called the ultimate answer. And, you know, the syntax of this really defies human logic. You just have to kind of go with it. You know, it's something about Scala that I just don't like. But keep this worksheet around for reference. So if you do need to do some regular expression stuff later on, you'll have this to look at, because it really doesn't make intuitive sense at all. Anyway, what that does is it does apply that regular expression to this string, extracts out that number 42, and sticks it in the string answer string. Last thing we need to do is, because that is a string, but we really want to treat it as a number, we can call toInt on that string and extract the integer value 42. So toInt will convert any string to an integer. And, you know, like you might expect, there's also toFloat or, you know, whatever else you might need. Conversion operators there as well. Notice that I didn't actually have to put a open and close empty parenthesis there. That's not actually necessary. And we print the answer, we get 42, okay? So honestly, this is about as weird as Scala gets. If you made it through that, it's all It's all downhill from here. Okay, it's going to be easier. As promised, with getting easier, Booleans work much as you would expect. So if you just want to compare two things, if 1 is greater than 2, well, no, the answer is false. 1 is less than 2 will give you true. One thing that's a little bit ambiguous in some languages is what does 1 ampersand versus 2 ampersands or 1 pipe versus 2 pipe do, when you're doing and or comparisons. You can do either one in Scala. The only difference is that if you use a single ampersand, both expressions get evaluated and then, anded together. Whereas if you use a double ampersand, that means that it can actually bail early. So if is greater were false, it would actually not even bother evaluating is lesser at all, and would go left to right, only as far as it needed to. So for performance, you'd probably want to go with the double ampersand usually. But for safety, a single one might be better because you might have some expression in there that you assume gets run, and it might not if you're using a double ampersand. Either way, here you get the same answer. You can't be greater and lesser at the same time, so both of these provide a result of false. String comparisons, also something that works differently in different languages. In Scala, it makes sense when you compare two strings using the equals equals operator. It actually compares the contents of the string and not the string objects themselves. So if I set one string equal to Picard, and I have another string called best captain that's also set to Picard, if I test Picard equal best captain, it compares the contents of those strings and says true. And, well, I don't want to get all nerdy on you and debate the values of Star Trek captains, but we'll leave that for an exercise to the reader, shall we? All right, so that's lesson 1 with Scala crash course. Some basic stuff here. All we did was cover, the syntax for declaring mutable and immutable variables. We looked at some different Boolean operators, some ways of printing out information, applying regular expressions, and you have what you need to do a little exercise here, so make it real. So while you're in here, like I said, you can just add in code here and hit save and it will get evaluated right away, so play around with it. My challenge to you is to write some code that takes the value of pi, doubles it, and then prints it within a string with 3 decimal places of precision to the right. So you should have enough examples within this worksheet to do that pretty easily. This isn't meant to be difficult, but I just want you to get your hands on with some Scala code, actually get comfortable with the fact that, yes, you can write Scala code yourself and actually make it run and operate. So please do that exercise, even though it does seem trivial. It will be helpful. So do that, and we'll move on to the next lesson. All right, moving on. This next topic's going to be a little bit easier, a little bit more straightforward. We're just going to talk about flow control in Scala. So to get started, go ahead to the resources for this lecture and download the learningscala2.sc file, wherever you download stuff, and I will sit here and wait for you. So hit pause and take care of that, please. All right, let's move on. So we're going to right-click on Learning Scala, our Scala project here, and say Import, and go to the file system, browse to wherever you download your stuff. For me, that is, C Downloads. And select learningscala2.sc and hit finish to import that into our Learning Scala project. And double click on that and you should see this. So let's just talk about flow control. How do we control the flow of our code in Scala? It's all pretty intuitive. There are a few syntactical differences from other languages, but by and large it should look very familiar to whatever language you're already familiar with. So, for example, you can use if-else syntax. If 1 is greater than 3, print line impossible. 1 isn't greater than 3, else print line the world makes sense. And sure enough, that will output the world makes sense. Now I could also put brackets around this if I wanted to make it more than one line. That's okay. You'll see that down here where I'm actually splitting it out to be a little bit more readable. Often in Spark code, you see people jam things onto one line just because they can, and that's kind of a common attribute of functional programming, I'm afraid. But either way works, so that's fine. There is no else if operator, so you would have to actually do another, else after that if you wanted to. And that's all there is to that. If and else works just the way you would expect. Now, matching. So let's say you have like a switch statement in other languages where you have a value and you want to have different cases where you do something different depending on what value that variable has. So in Scala, that's called a match statement. So instead of switch, we use match. Other than that, pretty similar. So let's say we start with a constant value number that's set to the number 3. We can set number match would be the syntax here. So I want to match on the value of number, and for case 1, So you have this little like equal sign greater than thing that sort of says, you know, associate this function with that case. So that could actually be a whole expression if I wanted to, but in this example, we'll keep it simple. So in case 1, we're going to map that to println 1. Case 2 will be mapped to println 2. Case 3 will be mapped to println 3. And then this underscore is basically your default, your catch-all case here. So case underscore, meaning it's something that's not 1, 2, or 3, will printline something else. But in this case, our number is 3, so it falls through to the case 3 and prints 3, which indeed works. So again, you know, there's nothing really complicated going on there. It's just like a switch statement in other languages, but the syntax is a little bit different. We have match followed by the value name here, which is a little bit backwards from other languages, and we have this little mapping operator here, equal greater than, to actually map cases to what you want them to do. So that's the syntactical trickery there. For loops, nothing special about them. Well, a little bit syntactically. So look at what's going on here. We have for x 1 to 4. So basically we want to iterate through the values 1 through 4 inclusively. The only weird thing here is this little less than dash syntax here, and that is basically a range operator in Scala. So this says I'm going to take the value x within the range of 1 to 4, and it's going to create, you know, a list of 1, 2, 3, 4 and iterate through that in this for loop. So we will take here the square of each value. So for each value 1 through 4, I'll multiply it by itself and print the result. And we see 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and 4 times 4 is 16. So the for loop syntax itself is exactly what you would expect, but we have this new range operator here that's something new. So remember, that's how you specify a range of values in Scala. While loops, absolutely nothing interesting there. It works exactly the same as it would in other languages. So let's say I start with a x variable set to 10, and I want to iterate through this while x is greater than or equal to 0, while I subtract 1 for it as I go, printing the values. So, you know, there's really nothing fancy there at all. It does exactly what you would expect. We start with 10, and as we print the value and then decrement it, we'll keep on going until it hits 0. So 10, 9, 8 all the way down to 0. Just like in any other language. And just like we have while loops, we can also do while loops. Also, just like in any other language, there's really nothing Scala special here going on. We have basically starting with the value of 0, do, print the value, increment it by 1, and do that while x is less than or equal to 10. So instead of counting down from 10 to 0, we're going to count up from 0 to 10 using a do while loop. Again, if you have any prior programming experience at all, I'm sure you've seen this all before, and there's really nothing special about it when it comes to Scala. Works this way, you would think. Now, one thing I want to talk about, though, is expressions in Scala. And one thing that is a little bit different is that when you have a block of code like this, let's say I'm starting with the value of x equal to 10, and then I'm going to add 20 to that. Now, in other languages, that wouldn't actually do anything because we're not actually returning anything from that expression. But in Scala, this has an implicit value. So whatever the last expression is, will be what this expression as a whole is set to. So I can actually take this expression and use that as the value 30. So take a look at this. I can say println this expression, val x equals 10, x plus 20. That expression gets evaluated, and the number we're left with at the end is 30. So this all gets translated into the value 30, which actually is what gets printed out here, okay? So we're starting to touch on some aspects of functional programming here where expressions can actually be used as values of their own, okay? So that takes a little bit of wrapping your head around. So stare at those two lines a little bit longer and make sure that sinks in for you. Okay. Now just get your hands dirty. A little simple example here. You probably see this on a lot of sort of simple job interviews too. Print the Fibonacci sequence in whatever language you want. In this case, I want you to do it in the Scala programming language. Not hard. All you have to do is write a little loop that goes through the numbers 0 through 10, and the expected output should be something like this, where every time you go through the loop, you're adding in the sum of the two numbers before it. So basically you need to write a loop that keeps track of the previous two values, sums them up as you go. So a little exercise in some flow control and doing some looping in Scala there for you. Have at it and have some fun with it. So I just want you to get your hands dirty. And again, just get some confidence that you can actually write Scala code that runs. All you have to do is write your code in here, and every time you hit Control S to save, it will get evaluated for you, and you'll see the result right alongside your code. So give that a try and see how it goes. On to the next lecture. Moving on, like I said, Scala is a functional programming language, so now it's time to talk about functions, which are obviously very important in Scala. So, go to the resources for this lecture and download the Learning Scala 3.sc file. Hit pause while you take care of that. And just like before, we're going to import that into our project as well. So again, right-click on Learning Scala project, go to Import, go to File System, and select the folder where you download your stuff to, whatever that might be, and select Learning Scala 3.sc. Finish, and you should see it here in your project. Let's double-click that and take a look. Should look like this. All right, so let's talk about functions in Scala. Very important lesson here. Like I said, functional programming. This is kind of the building blocks of it. So syntax for a function in Scala, it looks like this. You start with def, which basically means I'm declaring a function of some sort, followed by the function name, in this case squared. I'm making a function that just squares some value. And the syntax, again, is backwards from what you might expect from other languages. So we start with a parameter of x that is of integer type. The way we say that is x:"int. And then the return value of this function is an integer as well. So we have another colon after that function name declaration in the parameters that is followed by the type that is returned by the function. So again, this is totally different from what other languages might do. Usually you would see int squared int x. Instead in Scala, it's squared x:"int. So just it takes some getting used to, but make sure you understand what's happening there. So again, def means we have a function followed by the function name, our parameters, which have a colon that specifies the type of each parameter, and then finally another colon followed by the type that is returned by the function. And then another thing that's a little bit different is that we have an equal sign between that and the actual brackets for the function, because we're basically taking this expression and assigning it to the square it name, okay? So a little bit different there too. But inside, all we're going to do is say x times x. And again, this is an expression, so remember from the previous lecture that we don't have to actually explicitly return anything. Whatever the last value computed in that expression is what gets returned. So this is all we need for a function that actually squares a value. So let's take a look again. Square it, takes in an integer, returns an integer, and it applies this expression to it, x times x, to actually get the square. Now we can do something similar here for cubing. Again, def cubit takes in an integer x, returns an integer, and uses the expression x times x times x to compute what gets returned. So let's see it in action. If we do println square it 2, you just call the function like you would in any other language. That will return 4. And if you println cube it 2, that will give 8, because 2 cubed is 8 and 2 squared is 4. All right, nothing too crazy yet. This all kind of makes sense, right? Things get a little bit weird now. So remember I said before up here, we're basically assigning this expression to that function named square it. So basically every function in Scala is kind of its own little object, and you can pass these functions around to other functions like they are objects themselves. So that makes a lot more sense with an example here. Let's make a new function called transform int. And what this function does is it will take a function to transform an integer, it could be any function, and apply that to some integer. So our parameters here in this example are going to be an x, which is an integer that we want to transform, followed by a function that transforms an integer to another integer. So we are taking in here as a parameter a function that expects as input one parameter that is an integer and returns an integer. And that's what this syntax here means. Takes in an integer and it outputs an integer as its result. And the return value of this function itself is an integer set equal to f of x. So we're going to take the function f passed in and pass in the parameter x that was passed in, and what gets evaluated is that function f applied to that value x. So let's see how that works. So for example, we can call transform int with the value 2 and the function cubit. So this will pass in the value 2 to x and the function cubit to f. The function will then take the function cubit and pass in x to that and return the result. So that gives us back 8, because that will pass in 2 to the cubit function and return 8. And we can print the results, and there it is. Now, for example, we could change that to be square it. Let's just make sure it works. Hit save. Sure enough, we get 4 now, because now I'm passing 2 to the square it function. So, you know, you might want to take a little break here, make sure that sinks in. This is kind of a very fundamental and very important concept of functional programming, that you can pass functions around as parameters themselves, okay? I mean, other languages, this is still possible to do, but you don't see it as often, okay? So very important that you understand how that's working. So stare at these little lines of code here. Make sure you understand what's happening there before you move on, okay? Now, you don't even need to have a separate function declared for this trick to work. You can actually declare these functions in line as well. And if you've worked with me on my other Spark class in Python, this is very similar to how a lambda function in Python works. It also goes by the name of anonymous functions, or function literals is a popular term in Scala. But you're going to see a lot of this, so make sure you understand the syntax of what's going on here. So here I'm calling transform int, and instead of passing in a named function that I already declared, I'm just passing in the expression itself. So I don't even need to have a separate function at all. I can say I'm going to pass in the parameter 3, and I'm going to pass in this expression that takes in a value x and transforms it using the expression x times x times x. And this becomes my entire function definition that I pass into that function. So instead of having a separate qubit function, I can embed what qubit does just right here within this call. So this is perfectly valid syntax in Scala. I can say I have some value x that gets transformed using equal greater than to x times x times x. And that actually works. You can see here that if I pass in the value 3 to transform int, and I pass in this function, x gets transformed to x times x times x, it actually works. It will pass in 3 into x and execute that function on it to get the number 27 as a result. Okay, let's look at it again. So here's another example. I'm using the same transform int that just takes as parameters some integer and some function, and in this case the function, the only requirement is that it transforms an integer to another integer. I'm taking x and transforming it to x divided by 2. So in this example, 10 gets transformed into 5 that way. Okay. One more time, we can do a more complicated expression here. So instead of just a simple one-liner, we can actually do a multi-line expression as well. And in this example, we're going to take the value 2 and pass it into this function that transforms x into this expression that actually does a couple of different steps. It takes a value of y that's equal to x times 2 and then squares that resulting value, and that becomes the end result of that expression. So we take 2, assign y to 2 times 2, which is 4, and then we multiply y times y, 4 times 4, to get 16. And that is indeed what we get back. So make sure you understand what's going on there. You're going to see this syntax a lot in the world of Scala and in the world of Spark in general. So very important you understand that syntax. It's pretty easy to eyeball it, but to get a really intuitive understanding of what's going on, that's important, okay? So let that sink in. And once it has sunk in, I'll give you a little bit of a challenge here. So a very simple exercise here. Every string has a .to uppercase method that you can call on it to just transform the contents of that string to uppercase characters. So play around with some functions. Write a function that actually converts the string to uppercase. And try it out. Actually execute that function on some strings of your own. Make sure it works. And then actually get rid of this separate function entirely and do it in line, just like we did here with function literals. Okay? So I want you to try both doing this with a named separate function that's defined and also with a function literal that you just do in line. So go do that to get some practice with functions. And hey, when you're done, you can say you know functional programming. Congratulations. That's something for the resume. All right, let's move on to our final lecture on our Scala Bootcamp series. All right, we're down to our last lecture in our Scala crash course here. This one's going to be about data structures, and it's a very important lecture. We use these a lot, so don't skip this one if you don't know them already. As before, go to the resources for this lecture and please download the learningscala4.sc file. I'll wait for you. Hit pause while you go take care of that. And when you have that, go on out as before to right-click on the Learning Scala project and say Import File System, browse to wherever you download your stuff, and select the learningscala4.sc file. Open it up, and you should see a little something like this. So let's talk about what's going on in here. Okay, so a really common data structure you see in Scala is called a tuple. And you see this in Python and some other languages as well. Basically, it's a collection of stuff that is treated as its own object. So we can make basically this immutable list is how you can think about a tuple. It's a list of objects that you cannot change once they've been created. Very common in Scala. So how do we declare one? You just put them in parentheses and separate the contents of the list by commas. So for example, we can create a tuple called Captain Stuff that contains the strings Picard, Enterprise D, and NCC 1701D. So maybe this is a tuple that represents information about a Star Trek captain and contains individual fields that have different information about that captain. So it's sort of an easy way to pass around, semi-structured data as its own entity. And if we print that out, we can see that gets converted to the string that is, the same syntax within parentheses, the different contents of that tuple separated by commas. So Captain Stuff itself is a single object, but it contains 3 different values, these 3 different strings here. So that is a good way to sort of stuff different bits of information into one thing, which comes into handy a lot with Spark, as you'll see later on. Now, how do I get stuff out of it? So let's say I want to extract values out of that tuple. Well, the syntax here, again, with Scala is a little bit weird. What you do is you put a dot after the tuple name and then underscore and the number of the field you want to extract. And the thing you have to remember is that it is a 1-based index. So the first value is number 1, the second value is number 2, the third value is number 3. A lot of other things in computer science, you start counting at 0. This is not one of those times. We're starting with 1 here. So for example, if I print captainstuff._1, that extracts the first field of my tuple, which contains the string Picard. ._2 gets the second one, which is Enterprise D. ._3 gets the third element of that tuple, which is NCC 1701D. Okay. With me so far? Nothing too challenging here, but again, you just have to get used to the syntax. Now, a special case is a key value pair, basically a tuple that contains 2 things. And often you'll use this as sort of a key value mapping. So let's say I want to create a tuple that represents a captain and the ship they command. I could use this syntax to do that. That will just create a tuple that maps Picard as the key to the value Enterprise D. And all that does is give me back a tuple that contains Picard Enterprise D. I could have declared it the same way as I did up here, just by having it within parentheses separated by a comma, but this is sometimes a more readable format that sort of implies to the reader of your code that you are in fact associating a value with a key here, and that's your intent of creating that tuple. You would dereference it the same way you would any other tuple. Picard ship._2 would extract the value from that key value pair because it's the second element and give you back Enterprise D. Whereas ._1, let's try it, would give me back the key, which is Picard. Gotta scroll back up to where we were. There we are. Another thing about tuples, they don't have to all be the same type. You can actually mix and match different types of data within a tuple. So here's an example where we have a string, an integer, and a Boolean all jammed into one tuple, and that's a perfectly okay thing to do. Comes in handy sometimes. So that's tuples. Moving on, take a little break if you need to. Let that sink in, review it. We're good? All right. Lists. Lists are a lot like tuples, but it's an actual collection object, so it has more stuff you can do to it. A little bit more heavyweight, but a little bit more flexible. So kind of like a tuple, you can declare a list. That's just a list of comma-separated values here. And under the hood, it's going to build a singly linked list to represent that information. So here we have a ship list value. That is a list of Enterprise, Defiant, Voyager, Deep Space Nine. So 4 different ships from 4 different Star Trek series in this example. And the syntax of dealing with lists is different than a tuple. So for example, if I want to extract a value from that list, I can just use parenthesis and then the field number I want to extract. So now in this case, we're not starting with 1, we're starting with 0. Okay, so you got to remember that. Very easy to make bugs around this stuff. In this case, ship list 1 will go extract the 0-based element of the list at 1. So we go 0 is Enterprise, 1 is Defiant. Ship list 1 gives me back Defiant. Okay? I know, it's confusing, but it's something you just have to remember with Scala. Now, .head will give you the first element of the list. .tail will give you all the remaining elements of the list after the head. Okay, so in other languages, tail might return the last element. That's not how it works here. Tail gives you actually a list, a sublist of the list that just excludes the first element. And sometimes that's useful if you're iterating through a list and you need to extract one item and then, keep working with the remainder of that list in the next iteration. Okay. Now, let's say I want to iterate through an entire list and do something to every value within it. That's something you need to do pretty often. So remember that range operator we introduced back when we talked about flow control? Well, same trick applies to lists. So we can say for ship in ship lists, and that will actually produce a range, an iterator that goes through every ship in the ship list and assigns it to the ship variable. And we can print out each ship one at a time that way. So this code here, again, the key is this little range operator here that will go through the ship list, extract each individual element into a new value called ship that we can then print out within this expression. So that will go through and print out each individual ship in our ship list. More fun with lists here. We can also use the map function to actually transform a list using some expression. So let's take a look at what's going on there. Let's say I have my ship list of ship names, Enterprise, Defiant, Voyager, Deep Space Nine. I can call .map to actually apply an expression, some function, to every element of that list one at a time. So in this case, I'm actually defining a little function inline that takes a string called ship and maps it to ship.reverse, which just reverses the characters in each string. So what that does is say I want to take this function that reverses a string and map that to the ship list and return a new list called backward ships that contains the backwards names of all the ships. Okay, so stare at that line for a little bit until it sinks in, and the output is exactly what we want. So we have a list of all the ships with their names backwards. Okay, so that's what the map function does. It just applies some function that transforms each element of the list into a new list. Okay, and we can go through and print out those results too, just using that same trick with the range operator there to print out the results. And sure enough, we get the backwards versions of each ship name printed out one at a time. Okay, with me so far? Okay, so that's mapping. That's the map function. Mapping, sound familiar? Map reduce, same concept, same exact concept. The only difference is that we're not actually doing this in a distributed manner. We're just using Scala's built-in operators on the list to actually map one list to another. Now, I said map reduce. Can't talk about map without reduce. And sure enough, there's a reduce method on list as well. So just like we can use map to apply a transformation to every individual element of a list, we can use the reduce function to actually combine the contents of a list together. So here we're going to start with a number list. That's just a list of the numbers 1, 2, 3, 4, and 5. I can call reduce on that list with a function that tells how to combine these things together. So basically what reduce does is it goes through each list, and as it gets each pair of items, it will use the function we provide to combine them together. So basically we're saying as new values come in from the list, add them up. So as I get two values that are processed together, I'm going to add them up, take that result, add in the next value, take that result, add in the next value, and so on and so forth until we're done. So basically this is a way of saying I want to take the entire list, sum up all of its values, and give me back the result. And what that does is iterate through the list, one pair of values at a time. So it takes 1 plus 2, says that's 3. 3 plus 3 is 6. 3 plus 4, 6 plus 4 is 10. 10 plus 5 is 15, using that reduce operator, that reduce function we provided, and sure enough, the answer we get back is 15. And we can print out that result. Sure enough, 15. And hey, that's MapReduce. You know, the only difference is that in a real MapReduce application, you would be using functions that actually work on a cluster. Same concept though. Filter also can be used, and you know, if you've looked at Spark and MapReduce before, that might also look familiar. You can actually use that to create a sublist based on some filter function you define. So in this example, we're going to say, I have a new list called I hate fives, and I'm going to take my number list that contains the numbers 1, 2, 3, 4, 5 and apply a filter that tests to make sure that x does not equal 5. So I have in here a little inline function, a function literal if you will, that takes an integer x and tests if x is not equal to 5. And that Boolean result of that function will determine whether or not that individual list element survives and gets passed into the resulting list. So what goes on here, we start with 1, 2, 3, 4, 5. We apply this filter function to it, which will allow everything but the 5 to pass through. And you can see that we end up with a list 1, 2, 3, 4 where 5 has been excluded. We can do the same thing again here. A little bit of a more compact syntax here that you often see. Same idea, but here we're using a little bit of a syntactical shortcut. You can actually say in a function literal underscore to just say whatever it is not equal to 3. So that is sort of implicitly removing this x transform to x and just simplifying it down to, hey, I know I only have one parameter coming in. I want to take that parameter, whatever it is, and just compare it to 3. Okay, and you can see that works just as well. If I apply this filter function that makes sure that each element represented by that underscore is not equal to 3 is all that passes through, then I end up with 1, 2, 4, 5, where the 3 has been omitted. So, you do see this a lot in Scala, where we have these, people that want to save keystrokes at the expense of readability, but you need to understand that when you see it. Okay. Now, Spark, has its own map, reduce, and filter operations that can actually happen in a distributed manner. The only difference is that we'll be not operating on list structures, but something we call RDDs, but we'll get to that later. But same exact concept. So if you understand how this map and reduce function and this filter function worked, hey, you understand MapReduce now, and you also understand a good part about how Spark works. It's all the same idea. It's actually not that complicated. A few more list tricks here. Let's say I want to concatenate 2 lists together. We have our 1, 2, 3, 4, 5 list, number list, and I want to concatenate a new list called more numbers that contains 6, 7, 8. The plus plus operator will combine 2 lists together, and that gives us back the combined list 1, 2, 3, 4, 5, 6, 7, 8. Okay. A few more tricks. Every list has a dot reverse method that will give you the reversed list, so 5, 4, 3, 2, 1. It has a dot sorted method that will return a sorted version of that list. So here I took my reversed list that was 5, 4, 3, 2, 1, called dot sorted on it, and that returns a new sorted list that's back to 1, 2, 3, 4, 5. Let's look at distinct. So let's say I take my number list and append itself, number list plus plus number list, and I get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I just want the distinct values in that list, I can call dot distinct and just get back 1, 2, 3, 4, 5, because those are the numbers that only appear once. Okay. So we also have a dot max function that will find the maximum value in a list. Sum will sum them all up if they are numbers that can be summed. And I also have a dot contains function that can be used as a quick test to see if a list contains a given value. So I hate 3s, where we filtered out the number 3, contains 3, will return false because it has everything but 3. All right, that's lists. I want to take a break here, let it sink in, because we're going to move on to maps now. All right, maps. Maps, just like maps in other languages, sometimes they're called dictionaries. Basically, they're a lookup table of given keys to values. So the way to declare a map in Scala is something like this. So let's say I want to create a map that maps starship captains to the ship they commanded. So here we have a map of Kirk, maps to Enterprise. So we have this dash greater than sign syntax mapping keys to values here. Picard associated with Enterprise D, Cisco Deep Space Nine, Janeway to Voyager. And we can actually do a lookup very simply here by using this parenthesis key name here to extract the value associated with that key. So ship map Janeway returns Voyager. Okay, very easy to use. Now, one complexity is that when you're dealing with maps, you need to deal with missing keys, right? So what if I did like Archer, okay? That wasn't in my list of original captains, in my list of keys for this map. So what happens if I try to extract Archer? Well, that should generate an exception. So one way to protect against that is to make sure that the map actually contains the key you're looking for first. So if I do that test, I can say shipmap.contains Archer. That will return false because shipmap does not have a key for Archer. And at that point I could say, well, I know that key doesn't exist, so I'm not going to try to extract the value for that key because I know that would lead to an error. Another way you can deal with it is by using this try syntax. So, just like try exception blocks or try catch blocks in Java, similar concept there. What we're going to do is use this util.try function that's built into Scala to actually extract the value for Archer from shipmap. And what's going to happen is that's going to generate an exception because there is no key for Archer in shipmap. But instead of erroring out, we're going to wrap it in this util.try so it catches that exception. Get or else says, I want to actually get the value of this expression here, but if it generates an exception, here's my fallback value of unknown. And if I go ahead and execute that, you can see that when I try to do shipmap Archer, that does generate an exception. Get or else handles that exception and returns the string unknown in that case. So that's a safe way of accessing a map where you're not sure if the key is actually in it or not. All right, those are all the main data structures that we need to deal with Scala. There are others, and we'll maybe touch on one or two more of them as we go through the course. Obviously, there's a lot more to Scala than we've talked about here. We haven't even really gotten into object-oriented Scala and some of the more mundane details of the language that might come up from time to time, but as new concepts come up through this course that you might need, I'll introduce them to you as we go. This is all you need to get started. So these are the basics of Scala. If you do want to learn more, there's a good book called Learning Scala by O'Reilly that I recommend. I don't get any money if you buy it or whatnot, but really good reference, and it does go into all those little details that I talked about if you want to learn more. But that's enough to get you started. I think that's enough for now. So let's just start to dive into some actual Spark streaming next, shall we? And congratulations, you now know Scala. Woohoo! So we can't really talk about Spark streaming without talking about Spark. Spark streaming is a component of Spark, so let's talk about the larger system that it sits within, because that's important to understand first. So what is Spark? If you're new to this technology, what's the big deal? Well, it bills itself as a fast and general engine for large-scale data processing. So basically, it's a way to take massive data sets, big data if you will, and distribute their processing across a cluster of computers. And unlike MapReduce, it's a lot easier to use Spark. You can actually write very simple driver scripts to actually control how these big data sets are transformed and output into different systems. And you can see here that the logic of your Spark script lives in your driver program. And basically, wherever you have your master node of your cluster, or maybe on your desktop if you're just developing locally for now, you might have a little script that describes how to input the data that you have, how to transform it, how to process it, how to output it, whatever you need to do. And that all lives within your driver program on the master node. And your driver program is responsible for creating a Spark context object. And this is basically the object that creates all the different components that you need to manipulate your data. Now this Spark context and your driver will communicate with your cluster manager if you're using a cluster, and that can be built on top of Spark or Hadoop Yarn or Mesos. So even though a lot of people talk about Spark as sort of being the next big thing, the replacement for Hadoop, what they really mean is that it's a replacement for MapReduce and not Hadoop as a whole, because you can actually run Spark on top of Hadoop's cluster manager, which is called Yarn. So they're not mutually exclusive things. You can take advantage of the scalability and robustness of a Hadoop cluster and run Spark on top of it. But you're not required to. Spark also has its own cluster manager built in, and you can also use new technologies like Mesos, which is actually a very popular choice these days too. And that cluster manager is responsible for orchestrating the processing of your data across the entire cluster. So you can have many, many different worker nodes that are running their own executors, and each executor process, and there could potentially be multiple executors in each machine even, is given a budget of some memory that it can use, and it has a cache that it can use, and it's given a specific subset of your data to process or specific tasks to process as your data is being manipulated. And the beauty of this architecture is that it's what we call horizontally scalable. So you can actually add more and more servers to the problem and process more and more data as a result. You're never really bound by the memory of a single machine. If you have more data than you have memory to process, you can just throw more hardware at it. And given that computing resources on clusters are pretty cheap these days using commodity hardware, it's a very attractive approach. So that is Spark architecture at a very high level. What's the big deal about Spark? Well, it's really fast. And compared to MapReduce, it can be up to 100 times faster. Of course, that's a best case scenario. Your mileage will definitely vary, but it is consistently faster than MapReduce in my experience. And that's if it's running in memory. If you're running off of disk, it's up to 10x faster. And the reason it's so fast is because it uses what's called a directed acyclic graph. So instead of like in MapReduce where you're sort of explicitly chaining steps together, Spark actually, the way it works is you define sort of the flow of how you want to process your data programmatically. And nothing actually happens until you tell Spark to go and do it. And at that moment, Spark goes off and says, okay, what's the optimal way to approach this problem as a whole? And it will optimize the workflow of processing that data to be the best that it can be. Okay, so it's a lot more adaptable to the holistic nature of what you're trying to do with your data processing. And that's how it gets its speed. It's a very highly optimized system because it's basically a lazy evaluation system. It waits to see what you're trying to do as a whole and then arrives at the optimal way to achieve your end result. Very hot technology, just a partial list of some of the companies that have publicly said that they are using Spark. I'm sure there are many more who keep it a secret. And if you want to see even more, you can visit this website here to see the latest and greatest list of big names that you've heard of that are using Spark for real problems today in the real world. And these are also all big employers, I might add. So, there's some real value to understanding Apache Spark. And the beautiful thing is that it's actually not that hard. We just got through learning a whole new programming language with Scala, but the truth is the bits of Scala that you need to do Spark programming are pretty straightforward. And if you took my previous course on Spark, you'll see that in Python it's pretty simple, and it looks a lot the same in Scala. Basically, it's all built around one main object called the resilient distributed data set, and this embodies sort of a collection of data, basically key value data that you can transform and perform actions on. And the various methods on RDDs, we call them, make up the bulk of your Spark code. So you're not really going to get too involved in the minutia of programming languages here. Mostly what you're going to be doing is creating RDD objects and transforming those RDDs in different ways. So it's actually fairly straightforward. Now, as you can see, Spark Streaming, which is what this course is about, is just one of many components of Spark. Everything's built on top of Spark Core, which contains all the guts of actually creating and transforming and performing actions on these RDDs that we mentioned. And on top of that, we have different technologies, such as Spark Streaming, which basically lets us deal with real-time constant streams of data that just come in forever, that we can transform as it comes in. That's built on top of Spark Core. So all the functionality of Spark Core is available to Spark Streaming. Spark Streaming is just sort of the extension that lets us process data in real time as it comes in. Spark SQL allows us to create SQL views of our data out of an RDD, so you can actually run SQL queries on data in Spark, which is kind of a cool thing if you're familiar with SQL. MLlib, that stands for machine learning, so there's actually a small collection of different machine learning algorithms you can also apply on Spark, and some of those are even possible to use with Spark Streaming, and we'll talk about that later in the course. Finally, GraphX is another component of Spark, and again, that can interoperate with Spark Streaming in some cases as well, too. And GraphX isn't about, drawing graphs and charts and, lines and stuff like that. It's actually talking about graph theory, so things like social networks, where you have these complicated networks of connections between people or things or sensors or objects or what have you. We're talking about that kind of a graph in the computer science data structure sense, okay? And that contains some utilities that are useful for analyzing those sorts of graphs. So very powerful toolkit, and it's getting more and more powerful all the time. Spark is very actively developed still, and we're seeing more and more capabilities added with every release. And up next, we'll talk about resilient distributed data sets in more depth, so let's continue on to the next lecture. Let's talk about the core piece of Spark called the Resilient Distributed Data Set, or the RDD for short. This is kind of the fundamental building block of all Spark and Spark Streaming programs. So RDD stands for Resilient Distributed Data Set. Resilient, meaning that it can be distributed and run on a cluster that is actually resilient to failure. So if you're running on a good cluster manager and one of your nodes goes down for some reason, then your RDDs can still survive. There's probably a backup of their data on some other machine that it can be recovered from. Now, we'll talk about fault tolerance in more detail later on. It's by no means a guarantee that your cluster won't fail or your Spark job won't fail, but it can deal with some pretty nasty stuff. Distributed, you can actually distribute the processing of an RDD. An RDD is basically a giant, key value data store, if you will, and it can actually distribute the storage of this massive data set that it represents across many machines, across a distributed file system, what have you. So in this way, RDDs can represent a massive data set that could never fit on one machine, and yet we can still logically refer to it as a single object when we're programming. So that makes life a lot simpler. And it is a data set, obviously. It's the whole point of an RDD. It just encompasses a big body of big data that we want to do some operation on at a very large scale. And we're doing it in a resilient and distributed manner. It'll make more sense when we look at an example. So when we start with any Spark program, we're going to start by creating a Spark context. And the Spark context object is what creates our RDD objects. It's sort of the mastermind behind the whole script. And in Spark Streaming, we create a variant of Spark context called a streaming context. So this is just a special Spark context object that can actually deal with real-time data. And if you look at an example piece of code here that actually creates a streaming context, you can see in Scala, we just create a SSC, or whatever you want to call it, val. That creates a streaming context object. And the parameters might just be something like the master node. So normally this would be where you're running the script on. Local bracket star bracket means that I'm going to run this script just on my own PC, on my own local host. And the star indicates that I'm going to actually spin up a process for every core that I have available on my PC. So this streaming context means I'm actually going to spin up 4 different workers on my own little PC because I have a 4-core CPU. And the name of this context is going to be log alarmer. That's just something that shows up when we look at debugging tools. And the final argument here is the batch size. So this tells Spark Streaming that I want to process data 1 second at a time. It's going to take in 1 second worth of data from whatever stream source it has. We're going to process 1 second's worth of information, pull in the next 1 second of information, process that, and so on and so forth, on and on forever until this thing stops. And that's just how you set up the beginning of a Spark Streaming job. Now, in order to actually do something with that information, we need to create RDDs, or objects that are derived from RDDs, as we'll see later on. And there are many ways to do that. So in addition from creating it from a stream, we can also create RDDs from just some data that's in memory. So we can call parallelize to transform this list of numbers into an RDD, for example. But that's not very practical, is it? I mean, if you can actually fit all of your information on memory on one machine, what's the point of using Spark? It's not really big data. So that's really only useful for, small-scale experiments or learning. You can also import data from a text file, and that doesn't have to be on your local system like in this example. You can also load data from a distributed file system, which is more likely in the real world. So an HDFS file system, maybe Amazon's S3, whatever you got. If you have a Hive database, you can also use that. You can actually create an RDD based on a SQL query on a Hive database and store that in an RDD that you can then manipulate within Spark. And you can also connect it to lots of other systems, and we'll see some examples of this later on too in more detail. If you have a JDBC style database, you can connect to that, extract data from it, create an RDD from it. Cassandra database, HBase, Elasticsearch, data that's in JSON format or CSV format. There are libraries that let you import all these into RDDs very easily. So whatever storage mechanism your big data is in, odds are there's a way to get it with Spark. And if there isn't, you can always write your own custom code to import it. So once I have an RDD that represents some big data set, what do I do with it? Well, there's 2 things you can do. You can transform that data and you can perform actions on it. So here are some transformations you can do with RDDs. And some of these should look familiar from our Scala crash course because some of them are actually similar to the operations you can do on a list in Scala. And that's not an accident. I mean, there's a reason they chose Scala for Spark. It's just a very natural fit. One thing you can do is a map operation. So if you call map on an RDD, that lets you apply some function to every element in that data set. So let's say I have an RDD that's, lines of text from a log file. Maybe I could have a map function that transforms those raw lines of text into tuples of more structured information. Okay? Flat map is similar to map, but instead of a one-to-one relationship where every line of input in the RDD is transformed into a line of output into a new RDD, flat map can actually generate nothing or more than one result from a given line of input from one RDD. So using flat map, I can actually take an RDD that contains X number of lines of information and create a new RDD that has Y number of lines of information. They don't have to be the same. Filter, just like it is in Scala, allows you to apply a filter function to an RDD and only extract information that you want to keep. So if there's a bunch of information in there from Googlebot or something, you can use filter to filter all that out and create a smaller, more manageable RDD that will perform better. And the usual stuff, distinct, lets you just sample distinct rows that are in that RDD. Sample lets you take a random sample if you just want to do some experimentation. And there's also some set theory stuff here, union, intersection, subtract, and Cartesian products of RDDs that you can do. A little bit less common to see those, but good to know they're there if you need them. So let's look at an example of using map in Scala. So let's say that I actually create a RDD called input, just using Spark Context's parallelize method to parallelize this list in memory of 1, 2, 3, 4. So that will convert my list of 1, 2, 3, 4 into an RDD called input, a very small RDD, not a terribly good use of Spark. And then it will actually apply this map function to the RDD. So just like I could call map on a list, I can also call map on an RDD. And we're going to pass in, remember, our little functions here, function literals. We're going to take the X that represents the input data from the input RDD and transform that to X times X. So basically we're going to take every value in the input RDD, 1, 2, 3, 4, and square it, and put the result in a new RDD called result. So the resulting RDD, called result, will contain 1, 4, 9, 16, which are the squared values of 1, 2, 3, 4. So, that's really the main concept of Spark and Spark streaming, just this whole idea of taking RDDs and transforming them and performing actions on them. I mean, that's really all it comes down to. There are also actions you can perform on RDDs when you actually want to produce some sort of output. So, for example, collect will actually take a snapshot of your RDD and dump it to a conventional data structure that you can manipulate within your driver script. So that's a good way of taking your final results if they've been reduced down to something that you can actually manage on one computer and doing some further output on them. Some other things you can do is call count to just see how many rows are in your RDD. Count by value will break down a count by unique values that are in your RDD if you have key value data in there. Take will just take the top few results. Reduce is a more common action that you'll see that allows you to combine together the elements of an RDD based on their keys. So, for example, let's say I want to count up, we'll actually look at an example like this, a more concrete example, but if you had a corpus of lines of text from a book and we wanted to count up how many times each word appears, we might have an RDD where each word is an element in the RDD followed by the value 1. And if I say reduce in a way that I combine and add these all up together, what I can end up with is an RDD that contains each unique key, each unique word, followed by the sum of how many times that word occurred. I could do the same thing with count by value, but reduce gives you a little bit more flexibility on how you combine these things, okay? So reduce lets you combine together all the information combined with different instances of a key into a final result, okay? So just like in MapReduce, we have a map operation in the transform stage. The reduce operation is here in the action stage. And it's important to know that nothing actually happens in Spark until you call an action on your RDD. Remember, we talked about how Spark creates a directed acyclic graph to actually figure out the optimal strategy for processing your driver script. Well, it's when you call an action that Spark says, okay, I actually have to generate an output here at this point. So I'm going to go back through the entire chain of different transformations that I performed on this RDD in the script and figure out the best strategy for getting through the whole thing, okay? So that takes some getting used to, because when you're writing code in a Spark script, it's very easy to think that it's all running sequentially, but it's really not. What you're really doing is defining a chain of transformations on your data, and it's not until you actually specify an action to be performed on that final result that anything actually kicks off and actually happens. So that can be very confusing. If you're trying to debug something, you might say, why isn't anything happening at this point in the code? It's because Spark doesn't do anything until you tell it what the end result is. Okay. Now, this might be a little bit confusing right now, especially the part about reduce, but let's take a look at a concrete example here. And I think when we look at some code, it'll make a lot more sense. So in the next lecture, let's just dive in and actually look at that word count example that I talked about and actually run it. All right, let's see some Spark RDDs in action. Actually run some code on them. Yeah. So for the resources on this lecture, I want you to download two things. One is the wordcount.scala file, which is our actual source code for this exercise, and book.txt, and that just contains the raw text of a book I wrote. So I own the rights to it, so I can play around with it as much as I want. A little bonus for you there. And once you have those both into wherever you download your stuff, we can continue. All right, so the first thing we want to do is get that book.txt file where it belongs. So go ahead and highlight that and copy it. Just hit Control-C there. And you want to go into the folder where you created for your actual course, for your environment for Eclipse. It should look a little bit something like this at this point. And go into Spark Streaming Examples, and we're going to paste the book.txt file there, okay? So this has to be within the project folder that we're going to be working within. Okay, now let's go ahead and open up Eclipse, the Scala IDE. And then we're going to import that script in, and we'll take a look at what it does. So just right-click, open up Spark Streaming Examples, and open up Source, and open up the package com.sunducksoftware.sparkstreaming. And we're going to import that new word count file by right-clicking on that package and saying Import, File System, and go to where you downloaded the file, For me, that was C downloads. And select wordCount.scala and hit finish. And we should be able to double click that now and take a look. All right. Here we have a very simple Spark script that just loads up all the data in that book and counts up how many times each word occurs. So let's walk through this and see what's going on here. So we start off just by declaring the package we're in like we would in any Scala application, and we also import in the entire contents of the Spark library so we have them at our disposals. Okay. Now, good practice here is to use Java doc format for your comments here, so you can actually get nice little inline comments on your classes and functions and whatnot. So I did that here. We created an object called wordCount within Scala, and we created a main function within it. So this is basically how Spark knows where to start running from. It needs to be within a Scala object that has a main function, and then when we actually invoke the script, we tell it what class to look for that main function in. So this is just sort of boilerplate stuff. You're always going to have an object followed by the name of whatever your project is, and then a main function that looks like that, followed by the actual contents of your Spark job itself. Okay, so what is this Spark code actually doing? Here's the actual meat of what we're going to be doing here. We're going to start off by creating a Spark conf object, and this is how we actually set up the configuration options for our Spark context. You can also do it inline in the Spark context constructor here if you want to. There's more than one way to do it. Specifically, we're going to set up a new Spark conf here with an app name of wordCount, and that's just important for seeing it in our dashboards and whatnot. We're going to tell it that the master is local ***, and that just says we're going to be running locally on our own PC because we don't have a cluster yet. And the star means it's going to run on every available core of my PC. And next, we'll create a Spark context object for using that configuration. And remember, the Spark context is sort of the granddaddy of our Spark driver program. It's what creates our RDDs for us and ties it all together. So the first thing we're going to do with that Spark context is create an RDD by using sc.text file with the path to my book.txt file. So that's going to transform every line in that text file into an entry in my RDD. So the input RDD will now contain one row of information for every line in my book. Okay. Now, next thing we're going to do is do a transform on that RDD. So we're going to use flatmap to actually split each line of text into individual words. So line.split, that's a Scala function that will split a string into individual words. And then we're going to take that resulting list of words and create a new RDD called words. Now remember, map does a one-to-one transform of an RDD, but flatmap can create multiple results from one RDD line. So by using flatmap, we can generate many new entries, one for each word, from a single line of the input RDD. So at this point, what we have is a words RDD, where every row contains a word, and that's it. Next thing we need to do is normalize our data. So lowercase words is just applying a map function to transform that words RDD such that every word is transformed to lowercase. And that way we don't end up with individual results for different capitalizations of different words. And finally, we're going to actually execute an action on this RDD, and this is what tells Spark, hey, it's time to actually go do something and kick something off. So lowercase words count by value will actually count up every individual unique word in the lowercase words RDD and report back how many times each word occurs. So what we're going to get back here is a new RDD word counts, where every row of the word counts RDD contains a tuple of a word and the number of times it occurred. Okay. When we're done, I'm just going to sample the top 20 results from the list. They're not necessarily sorted or anything. I'm just taking the top 20 to look at what's in there. And that take function actually says, okay, give me back of my final results. And I'm going to just use this little for loop to actually iterate through the entire resulting data set. Remember, that's that little operator to have a range operator there. And what I'm going to get back from every row in my sample is a tuple of word and count. And then I can print out the final results and stop my context when I'm done. Make sense? If it doesn't, hit pause. Go stare at this code a little bit more. Look at my comments here. And, it's a pretty straightforward example, so it should make sense in your mind pretty quickly. Let's go ahead and run it, see what happens. So to do that, we need to go to run and create a run configuration for this. So we can double click on where it says Scala application and create a new configuration. We're going to call this word count. And we just have to tell it what the main class is that we're going to run from. So in this example, it will be com.sundogsoftware.sparkstreaming.wordCount. And that is the fully qualified class name of our main class, of the class that contains our main function. And we can just hit run and see what happens. So there we go. Spark's spinning up, and hey, it's already done. So if you scroll up here, you can see the results of the first 20 rows that we got out of the final results. Looks like the word foolproof only occurred one time in the whole book. Same thing with precious, but the word hourly occurred 3 times, appropriate twice, rate 7 times, and so on and so forth. So hey, it actually works. It's pretty cool. Your first Spark program. It's not using Spark streaming yet. You know, that's up next, but this is how a good example of using RDDs and actually using Spark. And if you were actually running this on a cluster, you could actually throw some massive text database at it that was on a distributed file system, and it would work exactly the same way. So pretty cool stuff. All right, so that's a Spark RDDs in action. Again, we started with an RDD of just every line of text in our book. We created a new RDD of every word in the book. We created a new RDD from that with all the words converted to lowercase. And finally, we reduced that down to get the counts by every unique word in the book and printed out the results. Okay? That's all there is to it. So, not too bad, right? Actually, it doesn't get much more complicated than this, honestly. So, take the time to understand what's going on here and you'll be in good shape for the rest of the course. So we talked about Scala, we talked about Spark, we finally have all the fundamentals we need to talk about Spark streaming itself. Finally, huh? Finally getting there. All right, so what's the big deal about Spark streaming? Why is it important? Well, big data never stops, right? I mean, if you just use Spark by itself, it's great for processing massive data sets in one fell swoop. You know, maybe you have a big corpus of data and you just need a one-time answer out of it for some reason. Or maybe, you know, running this job once a day is sufficient for whatever you're trying to accomplish. Maybe you're just generating some daily report. It's fine, you know, just use Spark for that. But what if you want to update your results in real time? What if instead of processing this giant data set periodically, you just process the new bits that come in as they come, and you just keep updating your results over time, basically forever? Wouldn't that be kind of cool? Well, that's what Spark streaming does. So instead of huge batch jobs, you can analyze your data as it comes in, one little section at a time, and keep aggregating those results as you go. So what are some examples of using that? Well, let's say you have clickstream data coming in from a fleet of web servers. You know, maybe you're running some massive website out there, and you actually can use Spark streaming to connect to an input stream of web logs coming in from this entire fleet of web servers. You know, parse that data out in real time using Spark streaming and transform that data however you want. You know, maybe keep track of sessions, keep track of how much people are buying, whatever it is. And you can do that all in real time with Spark streaming. Another hot application of Spark streaming is the whole Internet of Things thing that's going on that venture capitalists are so excited about these days. But imagine you have streams of data coming from lots and lots of sensors, right? As part of some sort of Internet of Things application. You could use Spark streaming to aggregate all that sensor information into one place and do that at a very large scale in a very reliable manner. So Spark streaming is also an enabling technology for the vision of the Internet of Things, if that comes to pass. At a high level, this is how it looks. So basically we have data streams coming in from some source. Like I said, it could be sensors, it could be web logs, it could be something else entirely, just something feeding us data. And we have a receiver on Spark streaming that listens for that data and ingests it into Spark streaming somehow. So we'll see that there's a lot of different kinds of receivers we can set up for different kinds of data. And at that point, it breaks that data up, that data stream up into a bunch of itty-bitty little RDDs that maybe contain 1 second's worth of data or whatever we configure it to. And these just keep getting generated and generated over and over and over again, and we just keep transforming them and processing them over and over and over again. And the output of that transformation can get sent off to wherever we want. Maybe we're updating some external database with some information that we're aggregating, or some subset of the data that we consumed. Whatever you want to do, this is kind of how it looks. You have like a big stream of information coming from potentially multiple sources at once. We have a receiver that listens to those data sources, and logically it transforms it into RDDs like we saw with our word count example that we can operate on just like Spark does normally. And we can transform those, reduce them, whatever we want to do, and send the output wherever we want, also in a distributed manner. So the real power of this is that the processing of all those RDDs, remember we broke it up into little chunks, we have, different bits of it going on in different places, we can actually distribute that amongst a cluster. So even if you have a massive influx of data coming in from a massive web fleet or a massive fleet of sensors, it's fine. We can actually horizontally distribute this problem and process those little smaller RDDs from our stream across an entire cluster of computers if need be. Now, another important abstraction in Spark streaming is what we call the D stream, and that stands for discretized streams. Okay? So basically, the logical stream of information that just goes on and on forever is called a D stream in Spark streaming. And that stream is broken up into these discrete RDDs of a given batch size. So you can think of a D stream as being the entire stream of data coming in from your receivers, and that D stream in turn is comprised of a lot of little, much smaller RDDs that contain the actual information. And this is a very useful abstraction in Spark streaming because we can apply transforms and actions to the D stream as a whole instead of individual RDDs in many cases. So even though we can still access individual RDDs from within a D stream, often we can just apply an operation to the D stream itself and describe the chain of transformations and actions that we want to apply to our data entirely in terms of the D stream. So you can see the power of that. By just writing some very simple scripting code on the D stream, you can actually flow that data, that logic down to these individual RDDs that could be getting executed and evaluated any place on a cluster. So all that complexity of breaking that D stream into little manageable chunks over time that might be distributed, it's all hidden from you. You don't have to worry about that with Spark streaming. It's a beautiful thing. So what are some things you can do with D streams? Well, a lot of stuff you can do with RDDs. You can apply map functions to them that can transform the information in them however you want. You can flat map them, so bust them out into even more or fewer elements if you want. You can filter them, and you can do reductions on them, reduce by key. So all the important things that you might do in an RDD, you can also apply to a D stream as a whole. Another thing you can do, and we'll get into this in more detail later in the course, is keep track of stateful data. So as D streams flow through the system, you can actually keep track of state that's keyed by some value. So a good example would be session data in a clickstream. So I could actually break down activity by IP address or some session identifier and actually keep track of the clickstream by session ID over time. And that could be stateful information that actually persists across the individual RDDs of my D stream. You can use that to keep running totals of things too and things like that. So if you want to do more than just transform an input stream of data and sort of extract the bits you want and put it somewhere else, you can also use stateful data to actually keep track of running totals or stateful data over time as well. So there's a lot you can do with Spark streaming. It's a very flexible system. So let's go back and look at that Twitter example that we ran really early on in the course and go into a little more detail about what it's actually doing now that we understand the concepts a little bit better. So now that we understand some of the concepts of Spark streaming a little bit better, let's take another look at that print tweets example. Remember back in lecture 2, we ran a little simple example that actually connected to Twitter and received live tweets and just printed them out as we went as our first Spark streaming application. So let's take a closer look at that code and understand better what's really going on here. So again, we're just starting by declaring our package name, and we import everything from Spark, including some specific things for Twitter processing and for log processing. We're also importing our utilities class that we included here that we haven't talked about a whole lot yet, but we will shortly. So we're going to use a object called print tweets in Scala, and there we define our main function. Again, this is just sort of the simple basic pattern you will follow for all Spark applications in Scala. I don't want to get into the minutia of object-oriented Spark just yet, so just take that on faith for now. First thing we do is call something for our utilities class called setupTwitter, and this isn't magic. This actually goes into our utilities class that we defined and actually reads through that twitter.txt file we created with all of your credentials for connecting to Twitter and sets a bunch of system properties that Spark streaming can use to actually connect to Twitter. Going back to printtweets.scala, first thing we do is create a streaming context. Remember, that's kind of the basic fundamental object that we build off of in Spark. So we're creating a new streaming context that is running locally on all cores. We're naming it print tweets, and we're telling it to actually run a batch every 1 second. So remember, our D streams are made up of little itty-bitty RDDs that keep flowing in. We're telling it that we want to create a new RDD every 1 second. And it might actually be multiple RDDs every second. You know, it's kind of up to Spark how it actually distributes this stuff. But fundamentally, we're going to model our stream of data as chunks of 1 second information. It'll be updated every 1 second. So every 1 second, what we're doing to our D stream will happen, okay? Whatever sequence of events we set up for transforming and acting upon our D stream, that is going to occur every second with a 1 second batch interval. Next thing we do is call another utilities function. All this does is set the log level forcibly. That way we don't see a bunch of log spam when we're running the actual job here. You know, until we get to the point where it actually creates a Spark context, we'll see a bunch of info messages and warning messages. Those are all completely harmless. Don't worry about them. But once we're actually generating output, I don't want that stuff cluttering up the output. And that just makes sure that only error messages get through from this point on. Now, here's where the magic happens. We call Twitter utils, which is part of the examples included with Spark itself. And we're creating a stream, a D stream, if you will, using our streaming context. Okay? So if you look at the type of tweets, you'll see it's actually a receiver input D stream. This is a D stream. Kind of like we talked about, the abstraction of all that little stream of chunks of little RDDs of tweet data coming in. Okay, so that's sort of where we start with. This is receiving raw information from Twitter in a D stream. Next thing we do is we apply this mapping function to it. So again, we have like a function literal here where we're taking each status object from within that tweet stream. It turns out that Twitter utils creates a RDD, a D stream of status objects, and you have to actually call getText to get the actual text of the tweet from that status object. And it contains a bunch of other stuff like who the tweet's from, where it's from, time, all that stuff, right? But for our example, we just want to extract the text of the tweet itself. So we take our large tweets D stream and we convert it to a new D stream that only contains the tweet text themselves. Very important to kind of extract the data you care about in Spark jobs because you want to throw away all that extra data. It'll make your job run a lot more efficiently if you can discard information early on. And then all we do is we call print, and print actually doesn't print the entire RDD, it just prints the first 10 results that it finds. Kind of a strange behavior, but that's what print does. If you wanted to actually get the whole thing, you could, call collect on it and go through all the RDDs to actually get that information. But for this simple example, we're just calling print on the D stream itself to print the first 10 results that are in it. So let's go ahead and run that again. If we go to run configurations, we can select print tweets again and run that. And let's see what people are talking about today. NBA Finals, apparently. I'm not a sports guy. I didn't even know it was NBA Finals. All right. Oh, I saw some dirty words there. People are nasty. Anyway, like I said, I can't control what people are saying here, but there it is. Live tweets running again. Pretty cool stuff. Spark streaming in action. So we're going to work our way through some more and more complex examples next. But first, I want to cover a couple of more conceptual things with Spark streaming. So let's talk about windowing next. When you want to stop this, hit terminate, and then you can get your computer back. Another important concept in Spark streaming is called windowing. And this lets us actually look back over a larger period of time than our batch interval. So we might want to have data coming in very frequently from our stream of input, just to make things a little bit more fault tolerant and more efficient. But maybe I don't actually want to aggregate data just on those small windows of information in my underlying RDDs. So windowing allows you to actually look back and aggregate data over a larger period of time. So one example might be, let's say I have a stream of purchase information coming in from some big e-commerce website. What I could do is I could still have that data streaming in every 1 second. So my D stream would be contained of RDDs that are generated every 1 second. But if I want to look back every hour and aggregate data over the past hour, I could have a window time, a window interval of 1 hour. So we'll actually keep around information for the past hour and allow me to aggregate that whenever I want to. And I can actually update that information at a different rate as well. Okay? So in our little example here, we have a sliding window of 1 hour that moves over time as time goes on, and that will sample a different set of RDDs, which might be coming in more frequently. And that's okay. Windowing allows us to aggregate those RDDs over a larger time period into a single result that looks back over a given window of time. So there's three different intervals that we talk about with windowing: the batch interval, the slide interval, and the window interval. Now the batch interval is what we saw from the beginning. Basically, as a D stream is constructed, every batch interval we construct an RDD of that information that came within the past batch. And usually that's a very small time period, like a half a second or 1 second or something. So that if something goes horribly wrong, at most we lost a second's worth of data, right? And that also minimizes the processing load on things. But often the time that you use for that batch time doesn't correlate with what you actually want to analyze over. So the batch interval is just meant in terms of, quickly sucking in all the data from whatever systems you're listening to. Now the slide interval is how often you want to actually compute a result. So let's say, going back to the top sellers from the past hour example, maybe I only care about updating that information once a minute. So I might have a batch interval of 1 second where every second I'm ingesting new data into Spark Streaming, but maybe my slide interval is only 1 minute. And then every 1 minute I'm actually computing a result based on that information. Finally, the window interval is how far back I look back every time I hit the slide interval. So maybe every 1 minute I look back for a window interval of 60 minutes to actually compute and aggregate the top sellers for the past hour. Okay? Let's say that again. Makes a little bit more sense in a graphical example. So let's take a look at another example here and look at it graphically. So let's say that we have a batch interval of 1 second. So every 1 second, a new batch of data gets transformed into an RDD in our D stream. Okay? Now, if we have a slide interval of 2 seconds, that means that every 2 seconds, I'm going to try to compute some result. And my window interval is 3 seconds. So I'm going to, every 2 seconds, look back for 3 seconds worth of data and use that 3 seconds worth of data to compute some result over the past 3 seconds. So 2 seconds go by, I hit my slide interval of 2 seconds. I'm going to look back for up to 3 seconds worth of data. In this case, I only have 2 to work with, but that's okay. Another 2 seconds go by on my slide interval, time to compute a new result. My window interval is 3 seconds, so I look for the past 3 1-second batches, and those all go into my result. Another slide interval of 2 seconds goes by. I look back on my window interval of 3 seconds, which includes 3 batches of 1 second. Okay, makes sense. It's a lot of terminology to juggle around, but the actual concept isn't that difficult. Just stare at this diagram for a bit longer if you need to before moving on. How does that translate into actual code? Well, the batch interval, like we saw before, is just set up as part of your streaming context. So when you set up your streaming context, you specify the batch interval right there. You say that I want my D stream to be comprised of 1 second chunks of RDDs. And then, when I actually want to create a result, I can use the reduce by window or reduce by key and window function to aggregate data over a given window interval. Okay, and when I do that, that's when I specify not only my reduce function, in this case I'm providing both a additive and subtractive function here to make things more efficient, but I'm also specifying my window interval and my slide interval as well. Okay, so that's all it takes to implement windowing in Spark Streaming. We'll look at some concrete examples later on in the course that are actually running, but for now, just get this concept in your head. It's actually possible to aggregate data using reduce operations in Spark Streaming using a window of time that goes back further than a given RDD. Okay? So one more thing to talk about on a conceptual level about Spark Streaming is fault tolerance. How is it so resilient? After all, you would think this would be a pretty fragile setup. You're setting up this system that basically runs forever on massive amounts of data just flooding into it. You would think that would just break left and right, wouldn't you? But in fact, it can be quite reliable if you make the right choices. So how does that work? Well, by default, for one thing, all incoming data actually gets replicated to 2 different worker nodes in Spark Streaming. So even if one of your computers goes down in your cluster, it can still recover that information from a backup copy that it had on some other node. So, even if you lose nodes on your cluster, you can still keep on running while you work on replacing that node, and things will just work just fine usually. Another thing you can do is use a checkpoint directory that Spark can use to actually restart if it has to. And you're actually required to do this if you have any sort of stateful data in your driver script. So if you're keeping track of windowed operations or some sort of stateful data as your stream gets processed, you can actually specify a checkpoint directory, ideally on some distributed file system like HDFS, which itself is reliable. And then in the event of complete failure, you can actually restart your Spark Streaming job, and it can pick up right where it left off based on what it stored in that checkpoint directory. Now to do that, you just use the checkpoint function on your Spark Streaming context object, and specify a path to some distributed file store. When we're doing this in our little examples here, that will just be in our local file system, but remember, in the real world, you'll want to use HDFS, S3, something that's distributed. But there are some limits to this still. So what happens if your receiver fails? What happens if your driver script fails? You would think that if a receiver fails, maybe I'll lose data. And yeah, sometimes you can. It depends on what kind of receiver you have. What if your driver script fails? Isn't your driver running on your master node a single point of failure? Well, it doesn't have to be. So let's talk about receiver failure first. So some receivers are better than others. Basically, if you have a receiver that's just getting data pushed to it all the time, yeah, if your receiver goes down, you're going to miss any data that came in while you weren't listening to it. So a good example is our Twitter receiver that's just listening to tweets being broadcast by Twitter all the time. If my receiver goes down, all those tweets just go to the ether because I can't actually go back and say, Twitter, please go give me back all the information I missed before. There are also some configurations of some popular technologies called Kafka and Flume that we'll talk about in more detail later on that can stream information into Spark Streaming. And again, if you configure these to just push data into Spark Streaming, then yeah, if your receiver goes down, you're going to lose all that information. But some receivers can actually request to pull data from their data source. So in that case, you can actually configure the receiver to say, okay, I know I went down at this time. When I've been restarted, I can actually go back and request this data historically that I missed when I came back up. So for example, if I have a data stream coming in from an HDFS file system, the Hadoop distributed file system, that data is still going to be there. HDFS is reliable, and it's going to keep stuff around for a while, so I can still go back and retrieve that data even if my receiver goes down and comes back up again later. Same thing with directly consumed Kafka, which is what we'll show in this course later on, or pull-based Flume. In those cases, I can actually go out to Kafka or Flume and say, hey, please pick up from this point in time and get me caught up on anything that I missed. So your choice of receiver technology makes a big difference into the fault tolerance of your Spark streaming job. Another problem is driver script failure. So your driver script runs on your master node and kind of coordinates everything on your cluster, but it can be a single point of failure if you don't do things properly. Now, we talked about using checkpoint directories briefly before, and that's kind of the secret to getting resilience on your actual driver script. So if you're actually dumping state to a checkpoint directory, here's the trick you can do. Instead of just creating a new streaming context object every time your script starts, you can instead call streaming context get or create. And what this takes is a checkpoint directory as well as a function that will create a new streaming context. And what it does is it first checks your checkpoint directory to see if something was left over there from a previous driver run that terminated unexpectedly. And if so, it can just pick up from where it left off, which is kind of awesome. And if there's nothing found in that checkpoint directory, then we assume that the previous job completed normally, and it will just create a new streaming context and start up from scratch. So that way, if you need to restart your driver script, it can still pick up from where it left off using that checkpoint directory, which again should be stored on an external distributed file system. So if your driver script master node goes down, your checkpoint directory should be somewhere else where it can still be accessed by the driver script when it comes back up, potentially on a different computer. Now, something still needs to monitor your driver script so that you don't want to be woken up at night when your driver script fails and you have to go restart it somewhere. Ideally, you would be using a technology like Zookeeper, that's part of the Hadoop ecosystem, to constantly monitor your driver script on the Spark master node and automatically restart it for you if need be if something goes wrong. And then it can all just be automatic. You no longer have a single point of failure in your driver script because it's backed up all of its state to a distributed file system, and Zookeeper can be there watching over it and restarting it based on that checkpoint directory whenever it has to. And you can also use Spark's built-in cluster manager to do something similar. It has a supervise option that you can specify when you run it, when you run your job with a Spark submit function that we'll look at later, and it can automatically monitor Spark's driver script for you using that option as well. So between all these things, if you're careful about your choice of receiver technology, you're careful about how you monitor your driver script, and you're careful about where you're storing your checkpoint data, you can have a very fault-tolerant system with Spark streaming, surprisingly so. So don't be afraid. It can actually work in production. In this next section, we're going to get our hands really dirty. I got a lot of little simple examples that will gradually teach you new concepts in Spark streaming and get you some hands-on practice in actually using Spark streaming. So our first example is going to be an extension of that print tweets example that we started with, it's actually going to save tweets to disk instead of just printing them out to the screen. And some stuff we'll learn in this lecture. We're going to learn how to save streams to persistent storage, and in this example it'll just be to our local file system, but the same concept applies to dumping out data to a database or a distributed file system or whatever you have for an output target. We're also going to learn how to access the individual RDDs inside a dstream object. So remember, a dstream is an abstraction of all the individual chunks of data flowing in through a stream. We can actually get access to those individual chunks and use that to write out their output one thing at a time. We're also going to introduce the concept of RDD partitioning. Remember, we talked about how Spark can distribute things out across many workers on a cluster. Well, we have the power to actually control how many partitions an RDD is spread across, and sometimes that comes in handy. We're also going to talk about RDD caching and persistence, which is a very important concept for maximizing the performance of your Spark job and preventing it from doing unnecessary work more than once. So let's just dive into the code and take a look at what's going on. So first things first, go to the resources for this lecture and download the savetweets.scala folder to wherever you download stuff from your web browser. Hit pause and go take care of that right now, please. All right, and when you're ready, go ahead and open up Eclipse from the Scala IDE. And we're going to import that script into our project. So to do that, open up the Spark Streaming Examples project, open up source and then our package name. Right-click on that and say Import. And go to File System, browse to wherever you download your stuff, where you downloaded the Save Tweets Scala file. For me, that's C Downloads. For you, it's probably somewhere else. Go ahead and select savetweets.scala and hit Finish. All right, and we should be able to open that up now. So let's take a look at what's going on here. This is similar to the example that we started with, where we were just printing out tweets as they came in, but the twist here is that we're actually going to capture them all and save them to disk. So let's take a look at how that works. So we start off declaring the package that our code is in as usual. We import all of the various Spark libraries that we need and our own utilities class, which contains our little helper functions for setting up your Twitter credentials and setting up log levels. And then we set up our object. Now, I've glossed over this a couple of times, so let me give you at least a simple explanation as to what's going on here. An object in Scala is basically the same thing as a singleton in other languages. So it makes sure that there's some static instance of this save tweets class that Spark can call the main function on. So that's all that's really going on with this object declaration here. And inside the save tweets object, we have our main function, which is where all the magic happens. First thing we do as before is set up all the credentials for your Twitter account. And then, just like before, we set up a streaming context that will actually use all of the cores on our local machine. We're going to call this context save tweets, and we're going to specify a batch size of 1 second for this stream. Set up our log level and create a Twitter stream just as we did before, using the Twitter utils class that's part of the examples that come with Spark. All right, and we're still not doing anything really different than we did from when we were printing tweets. Again, here we're going to extract the text from each tweet status object. So what we're doing here is taking the dstream of raw tweet status objects that comes in from our receiver, and we're calling map on that dstream to map each status object to just the text that's in that object. So this is going through every row, every tweet that comes in, and just extracting the text from that tweet and putting that into a new dstream called statuses. All right. Now we could just cheat and call save as text files, and that would dump out everything in that dstream as it comes in. But let's do it the hard way. Just give us a little bit more control and show you more about what's going on under the hood. So what we're going to do here is first of all set up a counter that will at most save 1,000 tweets. We don't want to fill up our hard disk if we end up running this forever by mistake, right? So just as a little bit of insurance there, we're just going to suck in 1,000 tweets and then stop. So let's look at what's going on here. Statuses, if you'll recall, is our dstream that contains the incoming text of every tweet. So we've transformed the raw tweet dstream into a new dstream that just contains the text of each tweet. And what we can do is access each individual RDD in that dstream as they come in. And that's what for each RDD does. So what we're saying here is for each RDD, I want to pull out both an individual RDD from the dstream and a timestamp that you can use or not use. It doesn't matter. We're not actually doing anything doing much with it here except using it for the file name. And for every RDD and timestamp that comes in, we're going to associate that with some expression that we call. So given an RDD that's arriving, we'll first check and make sure there's actually something in it. It is possible to have empty RDDs come in, and there's no point in it doing anything with them. But if we have a count of greater than 0 on that inbound RDD, we can start to do some processing on it. So, a couple of things going on here that are worth talking about. First of all, we're going to repartition this RDD into a single RDD. And what that does is consolidate the RDD down into a single partition. It might be distributed across a cluster, but we want to get access to everything all at once. And that's especially important if you're doing something like dumping it out to a database, because if you create a database connection to output your stuff to, and your data is actually distributed on multiple PCs, that database connection isn't going to be valid on all those different PCs. So you first need to consolidate everything back together into a single partition so you can actually use a single database connection to write that data out. It's just making sure that all the data is where you want it to be. Okay. Now, since we're running locally, only on one PC, that's much less important. But if you're on a cluster, that would be important. The other thing we're doing here is calling cache on it. And the reason we're doing that is because if you're going to actually do more than one action on an RDD, it's important that you cache it first. The reason being that every time Spark sees an action, it will go and compute that directed acyclic graph to figure out the optimal way to get the data that you want. And if you do another action on that RDD, it might do that all over again and actually reprocess the entire RDD from the ground up. So to prevent that from happening, if you call cache or persist on an RDD object, that ensures that that same RDD stays in memory so that if you call multiple actions on it, it doesn't have to go back and recreate it from scratch. Okay? So you can see here the first thing we're doing on repartition RDD is save as text file. So on an individual RDD that comes in that we've repartitioned down to one partition, we're just going to say save that to a text file, and we're going to name that with tweets_timestamp. And the name here is a little bit misleading. It doesn't actually save it to a single file, it actually saves it to a directory with that name, with a bunch of individual files underneath it, which we'll see when we run it. And then the other thing we're going to do to repartition RDD is call count. And that's just to make sure that we don't exceed 1,000 tweets. So we keep a running count of how many tweets we've actually dumped out. If that actually, we'll print that out as we go along so we can see something happening as these RDDs get processed. And once that exceeds 1,000, we will exit. Okay? Now, something that's a little bit confusing here is for each RDD, you have to make sure you don't think about this code in a procedural, sequential manner. Remember, what we're doing is just defining a workflow, if you will, of processing that happens on this stream as it comes in. So don't think about this all happening in order and in sequence. For each RDD is not going to wait for the D stream to terminate and then go back to the beginning of time and process every RDD that came in. No, it's going to do it as the stream processes over time, one little bit at a time. So that tripped me up at first. So, make sure you understand that. All right. So like I say, you can do things like write it into a database or whatever you want. And we don't actually need a checkpoint in this example because we're not keeping any stateful information around. But if you did, you could set a checkpoint directory. Make sure, of course, that if you are using a checkpoint directory, that's on some distributed file system if you're running this for real. Because the whole point of a checkpoint is to be able to restore your job if your master node fails. And if your checkpoint is stored on that same node, it didn't do you much good. Okay, so makes sense? Take another look at it if you need to. Go ahead and hit pause and stare at this code a little bit longer. It's pretty self-explanatory, and I've got some comments in here to explain what's going on. So make sure you can understand the concepts here. And if you're good, let's go ahead and run it. See what happens. So to do that, go up to the Run menu. We need to create a new run configuration. Double-click Scala application, and we'll call this Save Tweets. And our main class is going to be com.sundogsoftware.spark. Wow, I can't type today. Streaming.saveTweets. Okay. And then we can just go ahead and hit run and let's see what happens. All right, so you can see the tweet count increasing as we process more and more of that stream, and once it exceeds 1,000, it should stop, and then we can go and take a look at what we got. So what should be happening is that for every batch that comes in, we should be dumping out a directory with that timestamp. And looks like it terminated the way that we wanted it to. System.exit is the way we exited out of this thing when it was done, which isn't the most graceful way of doing it, but it is quite effective. But just ignore all those warnings and whatnot. So let's see what we got. We'll go back to our workspace folder, which is C Spark Streaming Course. And under Spark Streaming Examples, that's the directory we were running within. And look at that. Sure enough, for every second that we had a batch that came in, our script went out and dumped out a directory full of the stuff that it got during that time slice. So let's open that up. Take the first one. Yeah, let's take the first one, for example. And you can see there's a bunch of stuff in here that is above and beyond the actual data that we wanted. There's a bunch of success here and CRC codes that you want. But if you just open up the part file, and we can use WordPad for that for now, you can see we actually dumped all those tweets to disk. And we got lucky. I don't see anything obscene in here. I actually had to block something out in the previous video about this stuff. You know, my WordPad here can't do a good job of displaying Unicode characters, so you see a bit of garbage in there, but that's just foreign languages, probably some sort of Arabic. And you can see it actually works. So we are dumping tweets to disk here. Pretty cool. And notice also that we're seeing part-0000, and that's the end result of repartitioning that RDD. So, you know, one of the challenges I have for you that we'll talk about in a moment is to change that behavior and see what happens. But if we did not repartition down to a single partition, you could potentially see multiple parts of data here. And that makes life even more complicated because now you have to combine all that data somehow, potentially. So, not the most practical example, but it does show how you can output data from Spark Streaming. In the real world, you'd probably be outputting this to a database of some sort, you know, as opposed to a bunch of, you know, loose directories somewhere. At the minimum, you'd be outputting this to a distributed file system and not just some local file system like we're doing here. But it illustrates the concept, and that's all we want to do at the moment. So there you have it. Save tweets.scala, listening to a stream of, that's hard to say, a stream of Twitter data, and dumping out the tweets to disk as it goes. There you have it. All right, let's talk about your challenge, because this is a hands-on course. I want you to dive in and play around with it. So your challenge, like we talked about, try removing the repartitioning on those RDDs as we iterate through them and save them out, and see what effect that has on the output that we get. You might want to delete the folders that we already created just to prevent yourself from getting confused there, but go ahead and try that out and see what it does. And the real objective here is just to get you comfortable in modifying these scripts and playing around with them. If you see something else you want to try out, definitely go for it. That's the way you learn this stuff, just by manipulating these examples and getting more and more comfortable with what's going on and getting confidence in your ability to actually change it and make something meaningful happen. So give that a try, and then we'll move on to our next topic. For our next example, we're going to actually keep track of the average length of a tweet as we go through our stream of tweets, so a little bit more interesting. Maybe you need to output your tweets to a database or something, but maybe another use case would be actually computing aggregate data or some sort of data about the tweets themselves as they come in and maintaining that over time. So let's see how that works. Stuff we'll learn in this example. First of all, we're going to use a thread safe counter within our driver script so that we can safely keep track of things as processing happens. And we're going to do something a little bit more complicated with our D streams than just, you know, extracting the text and saving it somewhere. So we're just going to keep on working our way up through these examples of doing more and more complex operations. And that's kind of the main point of this example. So let's get the code and take a look. So go ahead and download the average tweet length.scala file from the resources for this lecture and save that wherever you download your stuff. Hit pause, take care of that. When you're ready, let's move on. So back to the Scala IDE in Eclipse, we're going to right-click again on our project for our package for com.sundogsoftware.sparkstreaming inside our Spark Streaming Examples project. And we're going to import that script you just downloaded. So again, go to the file system, browse to where you download your stuff, wherever that may be, and select average tweet length.scala and bring that into our project. So let's double-click on that, take a look. Alrighty, a little bit more of a complicated thing going on here, huh? So we're working our way up. Alright, the usual boilerplate stuff. We declare our package, we import the stuff we need from Spark. A couple of new things that we're importing are java.util.concurrent, and that's because we're going to be doing some multi-threaded stuff in this script, just to be safe. We're going to call our object average tweet length and kick off our main function. Usual stuff, we're going to set up our Twitter credentials using our utilities function that we wrote. And we're going to set up a streaming context again, running locally, just on our own PC on all of our cores. We're naming this context average tweet length and setting up a 1-second batch size. Set up our log levels, create a stream from Twitter just like before, and also just like before, we are going to extract the text only from each tweet that comes in. And we're going to keep track of that in a dstream called statuses. So the statuses dstream only contains the text of all the tweets coming in. Now the next thing we want to do is extract the length of those tweets, because that's what we're interested in computing over time, the average tweet length. So we create a new dstream called lengths, and this just maps the statuses dstream using this function. It transforms the status string that comes in from the statuses dstream into a length integer. That is just the length of each status tweet in number of characters. So now we have a new dstream that we got from transforming the statuses dstream from its actual tweets to just the length of each tweet. So kind of a pattern you see often is you want to keep reducing your dstreams down to just the data that you need. And the less data you start pushing around, the faster and more efficient your scripts will get in Spark. All right, so we have this dstream of tweet lengths, but how do we keep track of the average? Well, to compute the average of anything, you need both the total and the number of samples, right? So you're just going to take the total number of characters in some sample of tweets divided by the number of tweets, and mathematically that will give you the average tweet length. So that means we need to keep track of two things over time. One is the total number of tweets and the total number of characters. And to do this, remember, Spark is all distributed D, it's running concurrently and whatnot, so we need to do this in a thread-safe manner. Even though we're keeping track of it within our driver script, we need to make sure that we're using this atomic long object, which is a Java object that can let you add and access a long integer value in a thread-safe manner. Okay? So we're going to take advantage of that. And as new data comes in on our dstream, on our lengths dstream, again, this just contains the tweet lengths for each tweet that came in. We're going to go access each individual RDD as it comes in. And this time we don't care about the timestamp, we just want to access those RDDs and count up the information that's in them. So first we check again to make sure that each RDD is not empty. And if there is stuff in there, we are going to take the total tweets atomic long, get and add it in a thread-safe manner. So that basically adds count, which is the number of tweets in that RDD, to total tweets. So see what's going on here? We have an RDD full of tweet lengths. We're using count to extract how many rows of information are in that RDD, and we use that to keep a running total of how many tweets in total we've processed. Okay? Now, here's where things get interesting. We're going to be using a reduce function on the RDD to add up everything inside of it. So what reduce xy to x plus y does, we're saying I want to combine everything together in this RDD into one final value. And I'm going to use this expression to do that combining. So whenever I have two different subtotals within my RDD, the way that I combine them is just by adding them together. So basically this means I'm going to go through the entire RDD of tweet lengths and add them all up together, because I'm using x plus y to add everything up as I go through it. So what this ends up doing is returning just an integer. That is the total number of characters encountered within that individual RDD. So I can take that total number of characters within the RDD and use get and add to actually add that to the total chars running counter that I have in a thread-safe manner. And as we go through, I'm going to print out our running totals as we go, just so we can see some progress as things get processed. Okay? So, again, take a look at that again if you need to. Hit pause and let it sink in. All we're doing is we're going through each RDD in a dstream as it comes in. And we're going to keep a running total of the total number of tweets in that RDD and the total number of characters encountered in that RDD, and keep adding it up as we go through. All right. And we can just watch this go through over time. We're printing up basically our running totals here and also the running average over the data that we have so far. When we're done, set up a checkpoint. Again, in the real world, that would be in a distributed file system, and start and await termination. One other thing worth mentioning, there is actually a more Spark streamy way of doing this sort of a thing without resorting to using Java objects for thread-safe counters. We have a map with state function we can use, and later on in the course, in the advanced section, we'll talk about how to do that. Okay, but for now, this will serve our needs. Let's go ahead and run it. So, as usual, go up to Run and set up a run configuration for this guy. Double-click on Scala application, And we will call this average tweet length. Main class com.sun.software.sparkstreaming.average tweet length. Just like that. And off we go. See what happens. All right, it's working. So you can see this running count of all the tweets that we've received, the total number of characters we've seen in all those tweets, and the average of how many characters we see in the average tweet. It's kind of interesting. On average, it's about 77, it looks like. And what's the upper limit for a tweet? 140, I think it is. So most people aren't even taking advantage of all the characters they have, which is a little bit surprising. I always thought people just crammed as much as they could in there. It's actually a fairly stable number. So, hey, at least today, the average tweet length looks like it's around 76 characters. Pretty cool stuff. All right, let's talk about your challenge to actually extend this and get your hands dirty with it. Hit stop when you're done. So my challenge for you, go back and modify that script to actually just keep track of the longest tweet you've encountered, the maximum tweet length. This is actually a simpler problem because instead of keeping track of these two running totals, you can just keep track of one value that's the greatest tweet length you've encountered as you go. So give that a try. Again, the objective is just to get you more comfortable and hands-on with this code. Give it a shot, and then we'll move on. All right, I've been working you up to more complicated examples, and this is our most complicated one yet. What we're going to do this time is actually keep track of the most popular hashtags from our stream of tweets, and we're going to do that over a sliding 5-minute window. So we're going to see a lot of new concepts introduced in this example. First of all, we're doing a much more complicated chain of transformations and actions on this stream. So we're going to see, you can do some pretty complex stuff and do it in a distributed manner with a Spark Streaming D stream. We're also going to introduce the use of the filter operation on D streams for the first time. And we'll show you a case of using flat map instead of map on a D stream to bust out a D stream into a D stream of even more elements. We're going to also show you using windowed transforms. Remember, we talked about windowing a few lectures ago. We're going to see those in action finally. And we will also, for the first time, see the use of key value RDDs, where we can actually associate values with individual keys in an RDD and then use a reduce operation to consolidate all the values for a given key. And finally, we'll take a look at sorting RDDs to get our final results. So a lot of stuff to get through. Instead of just diving into the code, I want to talk you through the concepts first. So let's do that. So here's our strategy. We're going to start off by creating a Twitter stream just like we would normally. So we just go ahead and create a stream from Twitter utils, and as we've done before, we're going to use the status get text method to just extract the actual text of the tweets themselves into an RDD called statuses. So nothing different yet. So just for the sake of making this a little bit more fun, let's imagine that people are out there tweeting about Bodie McBoatface. And if you don't know the story of Bodie McBoatface, the UK recently is launching a new polar research vessel. And they actually made the mistake of opening it up to the internet to have a little contest of what they should name this new ship. And of course, the internet being what it is, the top result so far is called Bodie McBoatface. Now, I've heard they're not really going to name the ship this, but it's still pretty funny. And there have been some notable follow-up names, such as I like big boats and I cannot lie, or what iceberg. So let's imagine people are tweeting like crazy about this on Twitter right now. Some tweets that might come in might be vote for hashtag Bodie McBoatface, or vote for I like big boats and I cannot lie, or no, vote for hashtag what iceberg. Are you crazy? No, hashtag Bodie McBoatface all the way. So in this sample data set here of tweets, the most popular hashtag would be Bodie McBoatface, right? That's what we're trying to figure out. So how do we do this? Well, step one. We have to, first of all, split up these tweets into individual words. We need to extract these hashtags somehow and get the things we're interested in. So the first step is to break tweets into individual words. And to do that, we can use the flat map operation. So remember, map has a one-to-one relationship where you're transforming every row of one D stream into another row of another D stream. But with flat map, you can actually have a different number of output results than the input. So since we want to have an entry for every word in a row, we're going to end up with many more entries in our resulting D stream. So what we're going to do is call flat map and use this little expression here to map the tweet text string that comes in from the statuses RDD. We're going to split it out based on space characters into individual words, and then put the resulting list of words into the tweet words D stream. So what we have now is a D stream that looks like this: individual words, one on each row. Vote for hashtag Bodie McVoteface, vote for I, and so on and so forth. Next step, all we care about are hashtags, remember. So we can throw away all the words that aren't hashtags, and that will ease our processing by a great deal. So we can use the filter function for that. All we need to do is call .filter on tweet words and provide an expression that has some Boolean result that tells me whether or not I want to preserve this particular entry in the D stream. In this case, we're going to test whether the word, we're going to name the input word and test if that starts with a pound sign, meaning that it is a hashtag. So the effect of this will be to only extract the actual hashtags, or anything that starts with a hash, into the hashtags D stream. And so now in our little example data, we'll end up with hashtag Bodie McVoteface, hashtag what iceberg, and hashtag Bodie McVoteface. So you see where we're going with this. Now the next thing we have to do is somehow count up the final results. And one way we can do this is to create a key value D stream. So all of our little individual RDDs are going to become key value RDDs, where instead of a single hashtag element in each row, we're going to have a tuple instead. That is a key and a value, where the key is the hashtag and the value is going to be the number 1. Why are we doing this? Because we can use a reduce operation next to actually count up everything. Reduce will combine together all the values for a given key and use whatever operation we want to combine them together. So the trick here, we're going to set things up into these tuples, these key value pairs, where the key is the hashtag and the value is 1. We'll do a reduce operation, and what that will do is combine together all of the tuples for a given hashtag. So say for a hashtag Bodie McVoteface, it will then receive all the ones that are values from every time that showed up. And we can say to reduce it together by adding them all up, add up all the ones, and we get the final count. So you've seen me do this trick before if you've taken my other courses on MapReduce or Spark. Same idea here applies. Now finally, we not only want to reduce this stuff, but we want to reduce it over a sliding window of time. So we're only going to be looking back over the past 5 minutes. Otherwise, this stuff will pile up forever, and you don't want that. So, we already talked about the trick of doing the key value pairs where we reduce everything together by adding up all the values, but we're also going to do that within a window. So we're going to use the reduce by key and window function on our hashtag key values RDD. And by doing that, we can provide a function not only on how to combine together individual values for a given key, but as an optimization, you can also provide it with a function for removing something from it. And this just lets it do it a little bit more efficiently. There is a version of this function that only takes the addition part. So if you don't want to think about it too hard, it's an option, but this lets it run a little bit faster. And we're going to give it a window size of 300 seconds, which is 5 minutes, and a slide time of 1 second. Got it? All right, so what this ends up doing, like I said, the reduce part of this will combine together all the values for a given key and combine them using this function, x plus y. So we end up with Bodie McVoteface and then a list of 1 and 1. The 1 and 1 gets added together into 2. So the final result in hashtag counts would be Bodie McVoteface 2. And since we're doing this over a window, this is from the past 5 minutes basically, and we're updating that result every 1 second. Poor What Iceberg only got 1 hit in our sample data. Final thing we need to do is just sort and output our results. So when we do a reduce operation, we end up with these tuples of keys and the combined value. And so that final count that we want is going to be in the ._2 element of that tuple. Remember, when we dereference a tuple in Scala, you refer to it by ._, which field number it is, starting at 1. So we suck out the counts with this x._2, and we also call sort by to actually sort the RDD inside that D stream based on that count number. Now, let's talk a little bit about what's going on here. Hashtag counts was the result of the reduce by key and window call that we made. Now, we know that that will return a new D stream that has a single RDD in it. So it's actually safe to just call transform on that one RDD and sort the results, and that will still give us what we want in sorted results, because there's only one RDD, so it's not going to get split up into multiple different sorted lists. So it's something you just have to kind of know about how that works. When you do a reduce by window operation, it will just give you back a single RDD. So you can do tricks like this and get away with it. Finally, we'll call .print on the resulting D stream, and that will just print out the top 10 results that we have. So what we've done here is we have an algorithm that will count up the top hashtags over the past 5 minutes every 1 second, and sort them and show you the top 10 results over time continuously. So as you can imagine, watching this can be kind of fun. So let's go ahead and do that next. We'll actually import the code and run it and see what's trending today. Okay, so let's run this thing and see what the most popular hashtags are. First things first, download the popular hashtags.scala file from the resources for this lecture, please. And when you take care of that, we can move on. So as usual, we're gonna just right-click on the package here that we're working with under Spark Streaming Examples and import from the file system wherever you downloaded that script to. So in my case, that's going to be C downloads. In your case, probably something else. Select popular hashtags.scala and finish. And now we can open this up. All right, another quick review of what this code is doing. So the usual boilerplate stuff up here. Set up the Twitter credentials, set up our streaming context just like we have in the past. Set up logging, create a Twitter stream, extract the text from each tweet. And now things start to get interesting. So first thing we do is we separate out each tweet into a list of words, and that gets put into a new D stream called tweet words using the flat map operation. So my flat map is taking each tweet and busting it out into a bunch of new entries split by the space character. So I end up with tweet words, which is this giant D stream of every word in every tweet that comes in. Now I want to get rid of everything that's not a hashtag, so I can use filter on tweet words and pass this expression that will only pass through things that start with a £. So now we have a hashtags D stream that only contains hashtags that have come in. Now I'm going to do that trick of converting this to key value pairs. So I'm going to map my hashtags from just a simple hashtag string to a tuple that has a key of the hashtag itself and then a value of the number 1. And I can use that to use reduce by key and window to actually combine all of the entries for every given hashtag together and add up all those ones to get the final count for every time a hashtag occurs. So again, we're calling reduce by key and window on this D stream of tuples of key value pairs of hashtag to the number 1, and we're saying we're going to combine them together using an addition operator, and if you need to remove something, we're going to subtract it out. And again, that's just a optimization you can do to make reduce by key and window more efficient. We're going to specify a window of 300 seconds, 5 minutes, and a slide interval of 1 second. Okay? Now, just so you can, recognize other people's code, you'll often see this written in this sort of shorthand syntax using a wildcard underscore character. So underscore plus underscore comma underscore minus underscore comma is equivalent to this code here where I was a little bit more explicit. I think this is a little bit more explicit as to what's going on when you read it, but if you are familiar enough with Scala, that's a lot shorter to look at, and easier to type. So the final thing we need to do is sort the final results. So we have this hashtag counts D stream that will contain the final results of each hashtag and the number of times it occurred. And we just happen to know that reduce by key and window will return a D stream with a single RDD in it. So I can just call transform on that D stream to apply some expression to each RDD, to that single RDD in this case. That will just sort that RDD based on the ._2, or the value of the tuple, which is the count. Okay? And the final result goes into the sorted results D stream, and we just print out the top 10. So do the usual stuff, set a checkpoint directory, started, await termination. Let's see what our top hashtags are right now. Could be anything. All right, as usual, run configurations. Double-click Scala application. We'll create a new configuration called popular hashtags. And the main class is com.sundogsoftware.sparkstreaming.popular hashtags. Pay attention to capitalization, and hopefully you can type better than I can. Let's run it and see what happens. Here they come. Let's expand this a little bit. So you can see already, Bieber on BBMAs is trending. That is currently the top of the list in the BBMA. I assume this is some music award that I don't really know about. Kids these days and they're Justin Bieber. But apparently the BBMA awards are popular today on April 27th, 2016. So it is. And that's your clear winner. You could just watch this all day. It's actually kind of fascinating. Bieber is just taking over Twitter, apparently. I shouldn't be too surprised. Wednesday wisdom is creeping up there. You can just watch this, all day long, and it will just keep giving you the results over the past 5 minutes. So it's kind of fun. Real time, what's trending on Twitter. Pretty cool. And Twitter itself has sort of a trending feature on it. You have to wonder if they're doing something very similar under the hood to come up with their results. So you can see it's actually not that much code using Spark Streaming. So that's fun stuff. All right, when you're done, when you're sick of looking at this, just hit the terminate button here and you can move on. Let me give you your challenge for this assignment. So this is a really fun example to play with, and I want you to spend some time with it because it's fun stuff. So one thing you can do is start experimenting with different batch sizes or window sizes or slide sizes in this code and kind of get an intuitive feel of the effect that those have. Try setting a window size that's smaller, one that you can actually see happen over time while you're watching it a little bit more easily, and see what effect it has. What does increasing the batch time do? What does increasing the slide time do? So just play around with it and see what it does. Another thing you can try doing is to modify the script to just keep track of the most popular words in general, not just hashtags. That might be an interesting thing. Maybe a little bit scary, considering how potty-mouthed some of the internet might be, but I think you'll end up with some pretty clean results, hopefully. But that might be a fun extension to do to this script as well. So dive in there, play around with it, get familiar with it, and have fun with it. All right, so Twitter data is all fun and good to work with, but we're going to shift gears into something a little bit more practical here. We're going to actually be analyzing live clickstream data from a weblog, or a simulation of it for this course at least. So this is a little bit more akin to something you'd probably be doing in the real world. So things we're going to learn in this example, we're going to listen to streamed data on a TCP socket. Most often you might be connecting to a larger system like Kafka or something, but we'll talk about that in the next session. For now, we're just going to listen to streamed log data coming in on some TCP socket. And we're also going to use regular expressions to parse that data out into fields that we can actually work with in a more structured manner. Everything else is kind of building upon what we learned already and some of the stuff we did in the previous example with the popular hashtags. What we're trying to do here is actually keep track of the most visited URL in our clickstream information coming from our weblog. So to do that, first thing we have to do is set up a stream, a receiver that listens to this weblog data being transmitted to us on some port on the network. And then we're going to use a regular expression to actually parse each line of that Apache access log data into fields that actually mean something. And one of those fields is called the request field, which contains something that looks like this. The HTTP command get, that would be a page request, followed by the actual URL that was requested, followed by the protocol, HTTP 1.0. So if we can just extract out that actual page that was requested from each request field, we can then kind of do the same trick that we did before on the most popular hashtags example, where we just map that into URLs, one tuples. That gives us keys of a given page and the number 1, and then we can use a reduce operation over a window to keep track of the most popular URL requests over some window of time. Okay? And then we'll sort and print the results as we go over the window, just like we did with the most popular hashtag example. So in order to do this, you might not have a web server running on your at home right now. In fact, you probably don't, and if you do, it's probably not getting a meaningful amount of traffic. So we need to simulate this somehow. So in the resources for this lecture, you'll find a download link for the NCAT utility, which is a little utility you can use on Windows to simulate something broadcasting information. And basically we're going to give you an access log from a real web page, a real web server that I have, and we're going to use NCAT to broadcast that out over a given port on your local host. So to do that, we're going to download both the NCAT application and my access log, and we're going to basically pipe the access log into NCAT and tell it to serve that up on port 9999. Okay? So I have NCAT sitting there simulating some sort of source of log data on a TCP port. And then my Spark streaming job can connect to port 9999 and suck data out of it. Okay? So NCAT is kind of like taking the place of some system that broadcasts access log data as it comes in this example. Now, if you're not on Windows, Linux has a built-in command called nc, and I think macOS has the same thing that you can use instead. So if I type ncat, you type nc if you're on Linux. Got it? All right, let's dive in and see what happens. All right, so let's analyze some clickstream data. Now, there are 3 things you need to download for this particular exercise. The first is going to be the script we're going to use, which is logparser.scala. You're also going to need to download the ncat.exe application if you're on Windows. And if you're paranoid about, running executables that you downloaded off the internet, well, I promise there's no viruses in it or anything, but if you're squeamish, you can just watch the videos. I won't be offended. And you also need to download the access log file, which is an actual access log from one of my websites that I own that we can use as a little test case. So get those three things into wherever you download stuff in the resources for this lecture. We need the log parser Scala script, we need the ncat utility, and we need the access log we're going to play with. So once you have those three things downloaded, hit pause here and take care of that, and then we'll move on. All right, so as usual, right-click on our package. You should be getting pretty used to this by now. Import file system, browse to where you download your stuff. And we're going to go for the logparser.scala file. All right, let's open that up and take a look. So just like we described in the slides, let's kind of walk through this again. First thing we're going to do is set up a streaming context locally called logparser with a batch of 1 second. And now what we're going to do is call a little utility function that we wrote that returns a regular expression pattern to extract fields out of raw Apache log lines. So let's take a quick look at that in the utilities.scala file. If you want to see the gory details of what that looks like, this is one giant regex stuck together, and it extracts individual fields from an Apache access log, which is a very complicated format, but it works. So, this might be handy for you in the future. It's actually quite reliable. We can actually extract the IP address of each request, the client, the user, date, time, the request itself, and that's where we're going to actually get the URLs that people are asking for, status code that was returned, if it was an error or if it was successful, number of bytes, the referrer, if it came from another website, the user agent, meaning what browser or bot it came from, and we can compile that all into a pattern, a Java util regex pattern. Now I'm cheating a little bit here. If you remember back in the Scala introduction crash course, I talked about how to do regular expressions in Scala itself. Now, you probably gathered from that lecture I'm not a big fan of how that works. So instead, we're actually using a Java class directly. We're importing java.util.regex.pattern and .matcher. And if you come from a Java background, that's going to make a lot more sense to you. One of the nice things about using Scala is that it's built on top of the JVM. So you actually have access to all the Java classes, all the JDK stuff within Scala. That's okay, you can use them. So we're going to do that. Back to our main script. So we now have a pattern for an Apache log. Next thing we're going to do is connect to our stream of input data. So we're going to use ncat, remember, to simulate something that's a source of Apache access log lines broadcast on port 9999 on our local host. So that's what this does. Socket text stream is a quick way to actually set up a receiver for a given host, in this case the local host, on a given port. And that's going to create a receiver input D stream that just listens to stuff coming in on that socket. Okay. So while we have ncat chugging away, feeding data into this stream, we're going to process it. First thing we want to do is run that regex on it. And what we're going to do is, first of all, get a matcher back from that pattern on the log line. And if that match was successful, if the regex actually worked, then we will just extract the request field, which happens to be field number 5. So if you were to count it up, 0, 1, 2, 3, 4, 5, it's a request field. So what this line does is it takes our raw lines of Apache access logs, applies a regular expression to it to extract the request field, and returns that into the requests D stream. So now we have a D stream that just contains the requests field. And if you recall, that request field itself contains 3 bits of information: the command, the URL, and the protocol. So we need to just extract the URL, which is the middle element. Here we go again. So we're going to take our requests D stream and we're going to apply this expression to it. And we're going to split it up by spaces to separate those 3 fields out. Assuming that we get 3 results, we're going to take the middle one, starting with 0. We have a list, so we start counting at 0 in this case. 1 will get the URL out of it. And if something goes wrong, we'll just return the string error instead. So that goes into a new D stream called URLs that only contains the URL requests for each access log line. And now, this will start to look familiar from the previous example on keeping track of the most popular hashtags in a Twitter stream, same idea applies here. We're going to use that consolidated wildcard syntax that we introduced back then to make this a little bit shorter. We're going to, first of all, map the URLs to key value pairs, to tuples of the key of the URL and the number 1, and then we can use reduce by key and window to count up all the occurrences of each unique URL. So we're going to reduce all the ones for a given URL together and add them all up together. And we're going to do that over a 300-second window that has a slide of 1 second. Okay? So now we should have in URL counts a streaming total of how many times each URL occurred in our stream of Apache access log information. And just like last time, we can take the single RDD that reduce by key and window returns and use transform to get at it and sort it by the count, which is in the second field of value. And print out our top 10 results. Kick it off and let Spark Streaming do its thing. So let's do it. As before, run configurations, double-click Scala application. We will call this configuration log parser. Wow, I really can't type after I've had too much coffee. Main class is going to be com.sundogsoftware.sparkstreaming.logparser. And let's run that. Oh, but before we do, we have to kick off our NCAT process, don't we? Doesn't really matter which one you start first, but let's take care of that. So I'm going to open up a Windows command prompt here. What I'm going to do is cd to where I downloaded all the stuff. So for me, that's c:\downloads. And change that to wherever you downloaded ncat.exe and accesslog.txt, okay? So ncat is the utility that's going to broadcast this text file over port 9999 for me. And access_log.txt is a real Apache access log. So again, if you're on Linux or Mac OS, you're just going to open a terminal instead and use nc instead of ncat. But what we're going to do is type in ncat-kl 9999. That tells it to broadcast on port 9999. Less than sign accesslog.txt. And that's going to sit there and tell Windows Firewall it's fine. We're just doing this on our local host. And that's going to sit there and wait for us to connect to it and feed data to it. So now we can go back here and actually run it. And let's see what happens. Hey, it's working. So NCAT is feeding in lines of access logs, and it looks like the most popular request is for wp-login.php so far. And this will probably change over time. You know, what was actually happening in this access log is some hacker was trying to break into my website, and they were trying to basically try every password in the book here. And there's also a vulnerability in WordPress using the xml_rpc.php script as well that they were trying to get through. So looking at this information can sometimes be enlightening. You know, I was actually under a hacker attack at the time when this was taken. But if you look beyond that, you know, we see that the homepage, just / is actually the most popular request. And some people looking at blogs and some web crawlers apparently are trying to see what they have permission to look at and what they don't have permission to look at. So you can see this go over time and increase. If you were to use a smaller window size, you know, you would see these numbers start to level off, right? Because, you know, once you hit that sliding window, you start to be looking at a constant period of time, you know, until we hit that initial window size of 5 minutes. These are just going to keep increasing. So there you have it. It's actually working. We are listening to a stream of Apache access log data, real clickstream data, over a port on a real network. And we are keeping track of the most popular URL using Spark Streaming. That's kind of awesome. So you can already, you know, the wheel should be spinning in your head right now. There's a lot of practical applications that you can actually build off of this example. So it's a good starting point for some things that you might have to do in the real world. All right, so let's talk about your challenge for this assignment. When you're done, hit the terminate button and go back to your command prompt and hit Control-C to actually stop the NCAT process. And then we can move on. So my challenge to you, modify that script to do something different. Maybe keep track of the most popular referring web page, or maybe the most popular user agent instead. And just get some familiarity with, you know, how the script works, working with it, working with clickstream data in Spark Streaming. This is a very important and very practical skill to have. So, you know, I definitely encourage you to mess around with this. And we'll also get you a little bit more familiar with using NCAT and using our access log data to simulate a stream of it, because we're going to do that in a couple of more examples too. So go have some fun with it and see what you can do. All right, we'll see you in the next lecture. Okay, let's keep building on this clickstream data that we've been working with, and this time we're going to put a little twist on it. Instead of just keeping track of the most popular URL from our clickstream information, let's create a system that will actually look at the status codes that are returned on each access log line and raise some sort of alarm if we start to see too many errors being returned. This way we can wake somebody up to actually see what's wrong with the web server if necessary. People hate these alarms in real life, but someone's got to write them, and it's important that they work well and reliably. There's nothing worse than being woken up on a false alarm. Some things we'll learn in this example. We're going to see another example of using util.try to handle exceptions in Scala. And instead of reduce, we're going to use count by value in window as a little bit of a shortcut. And that's how we're going to actually count up the number of success codes and error codes that we see over time throughout some window. Our high-level approach for this problem: again, we're going to use a regular expression to parse out our Apache access log lines into fields, just like we did before. But this time, instead of extracting the request field, we're going to extract the status code field. And that's going to be some, 3-digit number that indicates, a specific success or failure. Success codes usually are in the 200s and failures are in the 500s, generally speaking. So we need to map those codes into just whether it's a success or a failure in general. So we're going to have a mapping function that will do that. And then we will use count by value in window, which is a lot like reduce, to tally up the total number of successes and failures throughout a given time period. And then we can just keep adding those up as we go throughout each RDD in the D stream. And if the ratio of error to success becomes more than 50%, we're going to assume that something is horribly wrong. And we will, email somebody or do something that will cause somebody's phone to make a lot of noise, right? So let's go check it out, and we'll write a really annoying script that wakes people up at night. How fun is that? Okay, let's write our log alarmer script here. So from the resources for this lecture, download the logalarmer.scala file, please, to wherever you download your stuff. Hit pause while you take care of that, and then we will move forward. So as we always do, right-click on the package here under Spark Streaming Examples and import the file you just downloaded. So I'm going to navigate to where I download stuff and select logalarmer.scala. All right, let's take a look at it. So, just like before, we're going to create a streaming context and we're going to create a regular expression pattern that will extract fields out of an Apache access log line to get the information we're interested in. And as before, again, we're going to set up a socket text stream that listens to port 9999 for some stream of Apache access log data. And again, we're going to use ncat locally on our machine, or NC, to actually simulate that stream for us. All right, now things get interesting. So we're going to first extract the status field from each line that comes in. Before we extracted the request field, this time it's status, which happens to be field number 6. So same pattern as before. We apply our regex, our regular expression, for an Apache access log line to each input line from the lines D stream. And then we're going to apply our matcher to it. If it actually works, then we extract field number 6, which we happen to know is the status code field. Otherwise, we'll just return error. Okay, moving on. So the next thing we need to do is try to map those individual status codes to actual, was it a success or was it a failure or was it some code we don't recognize? So we happen to know that status codes in the 200s represent a success, status codes in the 500s request failure, other codes are something really weird. So first thing we're going to do is map each line of our statuses to a status code, a numeric status code. So coming in, we have a string from each status code that we extracted, and we need to convert that to an integer. Now the thing is, not all strings can be converted to integers, so our code needs to deal with the possibility that what we extracted is not a status code at all, but something bizarre. Maybe there was some problem with the output there. So to do that, to handle that eventuality, we use util.try and wrap x.toInt in that. And then we can safely get the result of that with get or else. So get or else will return the result of x.toInt. So if it is a numeric code, it will return that integer. But if it wasn't, and we get an exception raised by that, it will fall back to the 0 case. So what this line does is it says, I try to convert my status code string to an integer. If for some reason that results in an exception, I'll return the value 0 instead. Either way, I have an integer in status code, which is nice and safe. So if that code is between 200 and 300, I will convert that to the string success. If it's between 500 and 600, I will convert that to the string failure. Otherwise, I will use the string other. So now I have a success failure D stream that instead of individual status codes contains either success, failure, or other on every entry. Now I need to count them all up. So we can use count by value in window to do that. A little bit simpler than the reduce function we were using before. This will just give me back RDDs that have, key value pairs of unique values and their counts. And I'm going to say I want a window time of 300 seconds and a slide time of 1 second, just like before. And this will give me back a D stream of strings and longs. So basically our success, failure, or other is our string values, and it will give me the count of each. So then what I can do is go through that D stream to each individual RDD within it. And again, this is happening over time as we go. We're not like doing this back to the beginning of time all the time. Remember, nothing really happens until we kick off the job. So we go through this. If we have a non-empty RDD, we collect its results into, just a plain old array, a Scala array. So collect can be used to transform an RDD into a plain old array in Scala that you can just do Scala stuff on. So at this point, I've transformed my RDD of, string, some success, failure, or other to the count. I'm going to extract that string into a string called result from the .1, the key value, and the count comes out of the value ._2. So if my result is success, I will increment my success count. If it is failure, I'll increment my error count. And I'll print out the totals as we go along from the current window. And first I'm going to check, if you're going to be waking people up at night, you want to be careful about it. So first of all, let's make sure we have at least enough data to say definitively that something is probably wrong. And I'm going to say rather arbitrarily that if I've seen fewer than 100 requests, I don't really have enough information yet to wake somebody up. But assuming we have enough data to work with, next thing I'm going to do is divide the total number of errors by the total number of successes. And since that does have the possibility to return a divide by 0 error, I'm also going to wrap that with util.try to handle that exception and return a value of 1, assuming everything's okay in that case. So we have a ratio of errors to success. If that ratio is more than 50%, something is horribly wrong. And we can print, wake somebody up, something is horribly wrong. Of course, in real life, you would maybe use some sort of a mail client to actually send a message to somebody's email account that is listened to by somebody's phone, or maybe an SMS message or something like that that would actually make somebody's phone make a lot of noise and wake them up to go look at what's going on. Okay. Now, I do want to stress, don't use this in the real world, please. I haven't actually tested this on a real website, and I don't really know how sensitive it is to false alarms, but some good practices there. And it's also not going to catch every error either. So let's say that your website goes down completely. If there are no access logs being generated at all, then this script has nothing to work with. So that's something else you need to actually watch out for. But just for the sake of example, let's kick it off and see what happens. So as before, we're going to open up a command prompt and go to where we downloaded the ncat utility and my access log. And let's start streaming that again. So I'm going to run ncat-kl9999. So I'm going to broadcast my access log on port 9999 to whoever wants to listen to it. So we've got that running. Now we can actually go and run our script. So as usual, go to run configurations, Scala application. We're going to call this log alarmer. And the main class is com.sundogsoftware.log Spark streaming .log alarmer. Let's run that. All right, here we go. So far so good. We have nothing but successes. Everything's looking healthy. But I happen to know the hackers got to my site during this time and actually shut things down briefly. So if we sit here long enough, look, things are starting to go south. A few failures coming back. Mostly due to invalid requests being made by these hackers. And they're starting to add up. I'm starting to see more failures than successes. And sure enough, we hit that threshold where more than half of the requests over our window were failures. Time to wake somebody up and see what's going on. And, if this were the real world, that would actually wake somebody up potentially, and they would go take a look and see that, yes, the site is indeed under attack. So that might have been a good reason to wake somebody up. All right, when you're done looking at it, hit the terminate button here, and you can go back to your command prompt and Control-C to stop NCAT, and your system will be back to normal. So there you have it. Another practical example of looking at clickstream data or Apache access log data in real time using Spark Streaming. Pretty cool. All right, let's talk about your challenge for this assignment. All right, so some challenges here for you if you're so inclined. You can make this into more of a functional, real-world kind of script by handling a few extra cases here. So, for example, I can tell you from experience that there's nothing more annoying than an alarm script that wakes people up unnecessarily or more often than it needs to. So, one thing you can do is make sure that this script does not issue alarms any more than, say, once every half hour. So if something goes wrong, it sends an alarm and then it shuts up for a while, and only if the problem still is continuing after a half an hour does it issue another alarm. So that is a very important thing to do if you were to do this for real. Another thing you could do to make it more like an actual production script would be to actually extract the parameters that you care about, like the window length, time, the host and the port that you're connecting to, as actual command line parameters to the script. So that args argument to the main function that we've kind of glossed over actually contains all of the command line arguments to the script that you're running. And you can actually look at those and send those in and play around with it, see if that works. Another thing you can do is, we talked about the case of what if your web server goes down entirely and just stops sending log information completely. Well, that's also something you could potentially test for, see if a certain amount of time goes by during which no data is received at all, and if so, raise an alarm in that case too. So these are some more difficult assignments for you. You know, it's a little bit of a challenge, but that's the point. We're getting further into the course, so I want to make sure you're dealing with things that are a little bit more, well, challenging. So give it a try if you want, and gain some more familiarity with the script, a little more familiarity with Scala, and some more familiarity with Spark Streaming. So have at it. Let's talk about structured streaming. This is a new feature introduced in Spark 2.0 that has even tighter integration between datasets and streaming. So how does that work? Well, this was just introduced as an experimental feature in Spark 2.0.0. They're promising that as of Spark 2.1, it's going to be more fully fleshed out and functional. For now, it's just something you can experiment with and start to get a feel of. So let's do that. It is the way of the future, though. I mean, going forward, dataset-based APIs like structured streaming are taking over Spark, it seems. So we're seeing more and more APIs that are centered around the concept of a data set. And what's a data set? Well, in the previous lecture, we talked about using data frames within Spark SQL. And a data frame is really just a data set of row objects. So all a data set is it's just like a data frame, but instead of this unstructured row, it has an explicit type within it. So it's a kind of a subtle difference. You know, from a programming standpoint, it might not really seem to really matter. I mean, basically, we were creating data frames that had structured data in them and explicit case classes that we used with them before, right? So what's the difference? The only real difference is that with a data set, Spark can know at compile time what type of information is inside that data set. So it doesn't have to wait until runtime to actually figure out how to optimize things or if there's a problem. So there are some advantages there to where you can actually discover problems at compile time instead of runtime, and it can do a little bit of a better job in optimizing things. So under the hood, it's the difference is somewhat transparent, but you will see people using the term data set instead of data frame more often going forward. And remember, a data frame is just a data set of row objects, kind of the same thing. So how does this relate to Spark Streaming? Well, in structured streaming, the model that we use is we think of our stream as just a data frame that never ends. So we have a data frame, you know, basically an RDD of row objects, and we just keep appending more and more rows to it as time goes on. And we can issue SQL queries on that data set whenever we want to and get up to the minute information. So instead of, you know, more explicitly looking at things like we did with data frames in the previous example, things get a lot simpler when you think about streaming in this way. So you can just think of it as a database that keeps on growing that you can query and issue analysis on as you please. So it's a much higher level API and a lot simpler to use in many respects. So it's kind of cool stuff. I got this illustration off of the Spark website, and it kind of illustrates the idea here. Basically, you have a data stream coming in, and you know, as before, we're splitting that up into individual RDDs under the hood, but it's all going into this unbounded table. So over time, we just keep appending new rows to that input table, and it just keeps on growing and growing over time. And as with other streaming applications, we can window that. We can aggregate things, you know, by certain periods of time and whatnot. And it also gives us more control over how things are added. The good thing is that Spark Streaming will take care of all the stuff under the hood to make sure that things are added in the right order, things aren't duplicated and whatnot. You don't have to worry about that stuff. The Spark streaming framework will do it for you using structured streaming. So what are some advantages of this approach? Well, one is that Spark streaming code ends up looking a lot like non-streaming code. So often it's just a matter of taking a spark.read command and changing it to spark.readStream, because under the hood, it's just looking like a data frame, right? So there's not a whole lot of difference from a code standpoint of querying a data frame that is containing static information and a data frame that is actually growing over time. From a programming standpoint, these two things are treated exactly the same way. So it can greatly simplify your code and allow you to develop a non-streaming application first and pretty easily convert that to a streaming application, often by just changing one line, like I said, and adding a couple of lines to actually kick that stream off. And it also allows Spark to represent data more efficiently. Having that structured data at compile time allows it to make a more compact representation of your data as it's shuffling data around your cluster, which helps a lot. And by using these SQL-style queries, it can actually run a query optimizer on those queries to actually get even more optimal code at the end of the day. The other big thing here, though, is that Spark 2.0 and beyond is really standardizing on data sets. It's sort of the glue that ties the different components of Spark together. So you're not only seeing it creep its way into Spark streaming as its primary API, but also into things like MLlib and even GraphX. They're all moving toward data frame, dataset-based APIs as well, which means that it makes it easier for these systems to interoperate with each other going forward, and that's a powerful thing. All right, and it's just the way of the future. So, right now, like I said, it's experimental, but, this definitely does seem to be where Spark is heading in the future. That's what they're signaling pretty strongly. So what does it actually look like from a code standpoint? Well, for one thing, in Spark 2.0, instead of creating a Spark context or a streaming context, we're going to create a Spark session object, and this sort of wraps all these other things that we need. So when you're dealing with data sets and Spark SQL APIs, you're going to be using a Spark session. And it looks a little bit different. So you will construct one of these things like this, basically Spark session.builder, and then all the configuration that we would normally do when setting up a Spark conf. You can just do .appname, the name of your app, .master, local star. There is a little hack that's currently necessary in Spark 2.0 on Windows where you need to specify explicitly this configuration setting, and you need to make sure that you have a ctemp folder or whatever folder you specify here for temporary storage. If you're not on Windows, you can leave that out. In fact, you should leave that out if you're not on Windows. We also can specify our checkpoint directory at the same time and get this object. And this Spark session object is what we can use to actually issue SQL queries on directly. And it also contains a Spark context that we can extract as well if we want to do old style RDD operations on that same session. It's perfectly fine. Spark session, you can think of it as just like opening a database connection in other languages. So make sure that you actually stop that session when you're done at the end of the code. All right, so once you have that session, let's say we called it Spark, what do you do with it? Well, in structured streaming, it's pretty cool stuff. So let's look at this example. We have two lines of code basically that are doing a fairly complicated operation here. So let's imagine that we have a logs bucket on S3 and we're just dumping logs into it over time in JSON format. So let's imagine that we actually had something that transformed this into a structured JSON format. Beautiful thing is that readStream or even read can read JSON format directly and infer its schema just based on what's in that JSON file and automatically create a data set or a data frame based on that information. And once you have that data set, you can do SQL style operations on it. So I can say input df.groupBy. Let's say I want to group by the action field, and I can window it over a certain period of time, say 1 hour, using the time column. So this is also a difference in structured streaming. You're not relying on Spark streaming to figure out the order in which things are added to your D stream. You can actually say, I want you to order things by this specific column in my data. So if I have some sort of a creation time or input time or something column, I can make sure that things are actually processed in the order that I want, okay, instead of sort of relying on the arbitrary order that comes in from a D stream. And then I can do .count to just basically count up all of the actions within a 1 hour window with that one line. And hey, let's go even farther. Let's actually write the output out while we're at it. I can connect to a JDBC enabled database at this path and just start writing out the results as we go. So as each hour comes, each 1 hour window comes and goes, I will write that information out to this JDBC database. And in 2 lines of code, we basically have an application that listens to log data that's being dumped into an S3 directory, grouping it by 1 hour increments, and dumping that information out to another database, all in real time. And in the lingo of Spark streaming, we call this a continuous application. So they're calling it that instead of a streaming application going forward. And I think they're kind of setting the stage for maybe moving away from a micro-batch-based API to a true streaming API in the future. So it's kind of cool stuff. This new model allows that in the future. So let's take a look at a real example and see how that actually works in practice. All right, let's see some structured streaming in action. Now again, this is just experimental in Spark 2.0. It's pretty limited in what it can do right now, but as of Spark 2.1 and beyond, this should become maybe even the primary API for Spark streaming. So I've gone ahead and imported the structured streaming.scala file that's attached to this lecture's resources. If you need to, hit pause and go take care of that right now. Same way we've done it before, just right-click on the package and import that in from the file system. Once you're done, open it up and let's take a look. So what we're going to do in this example is stream in Apache access logs, just like we've done before in some other examples, but this time we're going to use structured streaming and use that to actually count up on a 1 hour sliding window how many times each given status code appears within those access logs that are coming in. And by using structured streaming, we're going to model this as just a data frame that keeps on expanding over time. So the code isn't that much different from a non-streaming application. It's a lot simpler. Let's take a look at it. So we'll define our package as usual, to import all the stuff we need for dealing with SQL stuff and also using SQL functions directly. We also have some things in here to actually deal with Java date transformations here. So a lot of the code in this script is actually just dealing with the problem of taking the Apache access log date and time format and converting that into a date time format that SQL can handle. So that's what we'll need for that. All right, so the first thing we need to do is create a case class to actually define the structure of our data that we're going to transform it into. So we're going to start with these just, raw lines of text in an access log, but we want to transform it into this structure. We're going to call it log entry. And it's going to consist of a IP address, a client, a user agent, a date time, a request, a status code, which is what we want at the end, bytes refer, and agent. So kind of a general purpose structure for a line of Apache access log data. We could simplify this and only import the stuff we need, but this might be a useful thing to have around as you go through your career. So I'm just going to go ahead and import everything there. From our utilities class, we're going to import the Apache log pattern, the actual regular expression we use to split up an access log line. And we're also going to set up a pattern for actually making sense out of the date field of the Apache access log. And that's going to be used in this parse date field function. So I don't want to get into this in too much depth because it's not really directly related to Spark or Spark streaming, but all it's doing is taking the date format in the Apache access log and converting it to a SQL timestamp. And Scala doesn't really have built-in utilities for that, so we kind of have to reach under the hood to the JDK and pull out the simple date format class from Java and also the java.sql timestamp class to actually do that. So that's what's going on here. And you can see it's actually returning an option of a string, so it will give us back either a valid SQL format timestamp or it will give us back none if it was unable to actually do that conversion. All right. Next, we need our little mapper function that converts a raw line of Apache access log to a log entry structure. So this is going back to the case class we defined. That's going to impart the structure that we need for our data set. And that's going to be used by Spark to actually transform this into something that looks like a database that we can query. So to do that, we'll first execute our regular expression across each incoming line of the access log. We'll see if that actually matches. And if so, we'll create a log entry by extracting all the different fields that came out of that. And we'll use that parse date field function that we created above to actually transform the Apache access log date to a date that can actually be used in a SQL query. And if something goes horribly wrong, we return none. All right, so let's get into the meat of the script itself, back to our main function here. So again, the Spark 2.0 way of dealing with Spark SQL stuff is using the Spark session interface instead of a Spark context. So we'll do that here. We'll set up our Spark session. We'll call it Spark Builder, give it a name, give it our master. Again, this is only necessary on Windows, so if you're not using Windows, take that line out. If you are using Windows, make sure you actually have a C temp folder, or else things won't work. We also specify our checkpoint directory. Again, if you're not on Windows, you'll want to change that to an appropriate path on your file system. And get or create. So get or create, worth talking about a little bit there. Spark can actually recover from errors. So by saying get or create, we're saying if we actually saved our checkpoint to the checkpoint location, we can pick up where we left off automatically. And if this is actually a new run, we will just create a new Spark session instead. So this actually lets it recover an existing Spark session that may have crashed before. Kind of neat. Set up our log level, and now we'll get into the real action here. So let's call spark.readstream.text. What this is doing is using our Spark session to actually monitor a logs directory on our file system for new data that's being plugged into it. And it's going to import that as a text file ongoing. So what we have here is a data frame, and this is the kind of data frame in structured streaming that just keeps on growing. So we have a data frame called raw data that just keeps getting rows added to it as new files are dropped into this logs directory. Okay, so there's a lot of power in that little one line of code, isn't there? Pretty cool stuff. All right, so now that we have this data frame that just keeps on growing over time, potentially, we need to tell Spark what we want to do with it. So first thing we're going to do is parse that out into a structured data. So instead of just a data frame of row objects, we're going to make that a data frame of actual log entry data. A log entry objects. So by doing that, we will do flat map using our parse log function, and that's going to give us back a data frame of log entry objects. And at that point, we can actually call select on it, just like we would in SQL, to extract the two fields that we care about. Those two fields are status and date time. So remember, what we're trying to do here is actually count up the status codes by hour, and we want to import them based on date time. So that sliding window is going to be based on the date time column. It's a little bit of a different thing in structured streaming. You can actually define the information you want to use for that window to actually operate on. You're not just relying on what happens to come into your D stream over time. You have more control over it with structured streaming. So now to actually do that grouping, we can do something like this, where we create a new data set that is actually taking our data frame of log entry objects, grouping it by status code over a sliding 1 hour window that's using the date time column to define that window. Okay, so this is different from how Spark Streaming normally works. We're actually giving it an actual date time information to do that window over. Okay, then we can do a count to actually count up the status codes in that 1 hour window over that hour. We're going to order it by window. So basically, we're going to keep track of all the counts of each status code by each individual hour, and we want to view this in order by the actual window timestamp. Okay. Finally, we need to output this data somewhere. So we can say windowed write stream with an output mode of complete. So we use complete if we're aggregating information over time, as opposed to append if we weren't. And we're going to format that out to the console. We just want to print it out. And then we say start to actually start the stream processing off. And we just keep going until we're done using query.await termination on this streaming query that we've created. And finally, we call stop on the session when we're done. So let's see how it works, shall we? All right, so what I've done, back in my Spark Streaming Examples folder here under my course materials, I've created a logs folder. And inside that logs folder, I've put an accesslog.txt file, the same access log we've used before in the course. So this is going to kick off our stream with the contents of whatever's in that log file. So let's see how that works. Let's go ahead and I've already made a run configuration for this called structured streaming. So go ahead and set one up yourself if you'd like to follow along. Hit pause. I'll still be here. Okay. Now that we're ready, let's run it. A lot of information in that log file, so it will take a few seconds for it to actually kick off initially. So right now, what it's doing is looking at that logs folder and saying, oh, I have a big old log file in there. Let's start seeding our stream with it. So it's actually processing that stream right now over that 1 hour window and doing our aggregation of status codes. And there we have it. So we've already processed our first batch of the stream here. And we can see that for the 3 o'clock hour, we had 3 200 status codes. And for the 4 o'clock hour, we had 36 200 status codes. And so on and so forth. We've told it to actually order by time, so we can see those times increasing. And for each given hour, we can see each distinct status code and how many times that status code occurred. So hey, it works. But now, this is a sort of a more static operation here. We just looked at a single access log, but since we said read stream instead of read, we can actually keep on adding more log files in there. So let's do that. I have a copy of my access log that I've renamed to accesslog2.txt here. So let's copy that and paste that into the logs folder as well and see if it picks it up. Sure enough, there it goes. So we can see we're actually processing another batch now that it's seen some additional data in the stream. And it's going to chug away on that. Remember here for the 12 o'clock hour we had 42 200 error codes, and now we have 84. So you can see since we actually duplicated that same error log, we would expect everything to be doubled now, and in fact it is. It actually works. So that's right, there you have it. Spark streaming in action. When you're done, hit the terminate button. Now, again, Spark streaming is experimental. In Spark 2.0, they have not worked all the kinks out of it yet, and one of the kinks is that actually recovering from a checkpoint doesn't really work yet. So you want to make sure you open up your C checkpoint directory and delete what's in there, or else you won't be able to rerun this script successfully. It's going to try to recover from that checkpoint, and it's not going to be able to do it yet. But maybe in Spark 2.1. So there you have it, a little bit of a sneak peek at structured streaming. This is probably the way of the future. So pretty important for you to grasp that and be ready for it as it comes. Spark's been pretty good about maintaining backwards support for its older APIs as well, though. So I don't think they're going to force you into structured streaming anytime soon, but it is the direction they want you to head in the future. So it's a good thing to understand this. All right, and there you have it. Structured streaming, Spark SQL. Congratulations. These are important topics to get under your belt, and hopefully you've done it. Go ahead and play around with this if you want, and get your hands dirty. See you in the next lecture. All right, for our final example in this section, we're going to look at an example of using Spark streaming and tying it together with Spark SQL. So we can actually issue SQL queries on our streamed data, which is pretty cool stuff. So we're going to learn about Spark SQL, might be a new thing to you. And we're also going to see using case classes in Scala for the first time in production here. So a couple of new concepts, but mostly we're focusing on Spark SQL in this lesson. So what is Spark SQL all about? Well, it's a way to give your RDDs structure and a schema, so using more structured data within Spark. The way it works is that you take your RDDs from your D stream or from just plain old regular Spark, and you can convert those into what are called data frame objects, where data frames have an actual schema to them, some sort of structure. And because these have a schema, you can actually issue SQL commands on them, and you can also output them more easily to real databases, like something with a JDBC connection or a JSON data, or to a Hive database or a Parquet database, what have you. You can even open up a shell to a Spark SQL instance and actually issue queries on it in real time. So it's pretty neat stuff. So if you want to expose your Spark streaming data or your Spark data in general to people who only know SQL, this is a way to do it. And you have all the power of SQL at your disposal there as well. So a very powerful thing. And using it, it's pretty straightforward, it turns out. So all you need to do is create a SQL context object. And then when you have an RDD that you want to convert into a data frame for Spark SQL, all you have to do is call this toDF function, toDataFrame. And within Scala, this can all be somewhat magical. What you do is you create a new type that embodies the data that you're putting in here in a structured format. So for example, we can use this case class syntax in Scala to actually say, I'm going to create a new data type called record. And this record includes a string that's named URL. Think of this as the column name for a string data. And then we're going to have another column called status that contains integers, and another column called agent that contains string data. And the magic about case classes, this is a syntax we haven't seen before in Scala, is that these names actually have meaning, right? And it's actually going to go and automatically create constructors and accessors for all this data automatically for us under the hood. So it's a very compact way of saying, I want to create a new data type that contains these fields with these names. And that's all I need to actually convert an RDD into a data frame. Because if my RDD contains tuple information that matches this format, then I can just go ahead and convert that to a data frame that has columns of those given names. Okay? We'll see how that works in the code momentarily. So once I have a data frame object, all I need to do is call register temp table on that data frame to associate it with a table name in my SQL context. So register temp table says, take this structured data in this data frame and we'll name it some table name from SQL purposes. And at that point, I can call SQL commands on that table using my SQL context. It's just that easy. It's pretty straightforward stuff, but let's look at the code. It's powerful, straightforward but powerful. So let's dive in. So let's do it. Spark SQL and Spark Streaming working together. So first, please download from the resources in this lecture the logsql.scala file. Hit pause and take care of that. And when it's ready, we'll do the usual dance. Right-click on our package, import, file system, go to where you download stuff, and import the logsql.scala file. Let's open that up and take a look. All right, not a whole lot of code here, so let's go through it. As usual, we're going to create a streaming context on our local host, set up our logging, and as before, we're going to set up a regular expression to parse out Apache access log lines. And we're going to listen to that again on port 9999, just like we've been doing. So we're listening to this stream of Apache access log data on port 9999. Now, what we're going to do here, kind of like we've done before, we're extracting information from that log data just using a regular expression. In this case, we're going to extract a tuple that contains the URL requested, the status code, and the user agent. So let's pretend those are the three things we're interested in querying with SQL. That's all this code does. I'm not going to go through it in too much detail because it's very similar to what we've done in the past 2 lectures. But anyway, same idea here. You know, we're just extracting the URL that we took out of the request field along with the status and the user agent, which happen to be fields 6 and 9. Now, as we go through, as each D stream gets processed, we're going to go through all the RDDs in that D stream as they come in. And here's where the magic happens. So the first thing we're going to do is create a singleton instance of a SQL context. And that's going to refer to this little class down here that just makes sure that we're always using the same instance of our SQL context. There's no point in having more than one. So once we have that, we're going to import the functions we need to use it. By the way, in Scala, you can actually use import statements wherever you want to. They don't have to be at the top of the file like they do in Java. So that can sometimes make for more readable code. All right, the next thing we're going to do is create a request data frame. So what we're going to do is use that record case class that we talked about before. So if you go down here, you can see we've defined this case class called record, and it consists of a URL that is a string type, status as an integer type, and agent, which is a string type. Okay, and again, with a case class, these names actually have meaning. It's going to go ahead and automatically create accessors for those. And Spark can actually use that to infer a data frame object from it. So I'm mapping my tuple that contains URL status user agent into a record that contains that same information. And since I'm using a case class that has names for all those fields, I can call toDef to automatically convert that to a data frame. And now that I have a data frame, I can call register temp table to associate that data frame with an actual table name in Spark SQL. We'll call it requests. And now, check it out, I can actually issue SQL queries on that data frame. So here we have an actual SQL query being run on the results of an RDD from a D stream in Spark Streaming. And we can just issue that command and take a look at the results as we go. And that's going to kick off every time we process our data. So let's see it in action. First thing we have to do is kick off our little ncat process here to actually broadcast our log information. So let's do that again. Again, make sure you're in the right directory for that to happen. And then we'll kick off our script. So run configurations, Scala application. We'll call this log SQL. Class is com.sundogsoftware.sparkstreaming.logsql, and off it goes. And check it out. As data comes in, it's actually working. So we're our actual query is looking at the total count of user agents over time. So looks like Mozilla 5.0 or Mozilla 4.0 has 262. It's all scrolling by so quickly, but you can see we're actually getting real results here. We're seeing counts of the user agents coming in from the stream of Apache access log data as it comes in using a SQL query. And we're actually seeing sort of a standard SQL output there too. So there you have it. Marrying the power of SQL and Spark SQL with Spark Streaming. That's how it works. Pretty cool stuff. When you're done looking at it, hit the terminate button, and though go hit Control-C on NCAT to stop that. All right, let's talk about your challenge. So your challenge, should you choose to accept it, like we said in the slides before, issuing SQL queries is just one thing you can do with Spark SQL. Another application is just to get things in a structured format that you can use to export to other databases or to export to a more structured data format. So why not give that a try? Instead of actually issuing SQL commands, actually write the results out to disk in some structured format like JSON. So for example, you can use .write.json, some file name, on a data frame object to output JSON files. So give that a try and see what you get. It could prove useful for you in the real world. All right, congratulations, you made it through this section. Those are some simple examples of Spark Streaming in action. Up next, we're going to talk more about how to integrate Spark Streaming with other systems. So in our next section, we're going to talk about integrating Spark Streaming with some real-world systems out there that you might need to consume data from. So far in this course, we've been listening to Twitter streams and listening to arbitrary data sent over a TCP port. That's all well and good for learning, but in the real world, you'll probably be listening to data sources that are coming from some other system. And one such popular data source is called Apache Kafka. So let's talk about that first. Usually when people ask me about, what should I cover in my courses, Kafka comes up. So I think it's pretty widely used these days, and it's with good reason. It's a very scalable and robust system. What is it? It bills itself as a high throughput distributed messaging system. So basically it's a publish-subscribe system where Kafka can publish out messages received from a bunch of different message producers, and consumers of those messages can subscribe to given topics to actually listen for those messages. So one example would be broadcasting weblogs that are dropped into Apache access log directories, for example. But it's more general than that. You can actually use it for messaging with anything. And publish subscribe is actually kind of fraught with peril. I mean, it's pretty easy to bring down a network with all the packets this sort of a thing can generate, but it seems like Apache Kafka has actually figured it out and gotten it right. It is fast, scalable, durable, and distributed, and based on its wide adoption, I think it lives up to those promises pretty well. So it's a good, reliable way to send data over a cluster of computers. So if you have, a cluster of computers generating a lot of information and another cluster of computers that want to receive that information, for example, a Spark Streaming cluster, Apache Kafka can sit in the middle and broker those transactions. So this is what it looks like graphically. Basically, with Kafka, you set up what are called topics that are a given type of message that people can produce and people can consume. So for example, a producer might be an individual web host, a web server, and that might be publishing topics of log data. And then I can have consumers, for example, my Spark Streaming job that listens to the topic for logs and consumes that data in a reliable manner. So Kafka just makes sure all the messages get to where they need to go one way or another. And the great thing is that as of Spark 1.3, Spark Streaming can do this in a very reliable manner. It used to be that it had to connect to the Zookeeper host that actually sat on top of Kafka, and there were a lot of room for things to go wrong and for messages to get lost. But today, Spark Streaming can connect directly to a Kafka server, and that way it can actually go back and request information it might have missed if something went wrong. It's a much more reliable mechanism that way, and there's just one less person in the middle that way. So that's what we recommend doing, and that's what we're going to show you in this example. Now, if you're actually going to use Spark Streaming with Kafka, that doesn't come included out of the box with Spark. So you will have to go and download the latest Spark Streaming Kafka package from Maven or whatever your favorite package repository is, and throw that into your Spark lib folder and import that in as an additional external jar file for your project. Later on, when we talk about actually deploying real-world applications, we'll talk about using a tool called SBT that can manage those sorts of library dependencies for you automatically. And when you're actually doing stuff in production, that's probably how you do it, but that's the next section. Well, 2 sections from now. So how does it work? The code itself is actually very simple once you have that library installed. So all you need to do is set up some parameters that give it a list of the various Kafka servers that you want to listen to. So in our example here, we're going to set up a single Kafka server that's going to be broadcasting on my own PC on port 9092. So you just need to set up a map of all those Kafka brokers and where Spark Streaming can find them. Finally, you need to give it a list of topics that you want to listen to, and you can listen to more than one if you want to. But in our example, we're just going to listen to something called test logs, which is a topic that we're going to broadcast our Apache access log data on. And you can listen to, like I said, more than one topic if you want to. And the way that works is that when you actually create your Kafka stream, what you'll receive are these tuples, these key data pairs, where the key is the topic name and the value is the actual information that's coming in on that topic. So you can use that to differentiate messages from different topics at runtime. So to actually create that stream, it's very simple. You just use the Kafka utils object. That's part of the package that we imported into our libraries. And once you do that, all you have to do is call .map to the _2 if all you want to do is extract the actual messages themselves. So since we're only listening to a single topic, we can just discard that topic name that's in the first element of the tuple and just extract the actual messages themselves by mapping them to just extract the .2 element of the tuple. So let's see it in action. Now, I doubt you have a Kafka cluster sitting around on your local network, but I actually went and set one up on Windows for me. So I can actually show you this working in the real world, and I thought that was worth doing because Kafka is such a popular technology these days. So let's go actually stream some data and listen to Kafka for it. All right, let's go ahead and look at some code here that actually consumes information from Kafka. I'm going to let you off the hook here a little bit and not make you actually load this yourself and run it because, like I said, you probably don't have a Kafka server handy. So you can just sit back and relax and watch me do it for once. Anyway, if you do want to set up your own Kafka server to play along with, though, you're welcome to do so. There's a URL here that gives you some instructions on how to set up your own little Kafka server on Windows, and it's actually not that hard. There are several steps involved, but they're all pretty straightforward. But diving into the code, so what we're going to do is set up a very simple example here that takes our old example of looking at the top URLs from an Apache access log. Remember our very first clickstream example that we did. But we're going to modify it so that instead of listening to a TCP port for a bunch of information, we're going to get that log data through Kafka. So we start off like we usually do, import all the stuff we need, including the Kafka package that we need. So we need these two classes to be imported as well, Org Apache Spark Streaming Kafka and Kafka Serializer String Decoder. And again, remember we had to download the Kafka library for Spark and actually install that into Spark's library file and import it into this project for it to work. So we create an object called Kafka example, we define its main function, and we create a streaming context just like we would with anything else. There's nothing different so far. Set up our logging, and we set up a log pattern, a regular expression to actually extract the fields we want from the Apache access log data. So far, nothing different, but now we're going to actually set things up for Kafka. So first thing we have to do is set up this map of Kafka broker hosts and where they can be found. So I'm running a single broker on my local host, on my own machine here that I'm running on port 9092. And if you had more than one, you would have to create more than one entry there. Now you can see that this is a little bit more fragile than the old school way of connecting to Kafka with Spark Streaming, which went through a single Zookeeper host. So it used to be you could just connect to the Zookeeper host, everything would flow through Zookeeper, and Zookeeper would worry about what the actual servers are. So you know, the trade-off of the additional reliability that you get by doing a direct connection to the Kafka servers is that you need to maintain this list of individual servers yourself. If things move around or go to different hosts or go to different ports, you're going to have to change your script to take that into account. So a little bit more maintenance there, but the reliability that you gain is well worth it. Next, we create a list of all the topics that we want to listen to. We're only going to be broadcasting our Apache access logs on a single topic that we're going to call test logs. And it actually expects that in a set data structure, which isn't something we've talked about before with Scala, but it is just another data structure like a list, but it's called a set, and you can just call toSet to convert a list to a set. And we'll set that to topics and pass that in our next line, where we actually create the stream for Kafka. And we say create direct stream, meaning we're connecting directly to the Kafka servers. And here's some more Scala syntax we haven't really encountered much before. When you call a function in Scala, you can actually provide an explicit list of the arguments that it expects here. So sometimes there's ambiguity as to what the types are that a function expects to have as input. And if you need to actually specify those as you do here, this is how you do it. So basically we're saying create direct stream is going to expect to be dealing with a type that includes a string, basically, and a string decoder and a string decoder. So this is telling Kafka that I'm basically processing string data. This is Apache access log data, and I'm using the string decoder to actually serialize that data. And by default, that's just what Kafka does, okay? So the actual parameters we pass in are the streaming context, the Kafka parameters, which is the list of servers that we're connecting to, and the list of topics, or more specifically, the set of topics that we want to listen for. Now, once we create this stream, it's going to basically subscribe to those topics that we specified. So it's going to go to Kafka and say, okay, tell me about everything that comes in on the test logs topic. And what it's going to give you back are these pairs that have topic, name, and then message. Now, in our case, we're only listening to a single topic, so there's not really any useful information in the topic. So we're just going to map this and extract only that second element of each tuple, which is the message itself. So what we've done in this line, we've created a direct connect stream to Kafka that listens to the test logs topic, extracts the message from that, and puts that into a new D stream called lines. So at this point, we're kind of where we were before with our Apache access log parser script. We now have a lines D stream that just contains every individual line of an Apache access log coming in on it, except this time we're connecting through Kafka instead of listening on a port. From there, the rest of the code is the same. So, I'm not going to go through this again. We're just doing the exact same code from our previous example where we apply our regular expression to the incoming Apache access log lines. We extract the URLs from the request field, and we look at a 5-minute sliding window to look at the top URLs for each 5 minutes. And we kick it off. So let's go and actually do it. Like I said, I actually set up a Kafka server already. So I already spun up a Zookeeper host. I spun up a Kafka server. So I've already set up a topic. If we look at my history here for test logs with Kafka. So with this command, I already created a test logs topic on through my Zookeeper host. And the next thing I want to do is actually call Kafka console producer to actually set up a producer that pipes my access log through that topic to whoever's listening. But first we need to listen. So let's go ahead and run this script. Kick it off. And there we go. So it's sitting there listening, subscribing to that test logs topic. Let's actually generate that and kick that off. And we should see that come through. There it goes. So you can see that was pretty quick. It actually shoved that whole log through there all in one big chunk, and we have our results here already. So I can go ahead and hit terminate here. And sure enough, our hackers are attacking our site again. XML-RPC is by far the most popular web request, followed by WP login, also from a hacker attack on this website, followed by the homepage. So there you have it. We just piped a ton of access log data through Kafka on my local machine to Spark Streaming using this source code, and it works just fine. So you could scale this up to an entire cluster, and Kafka makes sure that it can actually handle that kind of a scale. So as long as you have enough hosts on your Spark Streaming cluster to process that data and keep up with it, you should be okay. So there you have it, using Kafka to actually process massive amounts of publish subscribe messages in real time. Pretty cool stuff. Let's move on. Next, let's talk about integrating with Apache Flume. Apache Flume can be thought of as similar to Kafka, but it's very specifically tailored for log data, so for web logs and things like that. And it's also very tightly coupled with the Hadoop ecosystem. So it bills itself as a distributed, reliable, and available service, just like Kafka, for efficiently collecting, aggregating, and moving large amounts of log data. So whereas Kafka was a more general purpose publish-subscribe utility, Flume is more specifically built for log data. And its high-level architecture looks a little bit like this. You have a bunch of web servers in a cloud. They provide a source to Flume, and Flume has a channel that then basically feeds that information to sinks that listen to it. So for example, you might have a sink that talks to HDFS, where the sink is just getting a bunch of log data pushed to it from this channel, and then the sink stores it to a distributed file system. So there's a couple of ways of setting Flume up with Spark Streaming. One is a push-based approach that does just that. So in this approach, you basically set up your Spark receiver, your Spark Streaming receiver, as another sink. So the channel for Flume just keeps pushing data to you, and Spark Streaming can consume that and do whatever you want with it, depending on whatever code you write in your Spark Streaming job. So it's a very simple setup. All you need to do is import Spark Streaming Flume assembly into your Spark Streaming project, and you will have the access to everything you need to do that. It's very simple to configure Flume to actually look at your Spark Streaming setup as just another sink. But push-based Flume is usually a bad idea. It's not the most reliable approach. It's not transactional, so if something goes down, all that data is just going to get lost. And maybe that's okay. In some applications, losing a little bit of log data isn't the end of the world. Another downside, though, is that you have to code your receiver's hostname and Avro port into Flume's configuration. So if your server setup or server configuration for Spark Streaming ever changes, and if anything as mundane as a single worker node going down on your Spark cluster happens, that means you're going to have to go back and reconfigure Flume to actually talk to your new server host. So that can be kind of a pain in the butt, right? You get server goes down on your cluster for Spark Streaming. Now you have to shut down Flume and reconfigure it and start it back up again. That's not an ideal situation at all. But the upside, the good thing, is that it's very easy to set up. So in Flume, all you would have to do to set something like this up would be to set up a little something like this that makes your Spark Streaming cluster look like an Avro sync. You just give it the host name and port that you want to listen on, and you're pretty much done. So let's take a look at some code of how push-based Flume works. Just keep in mind that while this is an easy way to start, it's probably not the best approach in production, but let's take a look at some code regardless. So let's take a real quick look at some push-based Flume configuration here. And if you want some more depth on integrating Flume with Spark Streaming, you can check out this link here at the top of the script here that's in your resources for this lecture. A lot more information there if you need more and you really want to do this in the real world. But just to illustrate how easy it is to use Flume in a push configuration, let's take a look at this example. It's just a retooled version again of that top URL sample that we used earlier in the course, and the same sort of thing we did with Kafka. And you can see there's even less code involved here than there was with Kafka. It's quite straightforward. So everything here is pretty much the same as the original example that we had that just listened to a TCP port for log data. The only difference is that we're doing these lines here. So to create a Flume stream, we just call the flume utils.createStream function, and all you have to do is pass it in your streaming context, a host, and a port. That's all there is to it. It's just that easy. It's very, very simple. Now, the only little complication is that the stream that gives you, the D stream that you get created from that, consists of these Spark Flume event objects. So if you need to actually extract the messages themselves, there's a little bit of extra code here, and that's what this map function does for you. Basically, this will take in the Spark Flume event object called getBody to get the body of the message itself, convert that to a byte array, and convert that to a string. So if what you're publishing is string-based data, which most likely you are since we're talking about access logs or logs of some sort, you would have to do that step to actually convert this into a D stream of strings. And from that point, we have a D stream of string values, a D stream of individual lines of Apache access logs, and we can continue to handle that just like we did before. So nothing special beyond that point. That's all it takes to set up push-based Flume. Very simple. Of course, the upside being the simplicity of configuring and setting this up, but the downside is, in production, not the most reliable approach, and it's also not the most maintainable approach. So if you just want to get up and running quickly, that's fine, but I don't recommend doing this in production. So let's go back and look at pull-based Flume instead. So let's talk about pull-based Flume in a little bit more detail. So in this approach, instead of just sitting there waiting for Flume to push data to Spark Streaming, what you do is you install a special custom sink into Flume that actually pulls data from Flume. And that way, if your Spark Streaming cluster goes down, it can ask that special sink that's made just for Spark Streaming, hey, go back and pick up where we left off. Please resend this information if necessary. So that's a much more robust architecture for dealing with failures on your Spark Streaming cluster. But it requires more work. So it means you have to go and get the Spark Streaming Flume sync package and install that into your Flume build itself so that you have access to this special sync that's made just for Spark Streaming. But if you take that effort, you do end up with a much more reliable configuration. So once you have that plugin for Flume installed for Spark Streaming, it's called Spark Streaming Flume Sync. You just configure it with a few lines of configuration code here, nothing too fancy. And on the client side, on the Spark Streaming side, when you're writing your script, you just call flumeutils.createPollingStream instead of createStream. And from there on, it's pretty much the same from a programming standpoint. So Although you have to do a little bit more work in setting up Flume for this configuration, it's not any harder from the programming side on your Spark streaming job, so that's a good thing. So we talked about Kafka, we talked about Flume. How would you choose one over the other? Well, Flume is more tightly integrated with Hadoop, so if you are building an application around the Hadoop ecosystem, Flume might be a more natural choice because it's going to work a little bit more out of the box with Hadoop components. But Kafka is generally regarded to be more reliable and more scalable. So, there's a little bit of a trade-off there. It's easier to get up and running with Flume. Kafka, a little bit more setup potentially. You might have to write your own code for producers and consumers potentially. But if you take that extra effort, you'll have a system that's more reliable and scalable. And at the end of the day, you want a system that's not going to wake you up at night because something went wrong. That's a lot more important than spending a few extra hours of writing code. But you can actually do both. With Flume, you can support Kafka syncs and Kafka data sources. So you see an increasing amount of people that are actually combining Flume and Kafka in this way and getting the best of both worlds. But let's look at some code. So for the recommended configuration of pull-based Flume in Spark Streaming, let's see what that looks like. So let's have a quick look at some pull-based Flume code in Spark Streaming. And there's not a whole lot that's actually different from the push-based example. Most of the difference is in the configuration side. So again, you need to install that custom sync for Spark Streaming into Flume itself and configure it, and that's most of the work. When you get down to it on the Spark Streaming end, when you're writing your actual driver script, all you need to do is, instead of calling create stream on Flume utils, we're going to call create polling stream, telling it that we want to connect to that special Spark Streaming sync for Flume instead. That's going to pull information rather than get information pushed to it. That way it's more reliable and we can deal with failures better. And that's really the only difference from the push example. So from that point, we are still getting these Spark Flume event objects that we need to call getBody.array and convert to a string. So we have that same old map command here that transforms that Spark Flume event into an actual string-based message. And from that point on, you have a D stream full of strings. And that's all there is to it. It's really that simple. From there, we just treat it like we did everything else. So all of the actual Flume pull-specific code is just these 2 lines of code here. At that point, you just have a D stream of strings to work with, and from there on, you can do whatever you want with it. So it's just that simple. All right, let's look at some more technologies. Next, let's talk about integrating Spark Streaming with Amazon's Kinesis service. So what is Kinesis? Well, it's specifically called Amazon Kinesis Streams. They've actually launched a few other products around Kinesis recently called Kinesis Firehose, which is a service for actually pumping data into Kinesis from different sources, and Kinesis Analytics, which can sit on top of Kinesis Streams to give you some analytical data. So we'll refer to Kinesis as Kinesis Streams from now on. And it is a service provided by Amazon Web Services. So if you are using AWS to host your application, then Kinesis might be a natural choice for actually brokering messages between your systems. So let's say you're running a website on AWS using Amazon EC2 Elastic Compute Cloud instances. Kinesis might be a good choice for actually piping that data into something like a Spark Streaming cluster that you've also set up on EC2. Since Kinesis lives in AWS, that would be a very quick and efficient way of getting data from an EC2-based cluster of web servers to an EC2-based cluster of Spark Streaming hosts. So if you are an AWS user, this is definitely worth understanding. The good news is it's a lot like Kafka. Its architecture is pretty much identical. It's just in AWS. So if you want something like Kafka in AWS, Kinesis is definitely worth checking out. Architecture looks a lot like Kafka. So basically you can consume information from anywhere you want. Obviously, if it's coming from an EC2 instance that's also sitting on the AWS network, that's going to get to Kinesis really quickly. And then we have Kinesis Stream itself, which runs on multiple shards potentially. This is just like the brokers in Kafka. And that will basically consume all of these data, these messages that are being published by these hosts, and pump them out to whoever's subscribing to them on these EC2 instances, which might be running Spark Streaming. And from there, your Spark Streaming job can do whatever you want with it. Output it to Amazon S3, DynamoDB, Redshift. These are all Amazon storage technologies. And obviously, if you want low latency and all the benefits of AWS's scalability, you would want to use all of the different AWS components that you can. Okay, so moving on. Using it's actually very simple. The hardest part is actually just getting all the dependencies nailed down. So if you're using something like SBT, which I'll show you, a little bit later in the course, or Maven to manage the dependencies of your Spark Streaming project, it's a little bit easier to manage. But if you're going to be running this within the IDE like we're doing here, there's this huge list of dependencies that you have to bring in. So unlike with Flume and Kafka, there's not a self-contained jar file that you can download that has everything you need for Kinesis integration with Spark Streaming. You have to get the Kinesis package and all the things that Kinesis depends on. So we'll take a look at that in a minute. Another thing to note is that this is actually not using the standard GNU license. It's subject to the Amazon license, which is also permissive, and you're probably already dealing with it if you're using AWS. But I just want to call that out there, that the licensing terms of this Spark Streaming integration code for Kinesis is subject to a license you might not have seen before. So make sure your lawyers are happy with it. From there, though, the code itself is actually very straightforward. You just call create stream using Kinesis utils, and as they say, Bob's your uncle. Off you go from that point. So let's look at some actual code and see how it works. So before we actually look at some Kinesis integration code with Spark Streaming, I do want to call out the dependencies that you have when you bring in Kinesis into a Spark Streaming project. Again, if you're using a dependency management tool like SBT or Maven, it's less of a hassle, but it's kind of a chore to get this actually compiling. I had to download and install the Kinesis client package from Amazon, Spark Streaming Kinesis ASL, Spark Streaming Kinesis ASL assembly, and those in turn had dependencies on the Guava library and the JSR 166E library. So it took a little bit of time to sort all that out. So just be aware that you have several jars that you need to import into your project to actually get some Kinesis code compiling. And with that, let's look at the code itself. So if we look at our Kinesis example here, if you do want to learn more about setting up Kinesis and integrating it with Spark Streaming, there's a link here that will talk about this in much more detail. But once you have everything set up, it's actually quite straightforward. You just call kinesisutils.createStream, and you pass in, your streaming context that you have, your application name, your stream name that you're listening to, and basically the region that you're going to be working within, and the Kinesis endpoint that you can get from your account. And the rest is pretty much boilerplate, 2-second duration, and get the latest information no matter what. And that's all you need. At that point, you can use this to just take this byte array that you get back from the Kinesis stream and convert that to a string if what you're receiving is string data. And at that point, you have a D stream of strings. And from there, we can treat it like any other D stream of strings. In this case, it's just the same old example we've been using to count up the top URLs of a stream of Apache access log data. But the Kinesis specific bits are just these 2 lines of code. So again, very easy from the coding side once you have your Kinesis cluster all set up. And if you do want more depth, you can check out this link at the top here. But that's really all there is to it. All right, that's Kinesis integration with Spark Streaming. Let's move on. All right, we've talked about integrating Spark Streaming with Kafka, with Kinesis, with Flume, with just listening to a TCP port. But what if you have some wacky system that you need to integrate into that isn't any of the above, that doesn't have any existing library? Well, you're not out of luck. You can just implement your own custom receiver in Spark Streaming if you have to. So all you need to do is create a subclass of Spark Streaming's receiver class. And you can actually receive data from whatever you want that way if you can just write the code to accept it somehow. All you need to do is implement 3 methods in that class. On start, what happens when it starts, the receiver starts up. On stop, what happens when it shuts down. And a receive method that just sits there and receives data continuously. And what you do is you create your D stream from that receiver class using ssc.receiverStream on your Spark Streaming class. And you can just pass in a new instance of your custom receiver when you're doing that to create a D stream using a custom receiver class. So, that part of it's pretty straightforward, but of course, writing a robust receiver is not a small task. You need to make sure that it's going to keep receiving data until it's stopped. And if there's some sort of an error that happens, it's going to be up to your code to detect that error and restart the stream if needed. Otherwise, you can lose data, or even worse, your Spark Streaming job could just stop working entirely, which would be a very bad thing. But let's take a look at some code. It's not quite as bad as it sounds. We're going to take a look at some code that actually implements our own little TCP socket listener using a custom receiver, and you'll see it's not all that bad. So let's go and see a custom receiver in action. You can actually run this yourself. You have everything you need for this one. So if you are so inclined, go to the resources for this lecture and download the custom receiver example Scala class to wherever you download your stuff. And we'll go ahead and open up the Spark IDE, Eclipse. and import that into our project. So go ahead and hit pause if you need to get caught up here. Alright, so I'm gonna go to open up my Spark Streaming examples and go to my package here, com.sundogsoftware.sparkstreaming. Right click, import from the file system. I will browse to my downloads folder and select custom receiver example.scala. So let's open that up and take a look. So this example is basically going to do the same thing we did before, where we keep track of the most requested URLs from a stream of Apache access log data. The difference being that instead of just listening to a streaming socket, we're going to create our own custom receiver instead to listen to that information on port 7777. So how does this work? Well, all we really need to do is create this subclass of the receiver class in Spark Streaming. So nothing too special going on, but we imported the receiver class explicitly up here, as well as some Java stuff we need to actually deal with sockets directly. So again, we're kind of like relying on the underlying JVM to give us some of the functionality we need to deal with some low-level network stuff here. And I don't want to get it too much into the details of that, but basically what we're doing here is when we get called onStart in our custom receiver class, we're going to kick off a thread that just sits there and waits for stuff to come in, receives data. And then when onStop is called, nothing really happens. You know, we don't have anything that we have to explicitly shut down. So all we do is we define this receive function that actually does the heavy lifting. So this creates our socket, connects to it, creates a buffered reader from Java that listens to a stream coming from that socket in UTF-8 format and just sits there spinning until it is stopped explicitly reading in lines, and when it's done it closes. So has a couple of exception handles here. I don't want to get again into too much of the details of how to write Java networking code, but the important point here is that we have written a simple custom receiver that overrides the onStart and onStop methods of the base receiver class, where onStart kicks off a new thread that just runs this receive function forever until it's stopped. Okay, so now that we have this implementation of receiver that we want to use, all we have to do after setting up our standard streaming context is call receiver stream on our streaming context, and we instantiate a new custom receiver object that we create using our host and port name that we want to listen on. So we're saying we want to listen on localhost on port 7777. You can see here that just gets passed in as parameters to our receiver, which then in turn get passed on to the host and port used to create the socket. So that's pretty much all there is to it. At that point, you basically have a receiver input D stream, just like you would if you actually connected to a socket stream, and it's all treated the same from there. So let's go ahead and see if this works. Let's kick this off. Go to Run Configurations, create a new one. We'll call it Custom Receiver Example. And the main class will be com.sundogsoftware.sparkstreaming.custom receiver example. So let's kick it off. All right, so far so good. It's sitting there listening and failing to connect because I haven't kicked anything off yet to broadcast on port 7777. So let's take care of that next. Open up a command prompt and go to wherever you downloaded the access log and ncat utility previously. And we will type in ncat-kl7777 to output on 7777 the access log.txt file. Bam. And let's see if that works. It did. Data is streaming away through our custom receiver. So there you have it, a custom receiver in action in Spark Streaming. So obviously you could re-implement that receive method to do whatever the heck you want. If you have some custom proprietary system that you need to listen to in some obscure way, that's how you go about doing it. All right, let's hit terminate when we're done and stop ncat, and we're back to normal. All right, that's your custom receiver. So we've talked a lot about receivers and how to integrate with receivers in Spark Streaming. So let's talk about integrating with different output formats as well. We'll do that next. So we've talked a lot about integrating Spark Streaming with different receivers, different input sources, but let's talk about output sources too. So a very popular choice for an output source might be Cassandra. Cassandra is what they call a NoSQL database, where it's basically based around key value data, where you can put whatever structure you want in those values embedded within it, but fundamentally you're looking things up by a given key that represents an index that you've thought about ahead of time. So the idea with a NoSQL database like Cassandra is that you've thought ahead of time about the queries that you're going to be performing at high scale on this data, and you've actually structured a set of tables with those queries in mind, with the specific keys that you need to very quickly look up the information that your application needs. So, rather than a big monstrous Oracle database that has a bunch of relational tables, NoSQL actually flattens that down as much as possible so that everything is keyed off of what your application actually needs to look things up by. The advantage of this is that it's a lot simpler, which makes it more robust, and also makes it easy to scale. So if I just partition things based on those keys, I have a very straightforward way of partitioning the distribution of that storage across multiple hosts on a cluster. So not only is an approach like Cassandra very robust, it's also horizontally scalable. I can just add more servers to store more and more data and handle more and more traffic. Another good thing is that I can actually replicate that data easily too. So if I send data for a given key to more than one host, I have some redundancy built in as well. So that's why Cassandra is so popular. It's been around a long time, and it's well, as far as technology goes, it's been around a long time, and it's stood the test of time quite nicely. So in Spark Streaming, you can transform your raw input data into key value RDDs. So these are just tuples that we've seen before, where the first element of the tuple is the key and the second element is the value. And that value itself could be another tuple for all we know that has some sort of structured data within it. So this is very easy with Cassandra, because if you have a key value RDD, which is something Spark tends to produce naturally for you as you're writing Spark code, it's pretty straightforward to take that and dump it into a Cassandra database. So all you need to do is get the Spark Cassandra connector package from DataStax, I think produces that. If you Google that, you can find it. Get the jar file, add that to your project, and you just need to inject into your Spark conf this configuration that you use to create your Spark context, a little setting for Spark Cassandra connection host that just gives it the address of your Cassandra host that you want to talk to. And from that point, all you have to do is call save to Cassandra on a key value RDD, and it's just that simple. So let's do it. Let's see it in action. So I actually have a Cassandra database set up on my Windows system here. Just follow along with me here and watch me do it. Okay, so let's see some Spark Streaming and Cassandra integration in action. So, things that are different here. I'm importing the com.datastax.spark.connector package here that I installed as the external jar file to this project, and that gives me the library I need to integrate Spark Streaming with Cassandra databases. So first thing we have to do is configure things such as Spark Streaming knows how to talk to Cassandra. So I'm actually running Cassandra on my Windows box here. So I'm just using the local host port 127.0.0.1 and setting that to the spark.cassandra.connection.host property here as part of my Spark conf. And I'm also going to explicitly set a master of running locally on all of my cores and an app name. So this is a little bit different. We usually just do that as parameters to the constructor of the streaming context, but another form, if you have a more complicated configuration like this, is to set up a separate Spark conf object and then pass that into the constructor of your streaming context. So with this, we're setting up a streaming context with that configuration, and this time we're going to do a batch size of 10 seconds just to be different. Now from here on, we're just going to use the same old code from before, where we're going to listen to a socket on port 9999 that contains Apache access log lines, and we're going to apply a regular expression to those to extract fields from them. So just like in our previous examples, we're going to extract a bunch of stuff out of each access log line. In particular, we're going to be interested in the IP address, the URL request, the status code, and the user agent from each line. And we're going to suck that out and put it into a tuple. So this is going to be basically our values that we're storing in Cassandra. And since we're actually going to key this off of IP address, we're only going to end up with a unique entry per IP. So we're just going to keep on overriding each entry as we get new URLs from an IP address. Don't worry about it. This isn't a real example, but in the real world, you might do something a little bit more interesting than that. But I just want to show that we can actually extract this information from a real Apache access log and store it in a real Cassandra database. So once we've actually applied that regular expression, extracted the fields we want, and constructed a tuple of the information that we want to store somewhere, we can then hand that off to Cassandra. So to do that, we're going to take our request D stream that contains these tuples of information, and we're going to call for each RDD to access the underlying RDDs on each RDD within the D stream as it comes in for each batch. So I'm going to cache that RDD because I'm actually going to do a couple of things to it. One, I'm going to print out the count, how many items are in that RDD, just so I can see something happening in this script when I run it. And then I'm going to call save to Cassandra on that RDD. And what I'm going to do here is say I'm going to save it into the Frank key space that I created earlier under a table called log test. And I'm going to basically map the tuples, the information in these tuples, to these columns in Cassandra. So what this syntax says is that I want to take the first item in the tuple and map it to the IP column. Take the URL, call that URL, status, and then user agent, okay? And that's all there is to it. So that's Cassandra integration in a nutshell. Pretty simple stuff. Let's see if it actually works. So let's go ahead and kick this script off after we start off our usual NCAT job to actually broadcast access logs on port 9999. And let's start this script. And every 10 seconds we should get a batch and something should happen. I've already started Cassandra. There we go. So sure enough, we're writing data to Cassandra as we speak successfully. Pretty cool stuff. Let's wait for another batch 10 seconds later. Awesome. So let's go ahead and terminate this and terminate NCAT. And if we go to Cassandra itself in the Dev Center here, we can actually issue a query to dump everything from that log test table that we've been dumping stuff into. And sure enough, you can see there's real data in here. Actual IPs and statuses and URLs and user agents. So it actually worked. We successfully extracted information from Apache logs being consumed on a socket and output it directly to Cassandra. And that Cassandra host could have been running anywhere. It didn't have to be on my local computer, right? And it could be representing an entire cluster of Cassandra servers. So pretty awesome stuff. More scalability in action. So that is how you integrate Spark streaming with Cassandra. It's actually quite straightforward. Awesome stuff. Let's keep going. Let's start introducing some more advanced examples in Spark streaming. So let's talk about stateful data. And we're going to use an example of actually maintaining state across sessions in a weblog here to illustrate it. So if you need to maintain some sort of state while data is streaming in, maybe you're keeping some running totals, or in our example, we're going to be maintaining the state of a session as an individual IP clicks through a website. You can do that with Spark streaming. You don't have to just discard the data as soon as you get it or write it out or whatever you want to do. You can actually keep track of stuff as you go. And that's what map with state does. It's actually a relatively new feature in Spark streaming. There used to be a different way to do it that was less efficient, but the way we do it now is with the map with state function on your D stream. And the way that works is you just provide it with a function basically that takes in the incoming data as it streams in and updates some sort of state object of your choosing as time goes on. So syntactically, it takes what we call a state spec as a parameter, and that state spec is just something you create with a given function that processes and updates your state. So for example, you could say your state spec is a state spec that uses a function that we call track state func. That could be named anything you want. And you can also specify it with a timeout value. So in this example, we're saying I want my state to only have up to 30 minutes worth of information in it. So for example, if you're maintaining web sessions and you wanted your sessions to expire after 30 minutes, a 30-minute timeout might be appropriate. And otherwise, it will just pass information into your track state func that you write, and that function can maintain some state object that you define. There are other options you can do when you're creating your state spec to actually specify a specific number of partitions or some initial state that you want to start off with, or even a custom partitioner if you need to, but I'm not going to get into that now. That's really more for specific implementations and problems that you might have. So let's take a look at what that track state func is responsible for exactly. So the first thing we need to do is define an object that defines a state that we care about. So remember case classes when we were talking about SQL and Spark SQL integration. We used a case class to define very compactly a record in our SQL database. And we can use the same trick for very compactly defining a new type that represents the state that we want to track in our stateful processing. So in this example here, we're creating a case class called session data, and it's going to include a long value that's named session length and a list of strings that we're calling clickstream. So in our example, the stateful session data that we want to maintain for a given IP is going to be the length of that session and the actual list of URLs that session clicked on. And obviously you could do more complex stuff in the real world if you wanted to. So let's take a look at an actual track state function actually fully fleshed out here and see what's going on. So the input parameters that you're going to receive from the framework are the timestamp of the batch that's coming into it, and then your key and value that's coming in from the stream. So in our case, the key is going to be an IP address and our value is going to be a URL. And the state object that we're keeping track of is this session data class wrapped in a state object so that we can actually use it uniformly. So the syntax here is just saying I'm creating a state object that contains a session data object that I defined. And it's going to return on its output the new key and state that you have. So for example, we can take a look at our previous state that we had before this data came in using state.getOption.getOrElse. We'll talk more about what that does in the next slide, but that will just receive the previous session data. And if there wasn't a session previous already, we're going to start off with an empty one that has a session length of 0 and a new empty list. Then we create our new state, which is constructing a new session data object just based on the previous session length plus 1 because we've added 1 to it. And using our previous state's clickstream, adding whatever this new URL is that just came in. And we're going to cap that at most 10, to be at most 10 URLs just to prevent that from growing unbounded. Then we just call update on our state object to update the state using this new information. And we return this sum class that we'll talk about in the next slide that returns the new state and the new key. So we saw some new syntax there. We saw options, we saw sum. What does all that mean? So this is actually a new concept we haven't encountered before in Scala. It's something that's in Scala called a monadic collection. So the option class is an example of a monadic collection, meaning it's a collection object that contains only one thing. Seems a little bit silly to have a collection that can only contain one thing, but hey, that's Scala for you. It can be weird sometimes. Of course, that one thing can contain multiple stuff jammed into one tuple, but this is really just a way that Scala handles elegantly empty or null values. So if you have some sort of function that can potentially return nothing, have a null result, it's not like in C or some other language where you can test against null. Instead, the way that it works in Scala is you create an option that can either be a sum object, which means that it contains some sort of valid data, or it can be a none object that means that it contains nothing at all. And that way, when you receive an option object back from some function, you can use the get or else function on it to figure out, well, is this a sum thing that I can actually extract data on? If so, return that value. But if it's a none, then I'm going to use my else condition there to actually have some fallback case that happens if there is a none value there. It'll make more sense when we look at the code again, so let's just go ahead and look at that code and give it a run. All right, let's maintain some state in Spark Streaming. So go ahead and download the sessionizer.scala file from the resources for this lecture and save it wherever you save your stuff. Hit pause and continue when you're ready. When you are ready, go ahead and right-click on our package here like we have all along and import from the file system wherever you downloaded that to. So in my case, that will be, not videos, C downloads. And in here we should have the sessionizer.scala script. Let's take a look at it. Alrighty, so what's going on here? Open that up. Nothing too unusual up here for the imports and whatnot. The only thing that we're doing different is that we're introducing this new track state func that we're using to maintain our session state. So like we talked about in the slides, we're defining this case class to define a data type for the stateful information that we want to keep track of for a given IP address or whatever key you happen to choose. So in our case, we're creating a session data class that has a long value that's called session length and a list of strings that is a clickstream. So basically a session in this example contains of a session length number and a list of the URLs that session visited. Got it? All right, and let's take another look at our track state func. This is the function we're actually using to keep track of the state as new data flows in. And I think it's worth looking at again now that we know what monadic collections in the option class does a little bit better. So again, the inputs are the batch time coming in, and then our key and value that's coming in from the stream. So in our case, the key represents an IP address that we're identifying our session by, and the value is the URL that was visited by that IP address. So, at some point later on, you'll see that we're creating a stream of key value RDDs, where the keys are IPs and the values are URLs, and that's getting passed into our track state func. And we also have the state object itself, which we are specifying to be of type session data. And what we return from this state function is an option class, which again, remember, can be a sum or a none, depending on whether or not you have valid data to return or not. That contains the new key, which is going to be the IP address still, and the new state, which is our new session data. So within this, first thing we do is we grab the previous state, which was passed in as a parameter to us. So that state object that was passed in is our previous state that we're starting from. And we can use get or else on it because it is an option, just like we talked about. So if that contains sum, it actually contains data, that will just get it. But if it's a none, if this is the first time that we've actually encountered this state, we're going to have some empty data to deal with, and we need to handle that first case. So in the case that this stream is just starting, we'll instead produce a new state that consists of 0 for the session length and an empty list for the click stream. Okay, makes sense so far? So we're just getting the previous state if it exists. If it doesn't exist, we create a new, fresh, empty state. Now we need to create the new state based on that previous state. So we're going to create a new session data state that is taking the previous session length and adding 1 to it, and taking the previous list of URLs visited, the previous click stream, and using this little weird syntax to append a value to it. That's going to be the new URL, which itself is also an option, so we can use get or else to retrieve that URL that was passed in, and if there was an empty value for some reason, we would just use the string empty instead as a placeholder. I'm also calling take 10 on this just to cap the length of that clickstream data to 10 different items, just to keep it from blowing up out of control. Next, we need to update our state object with that new state object, and we can return sum with the IP new state, the new key value result of our state value. Moving on, so let's go to the meat of this script itself. Nothing too out of the ordinary here. We're just setting up a streaming context like we do normally, and our usual access log regex pattern. All right, but here's where the action starts happening. So we're setting up our state spec object, and we're defining it as using the track state func method that we defined above. And we're saying that we're going to have a 30-minute timeout on this state. So no session can last more than 30 minutes in this example. Next, as before, nothing special here. We're just going to set up a socket text stream to listen to log data on port 9999 like we've done before, and extract IPs and URLs out of it this time based on that regular expression. So we are going to extract a new tuple, a new key value pair of IP and URL. And that is going into a D stream called requests, which consists of these tuples of 2 strings, the first value being the string, the key value of the IP, and the value being the URL visited. So now, here's where the state stuff happens. Got it? So we have requests, which is our D stream of key value pairs that we care about tracking a state across, and we're calling map with state using our state spec object. So this is what tells Spark Streaming, as this request stream, D stream, keeps coming through, apply this state spec to it to keep track of the state that we care about. Okay? And what we get back is a map with state D stream at that point. What you can do at this point is call state snapshots on it if you actually want to get a look at what's inside that state at any given time. And once you have that state snapshot stream, we can iterate through all the RDDs within it and do stuff with it. So in this example, we're actually doing a Spark SQL example here where we're actually going to query the results of that as a data frame and see what's inside that state as we go. So let's go ahead and kick it off and see what happens. Let's start by kicking off our stream of log information like we do normally. So we'll go to where you download your stuff, to wherever you put ncat and the access log, and type in ncat. Again, if you're on Linux, that's nc instead. -kl 9999 is the port that we're going to work with, and we're going to pipe in access log.txt. So let's kick this off and see what happens. So run configurations. We will call this sessionizer. And the main class is com.sundog software. Someday I'll learn how to type. Spark streaming sessionizer. Like that. Off we go. Hey, check it out, it works. So we have successfully dumped our state as we go into this little Spark SQL table. So you can see here, let's just terminate this so we can take a closer look. We are mapping IP addresses to session lengths, and we are keeping track of their clickstream history. So there you have it. Pretty cool stuff. Some actual session state from our web logs. Looks like this guy's probably one of our attackers here, huh? Coming from 195. We should look up where that is. Someone's hitting us 1724 times there and trying to hit our RSS feeds, it looks like. Kind of interesting. But yeah, actual session information there using stateful information in Spark streaming. Cool stuff. So if you need to stare at that source code a little bit more, let it make more sense. That's the cool thing. One thing I want to point out too is if you do try to use this code outside of this example, keep in mind that we are using this SQL context singleton class here. That was actually defined in our log SQL class. So if you need to use this code outside of this particular project, you will need to go grab that class out of there in order to use it. But hey, that's it. Stateful state information in Spark streaming. Very useful stuff. Let's keep on trucking on. So this is a pretty important concept to get, this whole thing about tracking state through Spark streaming. So I want you to get your hands dirty, start playing with that code, get more familiar with it, get more comfortable with it. So as a suggestion, I want you to go in there and modify it a little bit. And in addition to keeping track of the session length and the actual list of URLs visited for each IP address, also keep track of the total number of success error codes or success status codes and error status codes encountered for each session as you go. So you can probably lift a little bit of code from a previous example to make that a little bit easier, but extend that state object that we made and actually add in those two counters too, and query that in that Spark SQL toward the end too and print that out. So do that and you should get a little bit more familiar in how this is all working and get more comfortable with tracking state in Spark streaming. Good luck with that. When you're done, we'll move forward and start to learn about streaming machine learning algorithms. Fun stuff. What's up next? All right, we're going to get into some really fancy stuff now, actually combining Spark streaming with machine learning and using the MLlib component of Spark together with Spark streaming to do some interesting stuff. And we're going to start with an algorithm called k-means clustering. So just to step back a minute though, Spark has an MLlib library that can be used for various machine learning algorithms. And the potential of actually updating a machine learning model in real time as new data is received is pretty exciting. Now today there's only a couple of things it can actually do in that manner. We'll go through those right now, but it's early days, but the potential is pretty exciting. You know, you can imagine sort of a model that learns over time in real time, just like a human brain does, given more and more input, you know, as it happens. So that's kind of a little bit scary, honestly. We'll start with k-means clustering, and this is definitely not a scary algorithm. It's pretty simple in what it does, but this is one of the things we can do today with Spark streaming. So the idea of k-means clustering is what it sounds like, clustering data. So let's say, it's best to think about it in terms of examples. So say you have some data that can be broken up into a graph on X and Y axis, kind of like this picture down here. Let's imagine, for example, that these squares all represents locations where millionaires live or something. Now with k-means clustering, we could say, let's assume that there are 3 distinct neighborhoods. 3 would be the value of k in this example. And I want to try to cluster these individual millionaires into the neighborhoods that they live in. So the k-means clustering algorithm could actually take a look at that raw data of just where people live and try to divide that up in the most optimal way in which 3 different clusters emerge. So if I know that there's 3 neighborhoods, I can actually build a model of where those neighborhoods are centered. And I can then later use that same information to predict, given a new location, which neighborhood that new millionaire is assigned to. Another example, genres of music perhaps. You know, let's say I'm graphing, I don't know, maybe tempo of music versus its dynamic range or something like that. And I'm plotting those points on a graph like this. Maybe I could choose a k of, you know, several genres of music and see if I can naturally cluster different songs into their genre just based on those 2 dimensions of information. And you don't have to stop with 2 dimensions either. It's just easier to visualize that. So let's see how that works. Oh, one other thing. This is what we call unsupervised learning. So a little bit of bonus lecture here on machine learning in general. Unsupervised learning means that we aren't training this model given a set of known correct values. All we're doing is throwing raw data at it, and we're trying to extract meaning from it without any prior knowledge. So yeah, sounds like fancy stuff. Your head's probably spinning a little bit if you've never encountered machine learning before, but don't worry about it. It's actually pretty simple. The way it works under the hood is, we start with this graph of, this graph of information of raw data, and we just randomly pick a number of mean center points for each cluster. That's where the k-means term comes from. And then we just assign every individual data point to the center point that is closest to. And then we recompute those center points based on the actual values that were assigned to that cluster, and we keep iterating on that until things start to converge to the same locations for those centroids. Makes more sense with a picture. So let's imagine again that these squares represent individual millionaires that live somewhere, going back to our original example. What we do is we start off by picking 3 random locations that we're going to say are the centers of 3 neighborhoods. And that's what these circles represent. So if we chose a k value of 3, that means we're going to attempt to cluster this information into 3 different clusters. So the first time we go through, all we do is we take each individual millionaire and assign it to the cluster centroid that is closest to, and it ends up looking like that. So this one here is actually closest to the red one. These guys were closer to green, and these guys were closer to the blue center that we picked at random. What we do next is we adjust those centroids to be the actual mean value of those different points that we assigned them to. So everything gets shifted over a little bit. For example, this cluster only had one thing in it, so the center ends up being where that one thing is. This guy moves down a little bit, this guy moves up a little bit, and then we recompute who's closest to each centroid. And you can see that our red neighborhood actually picked up a new guy, and our green neighborhood actually lost a couple. So we keep doing this over and over and over again until things start to converge. And when we're done, we should end up with a model that is a reasonable approximation of the actual neighborhoods that these guys live in. And again, you can extend that to any wide variety of problems. So in our example, we're actually going to try to segregate people based on their age and income into different, stereotypes. They don't necessarily have to mean anything, but we'll see if people tend to cluster in terms of age and income. Anyway, making this real, how does this all work within MLlib and Spark? So MLlib has a general concept of a model, where k-means clustering is a machine learning model. And models need to be trained, meaning you feed it data to learn from, and then they need to be tested, meaning that you give it new unknown data points that you then try to classify using the model that you built. So to train the data on our data points that we have, where we don't really know what the clusters are or what they mean ahead of time, you call train on, and you feed it a bunch of what we call vector objects in MLlib, where vectors are just, raw information, and we call that feature data. The latitude and longitude of where these millionaires live, for example, would be features. And then to actually get a prediction, we need to feed it what we call a labeled point. So this contains both the feature information that contains the data that we're trying to make a prediction from, and a label, which in this case would be the cluster that we want to assign to that new millionaire that we see. And to do that, we just call predict on values to actually try to make a prediction based on the model that we built with our training data previously. Translating it into code, if you want to make a streaming k-means model, it would look a little bit something like this, where you can actually just call new streaming k-means from the MLlib library. Set k, that's how many clusters we want to use, 5. And there's sort of an art and a science to selecting the right value of k, but I don't want to get into that in this lecture. I have a whole other course on data science if you want to learn more. A decay factor, just to make sure that old data doesn't keep piling up forever. You want to make sure that your model is more responsive to new data coming in. And set random center is just defines how many dimensions we're working with, basically. So if we're dealing with age and income, that would be 2 different features that we're dealing with in two axes that we need to work with there. So let's actually look at some code and run it, see how it works. All right, let's do some real-time k-means clustering in Spark Streaming. Three things you need to download for this lecture: the k-means test.txt file, the k-means train.txt file, and the, streaming k-means.scala file as well. So go download those three things from the resources for this lecture first, and when you're ready, we can continue. So let's take a look at the data that we're dealing with here first. So like I said, we need to first train our model given some set of data points. And to do that, we've defined this k-means train.txt data file. And what we're going to do is stream this into our application as sort of a continuous stream on a socket. And all this is some randomly generated clusters that I generated offline that's mapping incomes to ages. So the first column here is an individual's income followed by their age in years. And this is all fake data, so don't read too much into it. But MLlib will expect this in a specific format. So this is what they call vector format, where we have these brackets with comma-separated lists of features. Okay, so in MLlib terminology, each line is a vector that contains two features, one feature being the income and another feature being the age. And we're just going to stream this data in continuously as our job runs. Now, the other thing we need to do is be able to make predictions based on the model that is created by the k-means clustering model. And to do that, we're going to use this k-means test data set that actually contains the same data, but what it contains is the actual cluster ID that we assigned originally when we were generating the data. So this will be an interesting way to sort of compare our known results versus what we get. Now, there's no intrinsic meaning to these cluster IDs, so all that matters is that we have somewhat consistent results, not that the actual numbers match up. So this is what we call labeled points in MLlib. Basically, we have this parenthesis where the first entry is the label, and in this case, the label we're trying to assign is a cluster identifier, followed by our vector data, the actual feature data itself, which is age and income. So as we stream this data into our application, we're going to be saying, okay, Mr. Spark Streaming K-means application, I want you to take all these people that are coming in that have some known income and age, and I want you to tell me what cluster they should belong to based on the training data that we sent in previously. And finally, we have the script itself, so let's go ahead and import that and actually run it. So as usual, right-click, import, file system, browse, wherever you download stuff, and we want streaming k-means. Open that guy up and take a look. You'll see the code is actually quite simple. What we're going to do here is basically set up everything like we do as normal, but we're going to set up two socket text streams, one to receive our training data over time, so the data that we're actually using to create our k-means clustering model, and that's going to listen on port 9999 for our training data. And at the same time, we're going to have another stream that listens on port 7777. And this is going to sit there waiting for new people to come in that we want to assign a cluster to based on the model we've been building up at the same time on this training data. So these two things can happen concurrently. As more and more training data gets received by the algorithm, it can build up and perfect its clustering model. And while that's happening, we can send in new testing data to try to assign new people to clusters that we haven't seen before. Okay? So from there, all we have to do is we want to cache that and parse out these vectors and parse out these labels to actually get D streams of labeled points and D streams of training data. So all that does is parse in the raw text input from those streams and convert it into the vector and labeled point data types that MLlib expects. Okay, nothing too fancy going on there. And just to see some output as we receive our training data, we'll print out the top 10 results that keep coming in as we go. And as that training data is received, we will create this new streaming k-means model that is trained on that training data stream. So that D stream gets associated with our streaming k-means model, and it will just keep getting better and better the more data that we send into it over time. And at the same time, we'll use our test data stream and map that into our features and our labels and call predict on values and print out those results. So we'll see as a result the actual new features that get assigned to these new values, to these new, did I say that right? The new labels that will be assigned to this new feature data. Okay, so let's just see it in action and it will make more sense. Let's go ahead and open up a command prompt, go to where we download our stuff. All right, so we should have ncat and that train data and that test data. So remember, ncat.kl, we were going to put the training data on port 9999. So let's do that. K-means train.txt. And then I'm going to open up another window. And this is going to be on port 777, where I'm going to put the test data. And now I can kick off my job after I create a run configuration for it. We'll call this one streaming k-means com.sun.software.spark streaming k-means. And let's see what happens. Hey, check it out. It actually worked. Let's do that again. That happened pretty quickly. So let's do it one step at a time. Get a little bit of a better feel as to what's going on. All right, so I've lost both of my connections here. Let's restart. All right, let's start by sending it some training data. Oh, there it was. So you see back there, it actually received that training data, so we printed that out. And now let's send it the test data, now that it's been able to build up that model. And there's our actual results. Cool. So if we scroll back here, we can see what happened a little bit better. Here's where we actually received our training data. And you can see all the individual incomes and ages coming in that we're building our k-means clustering model on. And then we sent in our test data on the other socket, and it produced these assignments. And what it's actually doing here is printing out the label that was in our test data and the actual label that it assigned. And you can see it's consistent, so it actually worked. Now, like I said, the actual cluster number doesn't matter in this case. You know, that's irrelevant. There's no real meaning to that cluster identifier. But what's important is that it's consistent. So while when we were generating the data, we kind of knew the right cluster for these points was cluster 0, our algorithm assigned it to cluster number 3 instead. That's not important, but it did do it inconsistently. So it seems like our cluster 3 is the same as our cluster 0 is the same as their cluster 3. So hey, it worked. You know, if you're new to machine learning and data science, a lot of this probably went over your head, and that's okay. You don't have to be a machine learning expert to use Spark Streaming. But if you are going to be using it within the context of machine learning, then this is definitely a useful trick to have up your sleeve. So there you have it. Streaming k-means clustering. Awesome stuff. Let's talk about streaming linear regression, another thing that Spark Streaming can do in cooperation with Spark's MLlib. So what is linear regression? Well, this is a pretty easy concept to understand. It's just a best fit line to some data, really. So if you have a set of observations, say, you know, people's weights to their heights, probably follows kind of a linear relationship there. If you were to actually measure a bunch of weights and heights of a bunch of people and plot it like this, you could probably find a straight line that fits it pretty well. And what linear regression does is try to find the line that has the least amount of error overall between all the data points that you have. And we'll talk about that a little bit more in a little bit. I don't know why they call it regression. Well, actually, one student actually looked it up and told me once there's some historical reason, but don't get hung up on the term regression. Think of it more as just a best fit line to some data. And you can use that for predictions, right? So if I go back here for a second, imagine that I see a new person where I only know their weight. You know, I could use that line to actually predict their height based on the model that I created with my linear regression line, okay? So say someone shows up who weighs 120 kilograms, I could extrapolate that line out to 120 and say, okay, that person probably is about 200 centimeters high or whatever it works out to. So that's the practical application of linear regression. You build a linear model based on some observed data, and you can use that linear model to predict values for new people you see. So in the terminology of MLlib, weight might be the feature that we're looking at, and height might be the label that we're trying to assign. So typically, the y-axis is what you're trying to predict, and the x-axis is what you know for incoming unknown data. How does it work? Well, the simplest way of doing linear regression uses a technique called least squares, where it just tries to minimize the squared error between each individual data point and the line that we create. And if you want to get into the mathematics of how that works, you can read the rest of this slide, but it's not really that relevant to Spark streaming, so you can go into that if you're so inclined, but I'm just going to move on, mostly because Spark streaming's implementation of linear regression doesn't even use that simple model. It uses something more complex called stochastic gradient descent. Wow, fancy term. And it is fancy, but you don't have to understand how it works. Just understand that it's an algorithm that's a little bit more robust when it comes to higher dimensional data. And that's what Spark streaming's linear regression is actually doing. So more importantly, how do you actually use it? Pretty simple. Basically, you set up a new model using streaming linear regression with SGD. SGD is stochastic gradient descent. And you call set initial weights to just make sure that it's starting off with an initial set of zeroed out values for the number of features that you have, okay? And then, as before, you train the model and then you test it to get predictions out of it. The difference being that when you train this model, you're not giving it vector data, you're actually giving it labeled point objects. And in this case, the label is what you're trying to predict in the end, what's normally on your y-axis, and the feature would be what's on your x-axis of that graph. And obviously, you can have more than 2 dimensions if you want as well. So, just thinking in terms of 2 dimensions, as it's easier to keep your head wrapped around that, you would train your model with a bunch of known x, y points. And then if you want to predict new y values for a given x, you can use a prediction on that model to do that. So in both cases, we're using labeled points this time. Now, there are some gotchas with streaming linear regression in Spark streaming. It has some frustrating limitations. So first of all, the algorithm doesn't handle what we call feature scaling well. It makes the assumption that your input data follows something that looks similar to a normal distribution, where everything is pretty much centered around 0 and, plus or minus 1 or 2, okay? It has this bell curve is the assumption. And if your data does not fit that assumption, then you need to scale it down to actually look as much like that as you can, and then scale up the results when you're done to get back into the proper space that you started in. So this is a real problem. For the example I'm going to show for this lecture, I was trying to show you a model that tried to predict the amount people spend based on the page speed of the page that they were encountering on a website. So the assumption is that there is some linear model between how fast a website is and how much money people spend on that website. But because seconds and dollars don't really map well to this standard normal distribution scale, I had to scale all those numbers down to actually fit within that range before I could get meaningful results. If I didn't, I got a bunch of nonsense out of the model where I had a bunch of invalid, not a number values coming out of it. And the only way around that was to scale it down to a range that the algorithm can handle better. So that is a pain that you just have to deal with this model. Hopefully it will get better over time. I would like to see the MLlib just handle that for you automatically. It also assumes that your y-intercept on your line is 0, which might not be the case. If you have reason to believe that your linear model does not intercept the y-axis at 0, you can actually call setIntercept true on model.algorithm to allow it to take that into account and actually give you a y-intercept that might not be 0. But the default is false. So by default, this code assumes that your linear model will go through the origin. Might not be the case, right? Anyway, let's try it out with all those caveats in place. So I've actually gotten fabricated some fake data for page speed and revenue, and I've scaled it all down to fit into a range that the algorithm can handle. So let's throw it in there and see if it works. All right, streaming linear regression in action. So download a couple of things for this lecture. One is the regression.txt file and the streaming regression.scala file. Okay, so get those down and continue when you're ready. Take a look at the regression.txt file. It contains these comma value separated rows. And like I said before, this was originally intended to represent page speeds on a website and the amount that people spent on that website. But because of the limitations of the SGD linear streaming model, I had to first offset and scale that data to make it look more like a normal distribution that's centered around 0 and doesn't range more than, a couple of units on either side. Otherwise, you get nonsensical results. So in the real world, I would have to take the output of what I'm about to write and then shift it and scale it back up to its original scale to get meaningful results out of it. So kind of an annoying little thing about linear regression with SGD. Anyway, we have our streaming regression Scala file, so let's add that to our project. Right-click, import, file system, browse, wherever you download your stuff, and streaming regression. Open that up, and here we have some code. So because this particular model is a supervised learning technique, we're actually going to use the labeled point structure for both the training and the testing data. So I can actually have that same regression.txt file double as both our training and test data set, just for the purpose of illustration here. Of course, you would never do that in the real world, but just showing you that it works. So nothing special. We're going to, again, listen to our training data on port 9999 and our testing data on 7777. So we're going to feed data into our linear regression model on port 9999, and that will build up our linear regression, build up our line that we're going to use to predict new values with. And then our testing data is going to be coming in on 7777 once we have our model built up, and we can use that to actually predict revenues from a given page speed. Okay, so we are going to use this labeled point.parse method to actually parse in that regressions.txt data, both into the training data and the test data streams. And notice that we're caching the training data because I'm doing more than one thing to it. I'm actually doing a print just to get some output and also, using it for the actual model itself. So that saves a little bit of time. And then we create our actual streaming linear regression with SGD model here with initial weights of one feature. So remember, we have two dimensions. One is considered the label, one is considered the feature. So we have one feature. If we had 3 dimensions, there would be 2 features and so on. And we kick off our model training on that training data stream. Okay. So at this point, training data contains a bunch of labeled points of page speeds and revenues. At the same time, we're listening to the test data stream, which is also receiving labeled points of basically known revenues and page speeds. And we're going to test if our model can actually predict whether or not those match up. Now, we can also just call predict on if all you have are the feature data itself. So if you don't actually have a set of known correct results that you're actually testing against, you can use predict on instead of predict on values and save yourself a little bit of trouble there. That way you don't need to use fake label data. So like before, let's kick it off and see what happens. So we'll start by training it on port 9999. So back to our, I never actually stopped it from last time. All right, so let's go to this window here, or open up a new one, as the case may be. And we're going to say ncat-kl9999, and this time we're going to pipe in regression.txt for our training data. We'll kick off our script, run configurations, streaming regression. com.sundogsoftware.sparkstreaming.streaming regression. And we should see that training data come in pretty quickly. There it is. And now that we have our training data all in, we lost our connection. That's all that those errors are about there. Save to ignore. We can now send in our test data and see if we can get a result out of it. So we'll ncat-kl7777, which is where we're sending our test data. And we're going to pipe in regression.txt to that as well. And see how well our linear model does. All right, I already did it. So let's go ahead and hit terminate. Take a look at the results. So basically we're looking at the predicted and actual results here. And they're not bad. Pretty good correlation there. There are formal ways of measuring how good it is, but just eyeballing the data, some results are closer than others, but overall, we have a pretty good match here. So, negative 2.54, negative 1.87, everything's in the right ballpark at least. So our model actually worked. Yay. And the beauty of it, again, is that I could just keep on sending in a continuous stream of training data and make that model better and better over time. And at the same time, I can send in a continuous stream of data that I want to predict and just do that in real time as well. And the whole system will just get better and better the more data it consumes. So streaming linear regression for you. Man, that's hard to say, but it's awesome stuff. So that's MLlib with Spark Streaming working together. Pretty cool stuff. So now we're going to talk about actually packaging up and deploying your application for Spark Streaming in the real world. So far we've only been running on the Spark IDE, and obviously you're not going to be running within the IDE if you're actually running a script in production. So how do you run these things for real? Well, it turns out inside the Spark bin folder there's a little command called Spark Submit, and that's what you normally use to run a Spark job, whether it's Spark Streaming or MLlib, whatever it is. Spark Submit is the script that will actually wrap everything that's needed to set up an environment to run Spark within, and make sure that everything's also set up to actually distribute that script out to a cluster if appropriate. So if you're actually going to run this in the real world, the first thing you need to do is make sure that your script doesn't have any references to your local file system in it. So in a lot of the scripts we've looked at, we've had checkpoint directories that point to our local C drive. Those would have to go, for example. Anything that actually references reading in a file directly from a local file system also would have to be modified. And remember, we just care about reliability and stability of these programs. So make sure you're actually reading data from some sort of distributed file system that itself is reliable in order to keep your script reliable. Maybe that's HDFS attached to the cluster that you're going to be running the script on in the end, or maybe it's Amazon's S3 service where you're storing stuff if you happen to be running on AWS for your final destination. Now, in order to do this, you need to package up your Scala project for Spark Streaming, or Spark in general, into a jar file. And remember, Scala runs on top of the JVM, so at the end of the day, all you need is a Java jar file that the JVM can actually execute, the actual Java bytecode. And the Spark Submit command can be used to just execute that outside of the IDE using that jar file that you produce. And if there are any dependencies that you have, for example, maybe you have an additional jar file for Kafka integration or something like that, you can pass that in on the command line as well to Spark Submit. So the general format here is spark-submit --class, and that will be the fully qualified name of the class object that contains your main function, just like we've been typing into the IDE when we're creating our run configurations. --jars, which will contain pass to any of the jar files that you depend on. And you can also pass in a --files parameter. So if you actually want some sort of small file that's distributed alongside your application, maybe it's a little small lookup information or something like that, you can do that too. And finally, the path to the actual jar file that contains your main class. So the jar file containing the code itself. So that's how it all works. Now, it's also possible to create a jar that is completely self-contained, and we'll talk about that coming up soon. But just to keep things simple for now, let's try this out. So let's go and take a look at our print tweets job that we started off with at the beginning of the course, and we'll actually run this using Spark Submit outside of the IDE. And this is what that command would end up looking like. So, for example, in this case, our main class name is com.sun.software.sparkstreaming.printtweets. We actually do have a dependency in this class on the Spark examples jar that comes as part of the Spark SDK, because that's where the Twitter streaming class lives. And finally, we specify the path to the jar file that contains this main class, which we're going to package up as clustertweets.jar. So let's go and actually do that and see it run. Okay, so actually packaging things up so you can run it outside of the IDE is something you're going to have to do pretty often in the real world. So I do encourage you to follow along with me here and see how we're doing it. So as an example, I'm going to set up a little project here that just has my original print tweets example here. That was the very first Spark streaming thing we did in this course that just listens to Twitter streams and prints them out to the screen. So let's go ahead and make a new project. Your entire project gets exported as a jar file. So in order to avoid all the extra dependencies and code that we don't need, I'm going to set up a fresh new project just for this exercise. So we'll go to new Scala project. We will call it print tweets. And go ahead and hit check next, make sure everything looks okay. I think we're in good shape. Hit finish. Okay, so now we're going to add in our actual package, which is going to be com.sundogsoftware.sparkstreaming. And from there, we're going to import our print tweets file. And you probably still have that in your downloads from the actually the second lecture that we did. If not, It is attached to this lecture again if you need it. Print tweets. Okay. Let's open that up. Now we do have a bunch of compile errors here because we didn't include all of the Spark dependencies into this project. So let's go take care of that just so I can make the IDE happy. We'll click on Properties for the project, go to Java Build Path. First thing we're going to do is change the Scala library to 2.10, which is what Spark expects right now. Go to Add External Jars under Libraries and select all of these standard Spark streaming libraries. So that would be all of these ones down here. Everything else is stuff that we added for the integration examples we did. Okay, and if we hit OK, things should be a little bit happier. Oh, I forgot my utilities class, so let's go take care of that too. Right, click on the project, import, file system, and utilities.scala is also needed. And now things should be happier. Yes, indeed, all my X's are gone. This project looks healthy. Just to double check, let's go ahead and run it. So let's go ahead and run this and make sure it works. We'll create a new run configuration for it. And we already have one named print tweet, so I need to call it something else. Let's call it cluster tweets, because this is intended to run on a cluster ultimately. Using the print tweets project, and the main class is com.sundogsoftware.sparkstreaming.printtweets. Let's make sure it runs. This always makes me nervous. I never know what people are going to be talking about out there. All right, I'm not seeing anything terribly offensive, and mostly languages I don't know, so who knows what they're saying actually. But anyway, it works. So go ahead and hit terminate there now that we're good. All right, so now we're actually going to package this up so I can run it outside of the IDE now that we're sure that it runs. So I'm going to go to my print tweets project here, right click and export. And I'm going to select a jar file. Under Java, jar file. And we don't care about any of this extra stuff over here. We just want the print tweets code itself. And compression is good. I think this is all good. So let's hit finish. Oh, and we need to select where you're going to save it to as well. So go ahead and change that if you want to. Cluster tweets.jar. All right. And we should have a jar file. Indeed we do. Awesome. So let's run this thing. Now, if you remember, the code actually looks up one directory to get that twitter.txt file. So I'm going to have to rearrange things a little bit here. If you actually look at the setup Twitter function, it goes up one directory and looks for twitter.txt from there. So I need to make sure that wherever I'm running Spark submit from is actually one directory below where twitter.txt lives. And I could change the code to work differently. That would probably make a little bit more sense in this case. But just for fun, let's go ahead and move that cluster tweets.jar file inside the print tweets folder so that that twitter.txt file is where it expects to be. All right, so now I can open up a command prompt in Windows and navigate to where I put that jar file. So in that case, that would be C Spark streaming course print tweets. And you can see here, there's my jar file. And now what I can do is a little something like this. So going back to my cheat sheet here, we're going to do the spark-submit --class, the class name --jars, and the Spark examples, and then the actual name of the cluster tweets jar file itself. So let's do Spark submit --class com.sundogsoftware.sparkstreaming.printtweets --jar jars, plural. And the one I need is C Spark lib. Change that to wherever you installed Spark if it's someplace different. Spark streaming, was it Spark streaming examples? Just Spark examples. Spark examples. Like that. And finally the name of the jar that we're running, which is cluster tweets.jar. And let's see if it works. Well, it's doing something. Hey, check it out. It actually works. So we are running our Spark streaming job outside of the IDE using the Spark submit script. Now, if you did not get this far, let me stop this before I get unlucky with what's going by. I'm just going to hit Control-C to stop it. So if you did not see this, there might be a problem with your path. So you need to make sure that the spark-submit command is actually in your path for Windows. You should have done that back in the setup instructions, but just in case you are seeing problems with says something like Spark submit could not be found, that's probably why. Go double check your path. Make sure that you have a Spark home properly set for your environment variables and that Spark home enclosed in %/bin is actually in your path for Windows. And with that, you should be seeing something along these lines. So hey, we have a self-contained jar file that we can actually run outside of the IDE. And this is how you would actually run a Spark streaming job in reality outside of an IDE. So very important skill, but we can take it to the next level and make it even more robust. So let's take a look at that next. Let's talk about packaging things up with SBT. So one problem that we had in our previous example of using Spark Submit was that we had this external dependency on that Spark Examples jar file. Now, what would happen if that wasn't installed on every machine in your cluster? It wouldn't work, right? And it's also kind of a pain in the butt to have to type in that --jars argument with every dependency that you might have. I mean, in a more complicated project, that might be a pretty long list of jar files, and you don't want to have to type that in on the command line every time. That's where SBT comes in. It's basically a system that can manage all of the dependencies in your Spark streaming or Spark project and bundle everything up into one self-contained jar file that has everything you need to run that program, all in one bundle of a jar file. And that makes it a lot easier to take that one jar file, deploy it to everything on your cluster, and run it in a way that is guaranteed to run on every machine. So it's kind of like Maven if you're used to the Java world. SBT is basically Maven for Scala. And like I said, it just manages all your dependencies for you. It would actually go out to the internet and download everything you need, and it will also go through the entire dependency tree. So if you remember the Amazon Kinesis library, for example, that itself had a bunch of dependencies of other jar files, and SBT can manage all that complexity for you. And we seem to be moving toward a world where more and more people depend on more and more dependencies, so this will become more and more of an important thing to figure out. Okay, so anyway, the first thing you want to do is go download SBT if you don't have it already from scala-sbt.org, and just download the package for your operating system and install it. And that should give you everything you need to actually build and compile jar files with SBT that are completely self-contained for Spark. Now, to actually create one of these jar files using SBT, it's called an assembly. And you need to set up a directory structure that looks like this. It's just what SBT expects. So you need to have a source folder and a project folder next to each other somewhere. Under source, you need to have a main folder, and under main, you need to have a Scala folder. And that Scala folder is where all of your source code for your Spark streaming job is going to go. Okay? So all of your source goes into the source folder. In the project folder, you just have an assembly.sbt file that you create that contains this one line that basically says I want to add a plugin in for SBT assembly, which is what it uses to actually create this self-contained jar file. And odds are this version number and these identifiers will change over time, so just to be safe, go check the SBT documentation on what that line should exactly look like right now. This line should work with SBT version 0.13.11. If you're using a later version, you'll want to double check what that line should be. So let's look at an actual SBT build file. So alongside the source and project directories you created, we need to create a build.sbt file. And this basically tells SBT what's in my project and what does it depend on. So let's say, for example, we're going to bundle up our word count example from earlier on, and we will do that shortly. We're going to give the project a name, word count, version 1.0, organization, and we're going to tell it what Scala version it depends on. So remember, we're using Scala 2.10 because that's what Spark wants. And for library dependencies here, we are just going to set up a Scala sequence here that contains all of the libraries that we need to actually run this example. So in our case, that will be Spark Core and Spark Streaming. Actually, word count doesn't even use Spark Streaming, but we'll throw it in there anyway just because we're doing a Spark Streaming course. So you see the syntax here. We have org.apache.spark. That's where it's coming from. Spark-core is the name of the package itself. The Spark version we're working with, 1.6.1. And provided means that this is actually part of Spark itself. So this is important. It's basically telling SBT that when I run something with Spark Submit, it assumes that Spark itself is installed, that Spark Core is present on the system. So we're not going to bother actually bundling up the Spark Core libraries themselves into our jar file because we already know that our cluster has Spark pre-installed on every node of our cluster. So there's no need to include the core Spark libraries, and that's what provided means. So there's an entire build.sbt file that's very simple. Now let's say that you had to add additional third-party dependencies. So for example, if we needed to add in our Kafka integration, well, you would just add another line into the library dependencies that would look something like this, org.apache.spark. Spark Streaming Kafka would be the name of the library we want, and the Spark version that we want to get it for, 1.6.1 at this time. And the beauty of it is that if there were any dependencies on that dependency, SBT could go fetch those as well and bundle those up for you too. Now, keep in mind I did not use provided on this line because the Kafka integration library is not part of the core Spark package. So if I were deploying this to a cluster that just had Spark pre-installed on it, it would not have Kafka pre-installed. And this tells SBT, actually, I do need to include the Spark Streaming Kafka jar file in my final assembly because I'm going to need that. All right. Now, when you have all those bits and pieces in place, all you need to do is go up to the root folder and run sbt assembly, and that will go off and produce a jar file. You'll find the output under the target/scala210 directory, and there will be your self-contained jar file. At that point, you can just run spark submit with just that jar file as an argument and nothing else because it has everything else it needs contained within it. So let's see how it works. It's actually pretty neat. Okay, let's see SBT in action. So I've already downloaded and installed SBT itself, so if you haven't done that already, go take care of that now. And also download the sbt.zip file from this lecture's resources, and that will have what we have to get needed to get started. So once you have all that in place, we can decompress the sbt.zip file from wherever you downloaded it. And inside we should see what we need to actually get started. So here's that file structure we talked about originally under the source main Scala folder tree. We should have the actual source that we want to package up as part of our deployment. And I'm going to open this up just to point out one thing. So we'll open this in WordPad for now. One thing that I changed here was instead of setting the master to be local within the code itself, I actually commented that out. And the reason is I want to be able to specify the master on the command line when I run Spark submit instead, because I want to be able to run this on a cluster and not just locally, right? So if I hard code local in the script itself, that will override everything else. And even if I run this on this gigantic Hadoop cluster, that line of code means that it's not actually going to use the cluster at all. It's just going to use the resources of the master node that I'm on. So that's another thing you need to remember. If you have anything in there that says I want to run locally, make sure you take that out, because you can just pass in -- master whatever you want that to be. And that can be local if you want, but it can also be something like yarn, saying you want to run on the local yarn cluster if you're on a Hadoop cluster. Or it could be, you know, the URL to your master node that you want to run from. So very important step there. Otherwise, this is just the same old word count example that we started with. Another thing that's worth noting is that it expects a book.txt file to be present alongside the application. So we have to remember to make sure that file is in place. And again, if we were running this on a cluster, that could be a path to an S3 file system or an HDFS file system or something else that would be accessible to every node on the cluster. So with that out of the way, we have everything where it needs to be. Let's take a look at the SBT stuff itself. So again, within the project file, we just have this assembly.sbt file. Let's take a look at what's in there. And as we had in the slides, we have this one line that just says I want to add the SBT assembly plugin into SBT. And let's take a look at the build.sbt file itself. Again, just like from the slides, we just give a name to the project, a version, organization, tell it what Scala version we're building against, and list our dependencies, which is just Spark Core and Spark Streaming in this case. And we're marking both of those as provided, meaning that we're not actually going to package them up, because we can safely assume that Spark is pre-installed on every node of our cluster, and it can already get to those libraries. But if you had additional library dependencies, you could list them in here without the provided flag. So let's go ahead and package this up and see if it works. Open up command prompt, and I'll go to where I extracted all of that stuff. Should look a little something like that. And now we can just run sbt assembly, and it will automatically look for everything that it needs. Assuming you installed sbt properly, it should already be on your path, and it should just work. And you can see it actually went out and it's compiling everything for us and grabbing all the dependencies and packaging it all up. And we're done. So let's take a look. If we go into target Scala like that, we should see our jar file, and sure enough, there it is. Word count-assembly-1.0.jar is the final jar name. And we should be able to just run this puppy with Spark Submit. But first, remember that it needs a book.txt file to actually read, and we did not specify that to be on a distributed file system, so I need to copy that over first. On a cluster, I could also use the -- files argument to move that into place, but for now, let's just copy that file where it needs to be. So I'm going to copy that from my downloads folder, where I originally downloaded book.txt, to here. So just make sure it's there, and now we can type spark-submit. I'm going to do -- local star like that to tell it that I want to run in every core, and then the name of the jar itself, and that's all I need. I don't need to specify a class name or any dependencies. And if we scroll up, we should see the results in there. Sure enough, it worked. So there you have it, a self-contained jar file created by SBT. And that is what you would actually deploy to, say, a cluster to actually run in the real world. So let's do that next. Actually run this script on a real, live Hadoop cluster. So the whole point of Spark is to run it on a cluster, and we haven't even done that yet. So let's take care of that little problem, and I'll show you how you can actually take your script or your jar file from your desktop or from your development system to an actual live cluster to run on and take advantage of horizontal scaling. So Spark is designed to be distributed, of course. The idea is that you have your Spark driver script, those things that we've been writing here and running locally, running on some master node somewhere that kind of orchestrates the entire cluster's activities. And it does that through a cluster manager. And there are several choices of cluster managers you can use. Spark has a built-in one that you can use if you want to, but you can also run Spark on top of a Hadoop cluster, and it will use the Hadoop Yarn cluster manager automatically if you tell it to. Another popular choice these days is Mesos. That's growing in popularity, and Spark works fine with it as well. But whatever cluster manager you use, it will be used to orchestrate different workers and executor tasks on each actual physical computer on your cluster. And depending on how things are set up, you might actually have multiple executors running on each individual computer, or you might have one executor per computer. If you're using virtual machines, you might only have one core per machine anyway. You kind of have to understand your hardware and understand how many cores you have available to you in total, how much memory you have available to you in total, and configure your job accordingly. So how do you do that configuration? Well, on Spark-submit, there's a bunch of parameters you can set, and probably the best advice I can give you is to actually run Spark-submit --help on the command line, and that will give you the up-to-date list of what these commands are and what they mean and when you should use them. Some of these parameters are only relevant if you're running on a certain kind of cluster manager. For example, num executors will specify the total number of executors that you want to run in your entire cluster, and you have to explicitly set that on a Yarn cluster if you're running on Hadoop. But if you're running in a Spark standalone cluster, you need to specify total executor cores to tell it the total number of cores you have available, whereas if you're on a Yarn cluster, you would just pass executor cores to give it the number of cores per executor. So again, run --help on Spark-submit to see the latest information on what parameters are needed for what kind of cluster that you're running on. But at a high level, some things you will always need to run is --master, telling it where to find the master node and what kind of a cluster you want to run on top of. So if you are running on a Hadoop cluster like we're going to pass in Yarn for the cluster manager master. And that will automatically communicate with Yarn through Hadoop to figure out what's available to it and how to distribute the resources of this job. Other options are Mesos or a specific host name and port if you're running it Spark in standalone mode. Now remember, if you specified a master in your Spark conf in your script, that will override what you actually put on the command line here. So make sure that production Spark jobs are using --master on the command line or some configuration on your cluster itself, as opposed to what's in Spark conf. Now, when you're running on something like Amazon's Elastic MapReduce, which will set up a Hadoop cluster for you, it does set up all of the configuration you need locally, so you don't actually have to specify anything for a master in that case. It will automatically do the right thing for you. So, just a little FYI, they do make life a little bit easier for you on some of these managed clusters that you can rent time on. So again, it's just a matter of understanding what you're running on, what it does and does not set up for you. Refer to the documentation of whatever cluster you're running on top of. Another important setting, though, is executor memory. So you want to make sure you're not using more memory than you have, and you want to make sure you have enough memory for the job you're trying to run. 9 times out of 10, if your Spark job fails, it's because you didn't give it enough resources. And that might be because you didn't give the executors enough memory to work with. 1 gigabyte's a good place to start, but again, you have to make sure you at least have that much memory free and available on each executor in your cluster to start with. And if you do see things timing out or things starting to fail throughout your Spark job as it goes on, odds are you need more resources. So that means either increasing the amount of memory on each executor or adding more executors, or both. Now, for the sake of example, we're actually going to spin up a real cluster on Amazon's Elastic MapReduce. So I already have an AWS, Amazon Web Services account that I can use to do that with. If you have one, feel free to follow along. Just be careful because this costs real money. If you're actually going to be spinning up clusters of computers, they're not cheap. I can probably spin one up for an hour and, spend 20 bucks or so, but if you mess up and leave this thing running by mistake, you're going to have a very large bill at the end of the month. So just for your own safety, I would encourage you to just watch for now. But if you are comfortable with what you're doing, feel free to follow along. Now, with Amazon's Elastic MapReduce service, it will basically rent you time on a Hadoop cluster that you can set up yourself for as large of a cluster as you want using whatever hardware you want. And you basically pay by the hour per instance. So each type of computer you can add to the cluster has a certain cost associated with it per hour. And for every hour you use, you'll be billed that certain amount. And they also charge you for storage space and for I/O over the network and to the storage. So they bill you not only for the computers you're using and the time you're using on them, but also the type of computer and how much storage space you're using and how much network activity you're using. The prices are actually quite reasonable, but like I say, if you're going to actually leave this running for a significant amount of time, it can add up quickly for an individual. But we have a very simple example here, so let's just go ahead and run it on a cluster and see what happens. All right, let's spin up an actual Hadoop cluster and run our Spark streaming job on it. So I already have an Amazon Web Services account that I've already set up, so that's already been done. It knows my credit card number and all that stuff, so money will start being charged here soon. But I will click on the EMR option here in my AWS dashboard console here, and that is their service for running a managed Hadoop cluster. And this can actually also let you run Spark as well. So I'm just going to hit Create Cluster here, and we'll call it. I'm actually going to run that word count example that we packaged up with SBT here. It would work the same way with any Spark job. So let's call it word count test. Logging, so you want to make sure you keep track of where it's putting these logs, record that somewhere, or actually specify a different destination if you have an S3 account, because if something goes wrong, you will have to check there to see what happened. So that can be very important for troubleshooting. I'm just going to turn that off for now because I know it's going to work. And we're going to launch a cluster where you're going to use the latest software, and we want the Spark option. Okay. Now I'm going to go with the defaults here of 3 extra large instances, 1 master and 2 core nodes that will be used as executors. And I've already set up an EC2 key pair as well. And we're going to use the Spark key one that I set up earlier. If you need to create one, if you're doing this yourself, there are existings here on how to create your own EC2 key pair. You will need that in order to connect to the master node of your cluster, which you'll need to do in order to do anything interesting. And that's pretty much it. So I'm going to hit Create Cluster. And I will start getting billed soon. So it's going to take about 15 minutes for these computers, these actual instances of my cluster to spin up. So Amazon has to go out to the cloud and actually find some virtual machines to actually allocate to my word count test cluster. And you can see right now it's provisioning them, and it's going to take some time to actually find that hardware, install the operating system on it, and to install all the software I need on it and boot them up. So through the magic of video editing, we're just going to wait for about 15 minutes here and come back when that's all done. Alright, so time has passed and my cluster is set up. You can see here that my master is running and my core is running as well. So I have one master running on a m3.xlarge instance and two executor nodes running on m3.xlarges as well. Now, one thing that I did change for this particular run was I modified that word count script to actually go to S3 in order to get its data. So if you take a look at what I did to the actual Scala code here, see, I changed the file path for the input file to be on Amazon's S3 service, and in Spark you can specify an S3N protocol to get that. So I have a bucket in S3 called Sundog Spark that I marked to be publicly readable, and in there I put my book.txt file. That way I can make sure that every computer on my cluster can actually access that input file. Now in the real world, if you're not on AWS, you might choose to use an HDFS file system instead, but the important thing is that you're storing that input data someplace that's accessible to every node on your cluster. Okay, so I've just made a modification to do that, and I repackaged this application in SBT, and I've uploaded that as well to S3. So I can copy that onto my cluster. So with that out of the way, how do I connect to my cluster and actually run stuff? Well, up here where it says master public DNS, that tells you where you need to go to actually connect to your master node where you can actually install and run your driver script for Spark. So if you click on this little SSH thing here, it gives you explicit instructions on how to actually connect to that master node on Windows or on Mac and Linux. So I'm just going to follow the instructions here. I've already installed a tool called PuTTY, which is basically a session terminal for Windows. All I have to do is copy that address, which is the fully qualified externally accessible name to my master node, open up PuTTY, paste that into the host name, and I need to actually set it up for my key file that I set up earlier. So under SSH auth, go to browse, and I'll go to my sparkkey.ppk file. That'll be different for you depending on how you set up your private keys. And hit open, and I should get a connection to my master. There it is. So check it out. I have an Elastic MapReduce cluster with Spark pre-installed on 3 different machines here, so that's kind of cool. So let's get up and running. So I'm going to first copy my jar file that contains my Spark code to this master node. So I'll do AWS S3 CP S3 sundog-spark word count.jar. And what this is telling it to do is to just go to copy this word count.jar file that I copied to S3, just as an easy way to get it onto this master node. Great. All right, so now I have word count.jar installed on this master node, and I can just run it. So again, on EMR, it automatically sets up all the configuration for you. So there's not a whole lot you have to do. I mean, you might want to tinker with the executor memory settings if you start to have resource problems, but by and large, the defaults are pretty useful. So all I have to do is type spark-submit word count.jar. And remember, SBT made sure this was all self-contained. I don't need to specify a class file or anything like that. I already made sure that my input file, that book.txt file, is accessible to every machine on the cluster. So when I hit return here, it's actually going to go and run this very simple little word count application on the entire cluster. And obviously it's overkill to use a cluster for something as simple as this, but this could be a very elaborate Spark streaming job that was connecting to a Kafka cluster and processing massive amounts of data, right? The same procedure would apply here. I just don't happen to have a giant website accessible to me right now to do that with. So let's go ahead and see if it works. Can ignore all these info and warning messages. And it's going to take a little bit of time to distribute this out and actually spin up all those clients, but it is actually doing it. This is such an incredible waste of computing power, but it's just for educational purposes, right? And there we go. So across an actual Hadoop cluster using the Yarn Cluster Manager, I have counted up the words in my little book. And here are the results. So you can see here it actually worked. We ended up with the word foolproof occurring once, the word of with a period after it. If you want to expand on this, you could actually strip out punctuation and make it work a little bit better. 3 times, salesperson 5 times, so on and so forth. So it actually works. There you have it. Actually running Spark on a real cluster using Hadoop with a prepackaged jar file made using SBT. So that's basically the procedure you're going to follow in the real world for running your Spark streaming jobs on a real cluster. Pretty cool stuff, huh? So we've learned a lot in this course so far, you know, from writing simple Spark streaming examples to doing some pretty advanced stuff and actually ultimately running it on a real cluster and seeing it work in action here. So I'm pretty happy about that. Last thing we need to talk about is some troubleshooting steps and some tuning steps for running Spark on a cluster. So let's wrap up with that. So now that we're actually working with real clusters, let's talk about tuning and troubleshooting when you're on a cluster. Now, as much as we talk about Spark and Hadoop and everything being scalable and distributed and reliable and all these wonderful things, the sad reality is that if you don't give your cluster enough resources for what you're asking it to do, it will fail. And it will fail in probably cryptic and strange ways that will be time-consuming and expensive to figure out. So the more you know, the better. First tool that you have at your disposal is the Spark UI. So this is especially handy on Spark streaming jobs because they just keep running forever, so that UI can give you a real-time look into what's going on. So if things seem to be backing up for some reason, that can give you some visibility into it. And what happens is it just automatically launches this user interface on port 4040, and you can just open up a web browser to port 4040 on your master node and take a detailed look as to what's going on. Now, unfortunately, on Elastic MapReduce, if you're using AWS like we just did, it's pretty complicated to actually get that working. You need to open up an SSH tunnel and a proxy server and all this stuff. But if you click on that connections item on that cluster page we were looking at where we saw the SSH connection information, they have some instructions of what you need to do there. It's pretty elaborate though, but hopefully you're just running on your own cluster where you don't have all these weird security issues going on and you can just connect to port 4040. So let's actually take a look at it, just running locally on our PC, and just have a little tour of what's going on in the Spark UI. Okay, so just for fun, let's kick off that tweet printer Spark jar that we made earlier in the course. I'm just going to kick that off with Spark submit like we did before. And let that kick off. Make sure we start getting some tweets. There it goes. All right, so now to look at the Spark UI, I can just open up a browser. And since this is actually running on my local host, I can say localhost 4040 to connect to it. That's all there is to it. And here we have it, a live view of what's going on under the hood with Spark streaming. You can see here that we have a history of the jobs that we've run, and currently we're running this job here. And let's just go ahead and dive into it, what it says here. Pretty cool stuff. So right now it's making RDDs, and this is the whole DAG visualization. And you can see it's a very simple task that we're asking it to do. It's really just doing one step here, so there's not a whole lot to see. But you could actually see the chain of how it's putting different components together if you had a more complicated job. Event timeline, also kind of interesting. You can see what's been going on. We basically started the driver script, and then it's been running ever since. Not too surprising. More interesting, let's go to the streaming tab here. This is pretty cool stuff. So this actually shows you kind of the throughput over time, and if you're actually running into some sort of a bottleneck, you can potentially see things flatlining here and narrow down what the bottleneck might be. So you can see here processing time is nice and steady, input rate nice and steady. Everything seems to be keeping up just fine, which isn't too surprising given that we're not really asking a whole lot of it. But you know, if you did see something spike over time, then that might imply some sort of hardware failure or network failure or something going on that you might need to look at. Obviously, ideally, the cluster would detect this and automatically reconfigure things, but that doesn't always happen in practice. Like I said, if you throw too much work at a cluster, if you just don't give it enough computing power, and that can be enough CPU cycles, it can be enough cores, it might not be enough memory, things can start to back up even on a cluster. So, you know, it's still possible to just not have the right size. And if you see things starting to trend upward over time when they shouldn't be, that might be nature's way of telling you that your cluster just isn't big enough. We can also take a little quick tour of the other tabs here, the actual executors running here. There's only one in this case, since we're just running locally. Environment. So if you want to get any specifics about the environment setup on the actual job itself, this can sometimes be useful for diagnosing problems. You might want to check what Java version you're actually running, what Scala version you're actually running, what the actual properties of Spark are. These are all things that might let you troubleshoot what's going on. So for example, if it couldn't find a class that it needed, looking at the path might explain why. Storage requirements. Obviously, I'm not storing anything. I'm just printing out tweets. And finally, the Stages tab. Kind of back where we started from. And we can look at individual jobs. All right, so there you have it, a little tour of the Spark UI. So, you know, if If you want to check on the health of your Spark streaming job, this is kind of the place to start. It can give you a good overview of what's happening, and obviously the streaming tab would be the most relevant and the most interesting to watch over time. You can see things are still healthy. I am merely chugging out printed tweets. Woohoo. So that is the Spark Streaming UI for you. Very useful tool. Let's talk about some performance tips for Spark Streaming. Very important to make sure both that your job runs as efficiently as possible, but also to minimize its hardware requirements. So bigger clusters cost more money, so you want to make sure that things are running as efficiently as possible with the resources that you have. And maybe you only have a certain amount of budget for how much hardware you can throw at a problem. You might have an upper bound that you need to stay within. So here are some performance tips, just general stuff. First of all, like we've talked about before on a couple of occasions, if you are going to perform multiple actions on the same RDD, make sure you cache that RDD first. That will prevent Spark from going out and recomputing it a second time. That way you can just keep a copy of it in memory. You can perform one action on it and then perform a second action on that same cached copy of the RDD instead of going out and reprocessing the whole thing. So that can make a big difference. Look for spots where you're getting an RDD from a D stream and doing more than one thing to it, more than one action, okay? As opposed to a transformation. I'm talking about actions here. One other thing to watch out for, make sure your executor memory isn't too large when you're running on a cluster. So remember there's a setting that you can pass to Spark Submit for the executor memory size. And if you make that too large, you might end up causing things to swap. So basically that's setting your heap size for Java underneath the hood. And if you set that to be more than the available memory that you actually have available, then your job will merrily fill that up and start swapping to disk. And obviously that can cause performance to do horrible, horrible things. So although it seems a little bit counterintuitive, setting your executive memory to be too high can actually have adverse effects on performance. So be aware of how much physical memory is actually available to each individual executor. Think about how many executors you're configuring to run on a given host, how much memory you have available on that host, and remember too that if you're running on a virtual machine, you might only have a subset of that memory actually available to you. So one thing you can try is, if you don't think you're actually using all of the memory available to your executor, try reducing that amount. It could actually help. However, when we're talking about the sum total of your entire cluster as a whole, usually more memory and more cores are a better thing. So the most common thing that I see in practice is a job will just hang because some executor will just fail to respond. It will seem to just go into never land, and usually that's a sign of you're asking too much of your cluster. So oftentimes you can just throw more hardware at the problem. That's the whole point of being horizontally scalable. But if you're seeing reliability problems with your cluster, or if it's just not being able to keep up, you might just have to add more hardware to it. Sad but true. And to try to arrive at the right size, one thing you can do is to start off with a subset of your data, or maybe a smaller stream, or like only sampling parts of the stream that are coming in. Get a feel of what you can actually run safely on the hardware you have, and then you can start to scale up the input data that you're processing and scale up the amount of hardware you're using accordingly. So sometimes you need to scale down the amount of work you're doing to try to arrive at a good estimate of how much hardware you really need. Think about partitioning versus your cluster size. So if you are repartitioning or doing some transformation on an RDD or a D stream that will cause it to either grow or shrink in size, it might be appropriate to repartition that RDD or that D stream to get better parallelism. So, if you're actually going to split things up into a bunch of different keys, you want to try to get roughly as many partitions as you think you have executors for optimal performance. So think about that when you're looking at your code. And if you're actually shrinking an RDD and repartitioning, you can use coalesce. So if you want to repartition down to a smaller number of partitions to a smaller RDD size, use coalesce instead of repartition, because that avoids the need to shuffle the RDD data as it goes down. So that can save you some time too. One other trick, the default serialization that Spark Streaming uses is Java serialization, and it's not the most efficient thing in the world. You can actually use what's called cryo serialization, which is quite a bit more efficient. And to use it, you need to do a couple of things. One, you need to set this configuration setting shown on the slide, and you also need to register all of your custom classes that's in your code with cryo using this conf.register cryo classes method. And the only reason that cryo isn't the default setting in Spark is because you do have to do this manual configuration of your own classes. So, they didn't want that to trip people up and people say, why doesn't anything work? Because they forgot to configure their classes. But if you do take that extra step, you can squeeze a little bit more performance out of your Spark Streaming application that way. Moving on to stability. So How do you make sure that your cluster keeps on running? I mean, with Spark Streaming, that's a very important concern because these things are intended to run for very long periods of time continuously, right? One thing, use a Mesos or a Yarn cluster if you can. I mean, they've been designed from the ground up for reliability and stability, and a lot of people are using them in the real world. So, a lot of people have worked out the kinks in it already for you. So the technology is there, you may as well use it. Mesos is a very popular choice now, and if you have access to a Hadoop cluster, you can use the Yarn cluster manager that is part of that as well. Also use Zookeeper. So remember, if you are using the Spark standalone cluster manager, Zookeeper might be necessary in order to prevent a single point of failure on your driver script. So Zookeeper is basically a free utility that can monitor processes and automatically restart them if something goes wrong. So instead of waking you up in the middle of the night, Zookeeper can handle that for you potentially if it's something that can be recovered from by just restarting. And remember earlier in the course we talked about how to actually make sure you're creating your context from a checkpoint directory and only creating a new one if that doesn't exist. So that way if you do restart your driver script, it can pick up where it left off. Finally, also make sure you choose the executor cores and executor memory settings wisely. Those are relevant to Yarn. And executor cores is basically how many cores each executor can use. And executor memory is how much memory each executor can use. So make sure that the total number of executors on your cluster does not exceed the number of physical cores and physical memory that you have. You want to keep a good amount of headroom there because Java actually needs a little bit of extra space in terms of memory to manage its memory well and make sure garbage collection happens quickly. So don't go too high on those. You need to be conscious of what the resources are on your physical cluster versus what you're telling it to do. And again, if you're using something like Amazon's Elastic MapReduce service, it will try to set that for you automatically based on the cluster that you set up. Make sure the receivers you're using are reliable. We talked about this in the integration chapter, but just a reminder, some receivers are better than others. So if you're using a push-based receiver that just pushes data to Spark Streaming, something goes wrong, you're going to lose all that data while the cluster's down. Pull-based models are superior because you can actually go out to the data source and say, pick up where we left off, for example, from HDFS. And of course, if something does go wrong, look at your logs. The reason is probably in there somewhere. You'll want to filter through for actual error messages and not look at all those info and warning messages. And if you're actually running this from hand from the command console, you can scroll through your terminal to see what actually happened there. Usually there'll be a little bit of a call stack there and an error message that's actually helpful. Worst case, you'll see something about individual executors failing or hanging, and if that happens, it's probably a sign that you just don't have enough resources on your cluster. So that's Spark Streaming and Spark in general, performance and stability tips for you. Should make your life hopefully a little bit easier when you're actually running this stuff in production. So congratulations, you made it to the end of the course. We've covered a lot here. We actually learned a whole new programming language, Scala. We covered the basics of Spark itself. We delved into a bunch of hands-on examples with Spark Streaming, and you've learned pretty much every nuance of it at this point. And we've talked about practical advice for actually running Spark Streaming on a real cluster and running it in the wild outside of your integrated development environment. So good on you. This has been a lot of material, more than I even expected. Where do you go from here? Well, there are some more resources you can look at. Honestly, Spark Streaming is a very relatively new technology, so there's not a whole lot of resources out there on it yet. But there are some books I can recommend if you want to expand your learning relative to the topic. First of all, if you want to learn more about Scala and the Scala programming language, we really only touched on the basics in this course, so there's a lot I didn't cover, like object-oriented Scala or handling threading properly and some of the finer nuances of the language that we kind of glossed over. If you do want to learn more, I highly recommend O'Reilly's book, Learning Scala. It's a good one. This is how I learned the language myself. I just read this cover to cover, and after that, with this by my side as a reference, I was able to write Scala programming pretty easily. So it's definitely a good one if you want to learn more about Scala. As far as Spark Streaming itself goes, I could only really find one book on it, and it's this one by Pack Publishing, and it's called Learning Real-Time Processing with Spark Streaming. You know, these Pack Publishing books are sometimes kind of a mixed bag. This one's okay. I think there's actually some really good information in there. It's no O'Reilly book in terms of formatting and editing, but it's still well written and there's some good information in here. There's also some stuff in here that I did not cover in the course. For example, integrating Spark Streaming with the GraphX library. And there's also some examples in here of using Spark Streaming with Java instead of Scala. So if you're much more comfortable with Java and you're still comfortable with dealing with things like Maven and whatnot, this might be a good way to get an introduction on doing Spark Streaming with Java instead of Scala. And finally, if you want to just learn more about Spark in general, another O'Reilly book that I like is Learning Spark from O'Reilly. And if you want to learn more about not just Spark streaming, but all the other components of Spark, including Spark Core, MLlib, GraphX, and Spark SQL, there's a lot more in here as well. And you can learn a lot more about the stuff you can do with RDDs and how they all interoperate with each other. So also a highly recommended book. I don't get any money if you buy these books. I'm just giving you my personal opinions on things I've found helpful. Beyond books, obviously the Spark website is a good place to look for new information. So spark.apache.org, and there is a Spark streaming page there as well. There's also a mailing list for Spark, a user mailing list that you might want to subscribe to, and most of it's people just asking for help on various problems, but if there is some new development, you'll probably hear about it there first. Spark is evolving quickly. They come out with new releases pretty often, and they have some pretty exciting new features in each one, so you definitely want to stay on top of what's happening in that world. So good luck on your journey. If you are at the end of the course at this point, I would appreciate if you could leave a review on this course. Let us know what you think. Hopefully you enjoyed it. And if you actually left an earlier review in this course earlier on, I'd appreciate if you could go back and update that review, based on the complete picture of where you've evaluated this course as a whole. That will be most helpful to the students, and it'll be helpful for me as well. If you did have any problems or concerns about the course, feel free to send me a message directly or put something in the discussions or Q&A for this course. I'm here for you. I'll listen, and I'm always open to feedback. So anyway, thanks for coming along. I hope you enjoyed this course, and I hope you found it educational and useful and a good way to further your career in big data processing. So go forth and stream with Spark Streaming. Thanks again.